We can see it. Okay, yeah. So we're very pleased to have Misha here for his last very exciting lecture.
Thanks, Boris. Yeah, so I thought I would start with a simple computation, which is I'll derive the convergence for PL conditions using Polak's argument. And first, to elaborate a little bit on the point I made yesterday about the problem with convexity. So what is the problem with convexity? Why is it so fragile? And the mathematics of this is really quite simple. If you take a second derivative, if you take second derivative of the composition, f composed with g prime prime is equal to f prime prime g times g prime squared plus f prime composed with g times g prime prime, right? Just in one dimension. And even if f is convex, so this thing will be positive, but you have no control over the second term here because you just don't know anything about f prime, and you have no reason to think that the sum will be convex, the sum will be positive. So you have no control over the second derivative of a composition, even if both f and g are really nice functions, or even if both f and f. So that's the problem with convexity. Recall now the PL condition. The PL condition is the following: grad f squared is bigger than mu f of x minus f of x star, where x star is the minimum, the minimizer of f. And let me very quickly do the computation, which is, I think, very elegant due to Wapnik, showing that this is condition. This condition is exactly, did I say Wapnik? It's Polak. The completely different Russian guys. Showing that this condition implies convergence of gradient descent. And for that, we need something called L smoothness, which is essentially Lipschitz condition for the gradient. So Lipschitz condition for the gradient is this, right? The gradient of f of y minus f of x is less than L y minus x. And an equivalent way to write it by doing some sort of integral is to say that f of y is less or equal than f of x plus inner product between grad f of x and y minus x plus L over 2 x minus y squared. So that's what's called L smoothness, if you haven't seen it, which is the same as Lipschitz for the derivative. And now putting these two things together, we get a derivation for convergence. So let me just go over it. So first, gradient descent Wt plus 1 is equal Wt minus eta grad f Wt. Okay, very, very simple formula. Actually, when I was writing this, I'm like, okay, this is like, it's like the simplest thing you can imagine. Now, what do we have? We have the following. We have that f of Wt plus 1 is less or equal, and I'm using, so y here is Wt plus 1, and x is Wt. So this is less or equal than f of Wt minus eta grad f of Wt. But now grad of f of Wt, of course, is, I'm sorry, I'm writing this grad f of Wt times y minus x, which is simply Wt plus 1 minus Wt. So as you can see, this is grad f of Wt, but y minus x is equal to eta grad Wt. So this is and plus L over 2. Now x minus y, again, Wt plus 1 minus Wt. So I have here L eta squared grad f of Wt squared. So write it out a little bit more compactly. This is f of wt minus eta plus L over 2, there's no L here, eta squared times grad f of wt squared. Okay, so that's essentially it, because what we do here is that we say that f of wt plus 1 minus f of w star is less or equal than f of wt minus f of w star. I'm just subtracting it from both terms. Plus, and here I'm going to put eta equals, so eta equals 1 over L. So plus, or rather minus, I should say. Minus, and what do I have? 1/2 1 over L grad f of wt squared. Now, using the PL condition, I know that this is bigger than mu times f of x plus t minus f of x star. So this is equal to f of wt minus f of w star. And please check it. I'm going through it quite quickly. 1 minus 1/2 mu over L. And that's it. So that's it. Now, f of wt plus 1 minus f of w star, right? Because I can do this recursively. So this is less or equal than f of w naught minus f of w star times what? Times 1 minus 1/2 mu over L to the t's power. And you can show that mu over L is less than what? Or 1/2 mu. So actually, usually there is no 1/2, but I didn't put this extra term to it in the definition. But that's basically it. So, and you can prove that mu over L is less than, that this quantity is less than 1 in the parentheses. So that shows exponential convergence. Now you see, this is actually an exceptionally simple argument. Actually, it is simpler than proving it for convexity. That's another indication that PL condition is something quite basic, quite fundamental. Okay, so let me now switch. Oops. I'm going to switch this back to the presentation mode. Okay, so can you see the slides now? I just went back.
Yeah.
Now, what do we have here? So we have this PL condition. This first order very nice condition that guarantees convergence of gradient descent, and it's invariant under changes of coordinate, which I haven't discussed. I'll discuss it a little bit more. There is a problem here. And what is the problem? And the problem is that if you look at the condition, you need to know something about the minimizer W star, right? You have to know the loss of the minimizer, but you also have to prove something about the minimizer, right? You're using this condition to show that it converges to the minimizer. So this is a little bit of a chicken and egg problem, right? To know that you prove that you converge, you have to know something about the minimizer itself. So for convex, I should point out that convex or strictly convex functions satisfy PL star, PL condition. But you can see this is a little bit of an issue, and maybe that's why it hasn't been used as much as maybe it should have been because of this kind of chicken and egg problem. So basically, if you don't know that W star exists or W star has some property, how can you prove convergence using this condition? Turns out that there is almost a trivial fix for this. And this is what we call PL star condition. And the fix is simply to remove this term. And the only thing we need to assume here is that the loss function is non-negative. So it's the same condition as PL, except it doesn't have this L of W star. So if you know that L of W star is equal to 0, then of course it's equivalent. But notice it's not equivalent as stated because you are not assuming here that anything about existence of W. Now this condition is very nice because, well, you can verify this point twice, right? Because if I'm claiming that something is PL star, mu PL star, then I just need to check this condition at every point separately. I don't need to have any global information about what it does in the set. So this is pointwise defined. And now, by the same argument as I just gave you, the Polak's argument, it guarantees existence of a solution if it holds in some ball of some radius. Radius is actually 1 over mu, essentially, or 1 over mu. Moreover, it guarantees convergence of stochastic gradient descent in a ball, which is quite nice, although the ball of a slightly larger radius. And it is actually controlled by the tangent kernel. And
Sure.
This is the analytical condition, yes.
So I think for this, you need to assume that the minimizer is exactly at, or the value of the loss at the minimum is exactly 0, right? Otherwise, near the minimum, you can't hope to have PL star satisfied, right? Like if the loss minimum were strictly positive, then presumably the left-hand side is 0 and the right-hand side is.
So Boris, that's a good comment. So it is true that with this condition, the minimizer will have the value of the minimizer will have to be exactly 0. But the good thing is that you don't have to assume anything. You just need this condition. And this condition will imply the
yeah, it's a minor point. I just can't help myself. You know?
Yeah, no, you're absolutely correct. But think about this, actually, it's kind of amazing because this guarantees, so if you think of the loss function as that loss function for the system of equation, right? Then saying that loss is equal to 0 is the same as to say that you can solve the system of equations. And this is a condition for when the system of equation is solvable. It's equivalent thing, which is crazy, actually, if you think about this, because this is some sort of arbitrary nonlinear system of equations. And you have such a simple condition. You got to think about algebraic geometry. It's extremely intricate when this existence, when the solutions exist, what kind of geometry they have. This is a very simple way to think about our parameterized systems. Okay, so controlled by tangent kernel, and now let me define the tangent kernel. I'm following the terminology from Jacot et al. Paper. But it's actually the tangent kernel itself is just essentially the derivative. So if you have a map from Rm to Rn, its derivative, or differential, whatever you call this, is a matrix, M times N. And the kernel is simply that matrix times that matrix transpose. So a kernel is nothing else but an n times n matrix valued function defined on the space. Okay, is a function of W. So what is good? What is good for? And here is a proposition, and it's gives you an analytic condition for PL star. And the proposition is very simple. If you have the square loss, as I define, so your loss function is a square loss, then if you can control the minimum value of the tangent kernel, so the minimum value of the tangent kernel is that mu and mu PL star. So you see the condition itself, it's not quite analytic, but this is actually very analytic because you have this matrix and you're just looking at the smallest eigenvalue. And I see there is a question. So PL star guarantees interpolating solutions for overparameterized least square loss. Correct. So L of W star equals 0 is not an assumption. So if PL star holds in a ball of radius 1 over mu, then the solution will have, the equation will have a solution at that ball. That's a theorem. Okay, so actually the proof, I'm not going to go over the proof, but yes, you can see it's just 2 lines. It's really simple, you just write it down. Something similar also holds for non-square laws, but it's not quite as clear. So this is nice because now you have to actually just know something about the minimum eigenvalue of the derivative of your function. And this is something that we already discussed a little bit, and it goes back to Boris's comment about the conditioning of these matrices. When overparameterized tangent curl well conditioned, well, it's df times df transpose. And basically, when the matrix is long and thin, it's well conditioned. The smallest eigenvalue is separated from 0. Why? Because if you have a bunch of rows, so imagine by matrix is very thin, it's just one row, right? That row is always non-degenerate unless all of its coordinates is equal to 0, right? That's the only way it can be degenerate. So the longer the vector is, the harder for all of these coordinates to be 0. And actually the, that's exactly what happens for, for more complex matrices. In particular, for Gaussian random matrices, you can, Chen and Dyer actually gave a computation for explicit estimation of the condition number. Okay, so, oops, what did I just do? So basically that's the intuition. Skinny matrices are well conditioned. And yeah, so if it's just one row, then it's just a norm. And unless the norm is very, very small, you're going to have well-conditioned matrix. Right, because if you have a skinny matrix times a very tall matrix, the product of it, so if it's just 1 by n and n by 1, then the product if it's just one number, and that number is a norm square. So notice, by the way, here, that the way I wrote it, only overparameterized systems can be well conditioned at all, because it's lambda min. If you do the opposite product, the lambda min is always 0. Because it will be the product, the size of the product is n by n, and it will be rank deficient unless m is bigger than n. So actually, you can prove it. Again, it's a simple theorem. Only overparameterized kernel can be well conditioned. And in fact, if you have a loss function f of w minus y of the form we considered, this loss function cannot be PL star at some fixed point w naught, it really doesn't matter, independently of y, unless it's overparameterized. So if it's not overparameterized, there is always a y, such as this is not PL star. So in some sense, PL star kind of happens almost if and only if you're overparameterized. Okay, so now this is the picture that you may have in mind. Is that consider now this kernel, this is a matrix value function. And how big is this matrix? This matrix is n by l. Now you have
one question, Misha.
Yes.
It seems that the PL condition is in the general PL condition, mu is general for all the space, but in this case we are working just with the minimum eigenvalue of the neural tangent. And this is just local information. When we move from this local information from this neighborhood to another neighborhood, the mu can be different because we linearize the problem different. So this only works if our space of solution is in a neighborhood?
So this is correct, and let me point out. So this condition is perfect local, right? So we have to have it at each point separately. To get a solution, we need to have this condition for every point in a ball. So what we need a uniform ball on the smallest eigenvalue. Okay?
Okay, thank you.
But think about what happens here. Suppose my kernel, suppose df, suppose f is just from R. So think about f. Wait. F goes from Rm to Rn, right? Suppose it just goes to R, just make it very simple. So that's one equation with m variables. Now, what happens is that the kernel is just a simple number in that case. It's just norm of the gradient squared. What is going to happen is that lambda mean of this number is simply its norm. And the norm, so it's a real valued function on my space, and my space have m dimensions, and I am forcing that one number to be 0, right? So I will have a manifold where it is 0. That's a bad set, where I cannot say anything about lambda bit, where the PL condition is broken. But this is a set of, you know, some codimension, in that case, codimension 1. So what you have something like that. You see, you have a bad set. And then what you expect is that there is some neighborhood around the set where PL condition doesn't work, when mu is, it still works, but mu is very small, so it's not useful. But away from the set, mu is somehow sufficiently large and you can prove convergence. So that's the intuition. Of course, we will have to prove it for specific things that this is true, but that's basically the intuition to think about. I will discuss how to prove it for neural networks. By the way, you know, in this case, this is not neural tangent kernel as such, it's just tangent kernel. Right? I'm not assuming anything about the structure of F itself. Okay, does it answer the question?
Yes, thank you very much.
The intuition is this picture. Now, existence of solution, this is the theorem of Pollack, or some reformulation of the theory of Pollack's original theorem. Basically, a system of nonlinear equation well conditioned in a ball of radius 1 over lambda mean of k, so uniformly separated from 0, has a solution in that ball. Now, a complement to that, which also fits into the original argument of Pollack, is that, which I just showed you actually, gradient descent converges exponentially to a solution, and the rate is controlled by a condition number, which is, so you know, for the linear, for matrices, condition number is lambda max divided by lambda mean, right? Here, it's not lambda max and lambda mean quite of the same thing, lambda max of the Hessian and lambda mean of the kernel. But lambda max is really not a big deal for the square laws. You can bound it by some sort of reasonable things in it. So it's a lambda mean that we need to worry about. Lambda max never causes us problems. And if actually the system is linear, then it reduces to the standard condition. So it's a real generalization. Now, the interesting thing is the same thing exactly gives you convergence of SGD, and it has the same rate, always as well. It has exponential rate. The coefficient there is slightly different, and actually I'm not sure whether, we basically have to take a smaller step size. And it's not completely clear whether it's some sort of shortcoming of the analysis or it's a real thing to do the smaller step size. But I thought I would make one comment about this because it's, I think, kind of unusual to think that stochastic gradient descent converges exactly with a fixed step size. We kind of think so, and there is this intuition about stochastic gradient descent. So stochastic gradient descent is simply gradient descent, where your estimation of gradient is not exact, it's noisy. And in that case, you would think you should oscillate. That doesn't happen in the interpolation, under this interpolation condition, which is especially given as by PL, because somehow your gradient, stochastic gradient descent, the noise is not additive noise. It's a noise which is given by the sampling process. And that actually essentially multiplicative noise. So what is happening if, and you can think of stochastic gradient descent as following. So suppose I have these two equations, f of w. So I have two data points which correspond to two equations. F of w of x1 equals y1, fw of x2 equals y2, right? So you can think of them as these two manifolds, and they intersect at w star when both conditions are satisfied. Now, what does stochastic gradient descent do? So imagine I'm alternating gradient steps in these two directions. I mean, you usually choose them at random, but it doesn't. So the first one gives you kind of a partial projection onto the set of this constraint. So you take a step toward the set of this constraints like this. Then you take a step toward the step of this constraint like that, and so on. And as you can see, you are actually converging pretty quickly toward that point by some sort of alternating projection. It's close to the method of alternating projections. Why is it different from the classical case? In the classical case, you don't have interpolation, and these constraints are usually not compatible. And if your constraints are something like this, the gradient would just oscillate. It never converge. So what you have to do, you have to change the learning rate, or you can average or do something. So that's why this is different from the classical. So in some sense, you can think that when you pass through the interpolation threshold, your additive noise becomes multiplicative noise, informally speaking, at least. Varun, question.
Yeah, I had a question about if you're already like, let's say I get lucky in my first gradient descent step, and I'm like interpolating at least one solution and stuff. So I'm wondering if like, let's say the initialization started on one of the curves. It seems like after you do like the SGD, you would like maybe go outside and then come back and have this behavior again, or like.
Yeah, exactly. You would just leave it, right? And
Okay, cool. Well, just
because unless you start at the point when all conditions are set, then of course you don't move, right? Because you're already at the minimum gradient. All of these gradients will be zero. So at this point, all gradients with respect to each constraint is zero. In the classical case, there is no such point because the constraints are not compatible. That's a difference. Okay, so let's continue. So in a sense, here is a very interesting thing. So when first we expect big systems to be well conditioned, and second, for well-conditioned non-linear system, gradient descent behave very, very similar to the way it behaves for linear system. So in some sense, this non-linear systems kind of like linear system, except their conditions are by that constant. This is not at all true in underparameter restriction. This is completely off. So this is the sort of complete summary of the landscape, and I think it's quite interesting. So you have this bad singular set when your conditioning number is 0, and you have a kind of set which goes around it when your condition number is small. Oh, the condition number is large, I'm sorry, the smallest eigenvalue is 0. And if you're away from the set, you have this nice thing that in every circle, in every ball of radius 1/mu, you have a solution. So, and if you start at the center of this ball, you will guarantee to converge to a solution. So in a sense, it's quite interesting is that solutions kind of like curve space filling curves, you know, like this curve which fill the space. So they behave kind of like that, except they don't fill it that tightly. They fill it with something with like a fill 1/mu. So you can imagine that there are some.
Can I ask you something, Misha?
Yeah.
You know, I've never really thought about it, but is it either easy or is there something out there which actually makes that statement precise? You know, you take a random system of kind of appropriately high dimensional nonlinear equations with the right overparametrization, then with high probability, you know, blah, 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 blah. This picture somehow roughly holds. because I mean, I can't, I understand the intuitive reason you're drawing it, but it's a little hard sometimes to have intuitions, right? You have a 2D picture and then like, we're talking about a 1,000,000 dimensional space or something. And so I don't know what's going on.
Yeah, fair enough. So for neural networks, we know that it holds, at least with NTK initialization, we know that it holds. It's exactly right. For general system, I believe, so let me say just a couple of words about this. I believe it's far more general than what we can prove for neural networks. But the proof techniques, which I'll just outline, I'll outline it briefly, they somehow seem kind of limited, and they rely on this remarkable fact of the neural tangent kernel is constant, which is wonderful, but it seems limiting because intrinsically there is nothing here which requires a kernel to be constant or anything which relies on this. Because what is happening is that if you have a very skinny log matrix, it's going to be well conditioned generically in some sense with random coefficient. And as long as it doesn't change too much in the ball, you should be okay. So this seems like any random system should have this property, but we cannot prove. The proof is much more special.
Right. I mean, for the neural network case, basically, you don't even see the singular set.
Yeah. So if
right,
you
in a
start
big
with
enough ball around
initialization, you never see it. Yeah.
So
of course, you can start close to it, right? You can start it.
Yeah. Right. Okay. Thanks a lot, Misha.
Okay. So how to control conditioning? So maybe a specific answer for, or not a complete answer, but some specific ways to doing it. And there are two ways to really that we can think of to control condition number. And one way, this is not an exclusive, this is not a complete list by stretch of imagination. This is just things that we have to know. So suppose you have lambda mean at one point, and you somehow know that it's not too small by some random matrix argument. Then if you have a bound on the Hessian, right? So lambda mean is like the first derivative. Hessian is the second derivative. So if the second derivative is small, the first derivative doesn't change. This is called mean value theorem, or whatever, one of those theorems from calculus. So if you know that Hessian is sufficiently small compared to lambda mean, then you can, and lambda mean is separating from 0, then you can guarantee this in a ball. So that's a Hessian, what you can call Hessian control. This requires, of course, that Hessian is much smaller than the kernel. The second thing is actually quite different. It's a composition control. And basically, it's I like the second one because it's very natural. It basically says if you have a change of the coordinates and this change is somehow well behaved, the Jacobian is not too crazy, then the composition will also be PL, we discussed already, and you can control lambda min of K because derivative essentially multiply, right? That's all there is to it. So there are the two tricks, but you can see this is not, like you see how strong the first Hessian control is, right? I have to assume that lambda min is much larger than supremum of the Hessian. So the first derivative is larger than the second derivative. But I don't really need it. I just need to know that the lambda min doesn't vanish, right? Hessian can be large and it still won't vanish. But it's hard to prove. So that's the annoying thing. But the wonderful thing about this is that actually this is enough to prove very general convergence of neural networks, just these two things. So this is a more specific thing for Hessian control. It's basically if L of W is mu PL in a ball of some radius, which is like inverse proportional to the norm of the Hessian. And if this ball is sufficiently large, then you can guarantee convergence. The smaller the Hessian is, the larger that ball is going to be, and the better your guarantee. And the composition control I already discussed. It's just a chain rule. So now let me very briefly discuss this constancy of neural tangent kernel. And I would like to make a couple of comments on this because I think there is some confusion about this. I think it's important to make it clear what this is. So this is really, I think, a really remarkable recent finding originally by Jacob, Gabriel, and Hogler. And they showed that tangent kernel is constant for some infinitely large systems. And well, they actually proved that it's constant along the optimization path in the functional space. And the follow-up work by Lee et al., they showed that it's actually in the parameter space as well. But what does it mean that the NTK is constant? And one thing I would like to point out is that I prefer to call it actually transition to linearity for the following reason, is that a function f of w is linear if and only if its NTK is constant. It's tangent. I should not say NTK since there is no neural network here. And it's not obvious, actually. You may think it's obvious, but it's stated like this. This is not obvious. Because think about a function with the single output. The NTK for this one is simply norm of the gradient squared, right? So norm of the gradient, constant. Why does it apply that f is linear? Of course, if f is linear, it's trivially derivative is constant. But if the norm of the derivative is constant, it doesn't mean that the derivative itself is constant, right? Not necessarily. So there is some argument which you can prove it. It's not difficult to prove, but it's not an obvious thing, because if you think about it, you can imagine that the norm of the derivative doesn't change, but the derivative itself changes, right? It can rotate. Turns out it's not possible. So, but once you sort of see this, you can see that constant tangent kernel is simply that the function becomes linear. So it's not something about optimization, the way it's sometimes written in the literature. It's actually the fact that the function becomes linear, or neural network becomes linear in its parameters. So that's point one. Point two is what is the nature of this transition to linearity? And there is a question. Yona, I can.
Sorry, I'm just going to wait and see if you answer it, actually, because I think this might be answering it.
Okay. So so if you write Taylor series plus Lagrange remainder term, you see that f of w is equal to f of 0 plus derivative plus the Hessian term, right? Plus high order terms, which well, actually, there are no high order terms because this is the remainder term. Now, what does it mean that the function transitions to linearity? It essentially means that this second order term is small compared to the gradient term, right? That's what I want to say. Now, there are some trivial ways in which it can happen. For example, you can simply rescale everything, right? And if you rescale everything, just multiply the function by some small number, everything becomes small, and the Hessian term is small. So your function essentially becomes 0. It's not really interesting. You can also rescale the input. You kind of just expand it, like imagine it's in a rubber sheet and you pull the rubber sheet, it becomes flatter, and it also transitions to linearity. Again, this is very boring. Now, the interesting part is when the Hessian gets rescaled, but the rest of it kind of stays the same. And this is actually what's happening with NTK. So I don't want to say this happens in neural network in general, because in neural networks, especially when they're wide, you have a lot of freedom to do different rescaling. So there are different rescaling modes. But I think NTK is particularly fascinating because what happens is that all the other terms stay the same order. Only the Hessian changes with widths. And let me, so this is kind of a theorem that you can prove, is that for a neural network which is wide enough and has a linear output layer, which is important, the Hessian is of the order of 1 over square root of m, the norm of the Hessian, in a ball of radius 1 around initialization. And in contrast, the value of the function itself is 1, and the norm of the gradient is 1 when you do the correct scaling. It's a So notice this is completely unrelated to initialization. This is really transition to linearity. The function starts looking more and more linear in this ball of x values.
Can I make
Now-
a comment, Misha? Very
Yes.
small comment.
Uh-huh.
So just to connect to the course of Dan and Show, if you try to track the dependence on depth of that thing, you could do this for not just a fixed depth, but for depth, that could potentially scale with the width. Then you'll get like square root of depth over width. So sort of, deeper networks take longer to become linear as a function of how wide they are. And, because that's some interesting direction from my point of view.
Right. So that's thanks, Boris. That's actually really interesting. So what is the trade-off between depth and width here? When does this transition happen as a function of both two parameters? So I'm just assuming depth to be fixed. But of course, increasing depth at the other direction. A lot of interesting stuff happens there. Okay, but let me clarify something. There is this common misinterpretation of this, and I just want to make clear why it doesn't quite work like this. So the common misinterpretation is that if you have small change of each parameters, that means that you stay close to initialization. And if you so it is true, it can be proven that along your optimization path, you stay, each of your parameters in each of the W's changes by a small amount, something like 1 over square root of m. And that means that you stay close. Well, the argument goes, I should put question mark here. Stay close to initialization. And if you stay close to initialization, you can kind of trivially get transition to linearity because the linear part dominates the quadratic part if you're close enough, right? Because we know close enough function looks like it's linear. This argument doesn't work. It cannot work. It doesn't, and it cannot, because it confuses two things, and that's why we have to be very careful with functional norms here. It confuses two things. So it does stay close to initialization, but it stays close to initialization in L infinity norm. So the infinity norm of the parameter vector changes by something like 1 over square root of m, little of 1. However, the second order term of the Taylor expansion does not depend on the infinity norm. It depends on the 2 norm of the vector. And the 2 norm changes significantly because h weight changes just a little bit, but together they went by the sum of their squares. So if you have m squares and each one 1 over square root of m, then the sum is of the order of 1. And you cannot say that the linear term dominates the Hessian term. So both of these implications are true, but they actually use different norms. So that I think is useful to keep in mind, because otherwise very easy to get confused and to see what's kind of easy and what should be obvious and what's not obvious. So small change of individual weights does not explain constant anti-K transition. Okay, so now let me just give you a very brief example to just show what actually happens. And I think it's a really interesting phenomenon, and it's a remarkable phenomenon. So what happens is that somehow the structure of the network sets it up so that Hessian and the gradient scale in different ways. So even though from just a purely norm point of view, this doesn't follow, but Hessian has additional structure. And that structure allows the scaling at different rates. So let me explain this very quickly with this example. So I have a neural network, and this is just one-dimensional neural network. The input is one-dimensional, and I am fixing the second layer. Okay, so it's a 2-layer, one hidden layer neural network with fixed second layer. You don't have to fix it, but it makes it much simpler. And so imagine that VI's here are plus or minus 1, and WI's are Gaussian. So then the output of this thing is O of 1, because it's a 1 over square root of m sum of random numbers. So it's of the order of 1. Now, what about the kernel? The kernel is actually, if you differentiate this, you see it's 1 over m times the sum, which is of the order of, each term here is of the order of 1. So the kernel is of the order of 1 as well. But what about the Hessian? And here is the key. if you compute the Hessian, you realize the Hessian is actually diagonal. So it's a diagonal matrix, and it has terms of the order 1 over square root of m on the diagonal. So that means that the norm of H is of the order of 1 over square root of m. So the norm of the gradient is 1, but the norm of the Hessian is 1 over square root of m, and that's where we see the scale. But you can also see that this is not true for general function. This is something very special, because why should Hessian be diagonal? This is not true in general. If it's not diagonal, even if each individual term of the Hessian is 1 over square root of m, the norm of that matrix would not be 1 over square root of m any longer. And diagonal is kind of special. You see, for a diagonal matrix, the norm of the diagonal matrix is just infinity norm of the diagonal, right? But this is not true, of course, in general. So again, there is some norm mismatch which happens because of the structure of the Hessian. So basically, Hessian is controlled by some infinity norm, while the kernel is controlled by 2 norms. And in high-dimensional spaces, 2 norms and infinity norms are very different. Infinity norm is a lot smaller. When you choose a random vector in a high-dimensional space, there is a square root of m factor between infinity norm and 2. So this is what is happening. And so there is some sort of essential thing going on with this high-dimensional spaces. It's not exactly just randomness. It's not exactly concentration, but it's somehow related to the fact that. So what you really need here, you need all weights to be kind of small. So for so which norm is it for H? For H, it's just a spectral norm, which is infinity norm for diagonal matrix. It's just infinity norm of the diagonal entries, right? If you think of the diagonal entries being a vector, it's just the largest diagonal entry. So you have a vector of on the diagonal of the Hessian with all entries of the square root of m, and you have a similar vector for the kernel. But for the kernel, you're computing 2 norm, and for the Hessian, you're computing infinity. That's mathematically what is causing the things to scale like that. So I think it's a very subtle effect, and something like that. I don't have time to talk about it, but yeah. So this is the norm mismatch. That's essentially what you have here. Now, for something like that happens for deeper networks as well, for fixed depths. If you fix the depth, you can show that, again, there is some norm mismatch, which I don't have time to discuss now. So yeah, you basically need to use some sort of Hölderlin inequality. You can see that the Hessian, again, is controlled by some infinity norm, and the kernel is controlled by 2 norm, but it gets a little more complicated. You need to take this activation function. Okay, so that's basically this transition to linearity. Now, I think a reasonable question to ask is transition to linearity a general property of large system, and the answer is no. And the example is actually really simple, and that in fact shows that just changing the parameter a little bit is not enough. And what do? Well, you take the same network as we had just now, and you just put a non-linearity on the output. Really simple. So put any phi here, which is nonlinear, essentially any. And what you observe that because the Hessian now has this extra term, which disappeared when phi was linear, the Hessian control fails, and you get something which actually changes. And so basically, you have these 2 terms. One is still of the order of 1 over square root of m, but there is an extra term to the Hessian, which is of the order of 4 of 1. So the Hessian itself is no longer scaling with the width. It's actually constant with the width of the network. I mean, I went over this very quickly, so but I hope the idea is clear. And you can verify this. Experimentally, you see that this is actually true. You take a neural network. If the last layer activation is linear, you see that with the width, it becomes more and more constant. So that's kind of measuring how constant it is. But if the last layer is nonlinear, like for example, swish or 10H on the last layer, on the output layer, you have essentially constant change of the hashing with the width. So it's not linear at all. Although each parameter still changes very little. So that is still true. Okay, I hope this is not too confusing, but I need to move on. So you can also think about bottleneck network, which is quite interesting in this case. You can see that the size of the bottleneck controls this, how it transitions to linearity. So now let me actually show how this together gives you convergence of neural networks. And really, there have been quite a lot of work. I'm not listing all of it here, but in some sense, you can think of it as kind of putting the ideas together to prove convergence in, I think, in a fairly simple way to show convergence of wide neural networks. So here is a proof, or quote unquote proof, very short. So imagine I have a neural network, and suppose it's wide. Then I can write this neural network as a composition of this wide neural network with a linear output layer and the last layer nonlinearity. So this is last. Okay. And now the trick is I use Hessian control to show that H is PL star, because I know that the Hessian scales differently from the gradient. So that's PL star. But well, there is an argument, of course. You can show that it's PL star. And then I noted that this is simply transformation of the last layer. So the last layer activation function just transforms the last layer. Actually, if you think about it, it changes something at every data point separately. So it's somehow diagonal transformation. And as long as the derivative of this transformation is, not too close to zero, you're basically okay. And you use a transformation control. So by putting the things together, that's actually the complete. So that's a very condensed idea for proving that linear network, that wide neural networks are PL. And of course, once you know that they're PL star, then you get convergence of SGD, you get all the wonderful properties that we discussed. So, and the question here is, well, so one thing which is unsatisfactory about this, I should point out, is that what about bottleneck network? Well, actually, we believe it's also PL star, but this proof fails because there is no transition to linearity on the first layer, on the first part of this H. And we don't know how to control hashing. Actually, hashing, we don't, not only we don't know how to control hashing, we know that hashing will change. So this argument doesn't work. Okay, now let me make one comment about what happens. Any questions about this? Questions, comments? Okay, I would like to make a comment about something which happens in practice. And in practice, you can say, well, it is not true that systems are always overparameterized, right? And even if you look at this huge, GPT-3 type of thing, okay, they have billions, actually hundreds of billions now, they have trillions of parameters, but they're being trained on data sets which are equally large or even larger. So it's far from clear that those things are overparameterized. And notice that overparameterization has something to do with the data, right? You cannot say that architecture itself is overparameterized. It's overparameterized with respect to the data that you're training. So if your training data are huge, then it's not overparameterized. But yet there is some sense in which it should be overparameterized. And let's think about this for a second. I'm training this huge architecture, and what I'm doing this mini batch training, right? So I'm presenting one, let's just say mini batch of size 1. I'm presenting it one example at a time. So for sure, it's over-parameterized on one example. What about 2 examples? Well, it's over-parameterized on 2 examples too. So until I get into the billions or even trillions of presentations, it's obviously over-parameterized. So you can kind of think that you start somewhere here, and you have some sort of walk on this W space of W's. And initially, you're clearly in this over-parameterized regime because you don't even know that this other data exists. The network hasn't seen it. So obviously, it's over-parameterized. And arguably, even after a few epochs, it's still over-parameterized because you're not training it well enough to be close to optimizing. So maybe the way to think about it is to think that you start with something which really looks over-parameterized. And as you get really low down, then you realize, actually, well, it's not over-parameterized. Maybe there is no exact solution. So I can kind of almost solve it. I can solve it on most of the points, but I cannot really exactly solve it on all of them. So you can imagine that it looks like PL, except close to the minimum when you see that it's really not PL. You have this bar. Actually, it's very easy to formulate this mathematically. You just basically say it's PL as long as the loss function is bigger than something. So if you want a mathematical formulation of something like that, and then it's easy to prove this theorem, which is essentially the same argument as before, is that if you have this almost PL, PL star epsilon, then you get almost convergence. By almost convergence, I mean that you converge exponentially up to level, which is epsilon. So we don't have a proof that specific systems satisfy this, and that's future, something to look at in the future. But I do believe that this is really happening. And this is an adequate representation for the phenomena that we get. So that's, so let me now summarize, and then I'm really happy to take any questions. So first, this is a summary of optimization. Landscapes of over-parameterized system are not convex even locally. That's the first observation. And as I have argued, PL star is the right notion for analysis of over-parameterized systems. And furthermore, PL star system really behave like linear systems in optimization in many respects, except that their condition numbers change. So wide neural networks in particular satisfy PL conditions and can be shown to converge. Now, for very large systems, I would like to conjecture that most of the optimization path still is on the over-parameterized regime when it's PL. PL star is nice, right? Because you don't have the star thing, you're just checking it at a point. So you just need to check that whenever loss is bigger than some small value, your gradient is bigger than the norm of the gradient squared is bigger than the loss. Okay, so that's that. And now I would like to, I had one more slide.
Could I ask a question?
Uh-huh.
So regarding your last point with this almost over parameterization, so I don't know what's the size of the mini batches for GPT-3, like you mentioned, but it sounds like there might be, I mean, my guess is that if it should like be quite sensitive to kind of the like in curriculum learning, the order of the examples you show the network. And I'm not, very familiar with the literature, but I think kind of the statement is that the order of the examples is not super important. And I wonder if, I mean, how could these two things like coexist or?
You see, there are two things here, right? One on optimization and one on generalization. So generalization may well be sensitive to the order of examples because that gives you some sort of inductive bias of which solution you choose on the solution manifold.
Right.
But optimization doesn't really care about the order of examples because as we have seen that you basically just keep going down along each of these gradients. So I think we need to carefully, and that's I think why I think about the interpolation, that it really allows you to separate those things. But ultimately we have to put them together. I'll say a few words about this. So let me finish. Maybe I'll have two more. This slide is the next one, which is so this one is kind of a summary, and the next one I would like to pose some questions or point out some open questions. But so this is in a sense a summary, is that we have this now, we have this space of parameters separated by the interpolation threshold in really two parts. And one part is this classical regime. And you usually have many non-global minima, you have local convexity all around each minima, SGD oscillates, and to choose a good model, you have to very carefully look for the bottom of that U. There is this new world, the modern world, and the landscape there are never convex, satisfy PL star condition, or at least we believe that they satisfy PL star condition. SGD converges exponentially, and the choice of model is easy. You just take a big model and you essentially, that's kind of all there is to it. At least to the first one. If you don't care about optimizing like last 1% performance to get state of that. Now, so we have these two worlds, and one thing which we don't understand, I think, is this connection. Because, and let me just go to the next slide. I have. Yeah, and somehow good generalization seems to come for free, which is not completely clear why. So what are the missing pieces now? First, and this is probably the most important one, why does optimization produce models that generalize? That seems to be very consistent. We understand that in some cases for some linear models and some kernel models, but really what we understand seems very specialized. What is true in general seems very robust and very general. Remarkably so. So it must be more, you have laws of gravity, right, which move planets around, and you have alignment of the planets. Once in a while, planets align in a line, right? So alignment of a planet is something special. It happens once in a while. Maybe you're lucky. Some things align, but there are these fundamental laws which control how planets move. So it seems that the generalization is a fundamental, there is some fundamental law associated with generalization. It really happens for broad class of models, and we don't really understand what that law is. Second, can neural network be thought of or replaced by kernel machines? Because at least for NTK, that is true, right? That we can show that wide neural networks are actually kernel machines, or can be approximated by kernel machines, and they seem to perform quite well in practice. Not quite well enough to sort of make a really convincing argument that they can always be replaced, but really quite well. So I think there are different narratives around this. Some people argue that they cannot be, and you could come up with examples when they cannot. On the counter argument to that we don't know how realistic those analyses are, right? Because if that's what happens in practice, so there are certain things which cannot be approximated by kernel machines, but are those problems that happen in practice? And it's unclear. I mean, my personal feeling is that actually a lot of things can be replaced by kernel machines. We just don't necessarily understand the right structure of the kernels. But in many cases we do, and it works quite well. The third one, I think, is another fundamental question. Why do inverse models requiring optimization like DNN work better than direct methods like K-nearest neighbors? Again, this is quite unclear, I think. There are some arguments about adaptivity, but I haven't seen anything like truly convincing about this. And finally, what is the role of depth, which seems a very fundamental question, which I haven't really discussed. I always assume that the depth is fixed. Okay, so I'll stop here, and I'm more than happy to take any questions. Varun?
When you talked about the optimization producing models that generalize, that you're meaning in terms of like using stochastic gradient descent and gradient descent and having that, like I think you referred to it in one of the last lectures, is like you're implicitly like minimizing some norm and you're in like a reproducing kernel Hilbert space of some sort, or some you're like imposing some smoothness implicitly. Is that what you're kind of like getting at? Like, where does this, like, how does SGD like imply the smoothness, for example?
Well, I'm actually thinking about something more empirical, right? So what do we observe empirically? We take pretty much any reasonable model. We initialize it at random in some way, run stochastic gradient descent. And we
I see, like
you know, and we get good results, right? They're not
Yeah.
always state of the art, but they're like consistently decent. So
Sure.
why does optimization? So if we say optimization, we expect that any large model will be PL star. So the fact that you could do optimization after like this, so initially it was surprising because we had this intuition about non-convexity, but after you think about overparameterization at PL, it becomes not surprising at all. It's post factum, of course, but whatever. But the fact that this model generalized very, very consistently, like we just don't know why. And you can say, yeah, maybe they maximize smoothness, but then what is that smoothness that they maximize, right?
Sure.
It has to be somehow
Sure.
mathematically right.
Sure. So like it seems like you've obviously thought about this at some level, but like the kind of work, what kind of stuff do you or like tools do you think are like useful, or like some things that are like should be explored in order to answer this question? The reason I ask is I'm, out of all of like the things that you said, I'm most interested in this one, obviously. So.
Well, to me, I think that's I mean, I've been sort of advocating kernel machines, and the reason I advocate them, well, there are several reasons, but one of them is that it actually gives us a very principled framework to think about smoothness, and the fact that you have this point evaluations being continuous functional seem to be exactly the kind of condition that we need to understand it mathematically. So if you believe that there is a mathematical description for these problems, which I do, and then I think the kernel machines and RKHS are the prime candidate for understanding this. Now, again, there are these different narratives of how much kernel machines, so you know, I should make it clear that this is not something that everybody agrees on.
Cool, thanks.
Any other questions? Yes, Sam?
Thanks, Misha. I was just wondering, so about this, the framework you were proposing or presenting, sorry, for the overparameterized linear systems of equations. I'm just wondering, so there's like, you know, starting 6 years ago or something, like a big focus in the non-convex optimization literature about like a special case of this framework, which is like matrix quadratic equations. So you can see a lot of these problems, I guess, inspired by matrix completion, but like matrix factorization type problems, phase retrieval, you know, various exotic measurement structures. And I think, so not all of these, but maybe some of them have been studied in this kind of overparameterized case as well. I guess I'm thinking of like the Colt paper by Ma et al. From a few years ago. And so I'm wondering, does the framework you presented have a connection to that? Are there any implications for that literature and what you're presenting here? I know the focus is more on highly nonlinear like neural network systems, but I'm just curious about any connections there. Thanks.
Yeah, so that's actually really, I think there are essential differences between this. So I think the kind of framework you're thinking is independent component analysis type of nonlinear methods, matrix completions. And so if you think about independent components analysis, for example, which is something I have thought. You also have a non-linear thing, and you also can solve it very nicely with actually sometimes even super linear, right? But it's quite different because you do actually have local minima there. It's just that every local minimum, local maxima, every local maximum is actually good because what you want to find some basis. And it turns out that every local maximum element corresponds to this basis element. So I think there is a fundamental difference between the things. However, you could also consider those in overparameter relationship, so there is some connection. But I don't know what that connection is. They seem to me that they're quite different ways of understanding non-convexity. Non-convexity more by those problems are somehow non-convex problem when you only have saddle points and every maximum is a good maximum. But these problems don't really typically have saddle points or have few, not many. Somehow the saddle points here are kind of irrelevant, and every maximum is actually global, or every minimum is a global minimum in this neural network. Seems very different, but I don't know. It would require thinking this carefully to think about the actual connection. Navid?
Hi, Professor. So
Mhm.
I had a little general question. So I was thinking, can we define a notion of overparameterization based on the underlying distribution instead of like the number of samples and the difference of number of samples and number of parameters, like some sort of statistical dimension of the distribution or some effective dimension of the distribution? And can we also prove that PL star condition satisfy for that loss function instead of the ERM loss function?
Yes, I think I haven't looked at this carefully. So the way I set it up here, it would not be possible for distribution because that would require infinitely many parameters for the neural net, right? To fit infinite. But there are some variational problems, and I think in variational calculus they have something which is analogous to the PL condition. So it's possible, but it probably would be quite a difference, I think. I get the honest answer is that I'm not sure, but something like that does exist, some infinite dimensional version of PL star.
I see. Thank you.
Jose Antonio?
Hello, Misha. Something I got stuck in my head that you mentioned about the normal to gradient when the normal gradient is constant and the function is linear. Is there any extra assumption on this proposition? Because I was thinking in the like a very classic counterexample function in real analysis, like the counter function. And the counter function, the derivative is 0 almost everywhere, and the function is nonlinear.
Yeah. So you cannot have almost everywhere. It literally has to be everywhere.
Oh, okay. So you need a smooth function.
You need some. You need. Do you need smoothness? Okay, I don't know what exact condition, but certainly, for example, if second derivative exists.
Okay.
With some Lipschitz conditions on the derivative is probably okay. Cool.
Okay, thank you.
Yeah. It's some pretty weak condition on the derivative.
Okay, thank you.
I mean, it's easy to check the proof and see what the condition is. Gati?
So could you go to your last slide? I'm not sure what you meant about this thing about what like in point 2 about what's like considered like practical settings or not practical settings. I mean, I know of kind of a few papers that showed like settings which are seem kind of natural where, you know, kernel machines or Gaussian processes like do much worse than neural networks. So I'm not sure what you meant there.
Yeah, so there are certainly examples. I don't know much worse, but there are certainly problems when it does seem that neural networks have a significant advantage. But it's not clear what the reason is. Because you know, think, okay, some neural network does great on ImageNet, try to do that with a kernel. But is it because the kernel not good? Is it because the data set is very big and we don't know how to train kernel machine very well? So it's not clear to me. I don't know what aspect of the combination of neural network, data, and computational resource makes it possible. And maybe once we make kernels better, more efficient, do the right architecture for kernel, maybe we can match that. I think it's not.
I mean, maybe, and also, I mean, I think it's kind of maybe two questions. I mean, one is right for you know, we know how to compute the NTK or the NNGP of several architectures, and so that's one kernel. But it could be, you know, that on a specific problem, there's some other kernel which is not related to the NTK or something that could somehow do better. So I guess you mean that in a broader sense, in the second sense.
It also, you see, so there is often an argument that the kernel in the kernel, so when you do neural network, right, if you think of NTK just being pointwise quantity, then it changes during optimization. So it is true that for many real neural network, it changes during the optimization. But you cannot say that just because it changes, that change is important, right? It can change and change may not be important, right?
Right.
So change and somehow we shouldn't identify change with good. Change is neutral. Yeah. Change is neither good nor bad. We don't know. It can be good, it can be bad. It's just change. So the question is, so there are some arguments saying that this change is important, but I haven't seen any sort of very convincing empirical or theoretical proof that this change is what makes it work. And in fact, even if the kernel changes, you can think of a data-dependent kernel, which is something that we actually did a long time ago, using some sort of Laplacian information to graph Laplacian information to control the kernel. Maybe you want to do a kernel which is data dependent. So you take your training data, you construct the kernel, and that is the kernel that you use. And for semi-supervised problems, for example, that's known to be often much better than the original kernel. Like if you somehow do this data dependent kernel, you can use unlabeled data. Help you inference. Maybe you can do the same with neural network, maybe neural network does something like that. So again, it's not completely clear. The argument has to be made, and maybe it's true, maybe it's not, but the argument needs to be made very clearly. And it's complicated. I hope it's sort of, it's not an answer as such, but it's, I think it's more an indication of uncertainty, and that I think many claims which have been made, there are very precise theoretical claims, but the connection of those to what happens in practice is very difficult to ascertain.
Great, thank you.
Siddharth?
Yeah, hi. I'm still thinking about the one layer neural network example that you had with the order of the norms for the NTK and the Hessian. So you said that, so you showed that the Hessian norm, the 2 norm, is 1 over square root of width, but it will appear in as a quadratic term, and there will also be a change in the weights from initialization to the point you are at, and over there it's in Euclidean norm, this change of the weights. So this could still be like something like order of m, order square root of m or something, and then overall this could still contribute, right?
Good point. Yeah. So what you can prove is that the Hessian, so the change of, so basically that thing allows you to show that in a ball of radius 1, you have PL condition. So your solution will be in a ball of radius 1 and L2 norm. So the change will actually be 1 over square root of M.
I see. So via the ball,
because
radius is fixed, so that's why you have it over there. But otherwise, there is no guarantee that you could basically just go outside of the ball, right? It could depend on the width.
Yeah. So in principle, you can go outside. Nothing prevents you. What happens is that because of the Pollack space theorem, optimization path will be contained in this ball. in the ball where function is still linear. That's a consequence of convergence, because you can establish PL condition. Now, here is something really interesting. This is for the square loss, and here where actually it makes a difference. Imagine I am using cross entropy loss, which is what people often use it for optimization, for trading in practice, for classification problems. Then you have to lose. So cross entropy loss, for for those of you who are familiar with it, it's something which actually only can be minimized at infinity. So if you run cross entropy loss to interpolation, you will definitely leave that ball. You will go off to infinity, and your kernel will certainly change. Your function is no longer linear, right? Because for every fixed width, your function is linear in, roughly speaking, ball of radius 1, or well, it actually depends on m, but it's kind of slowly. It's say log gamma. But with cross entropy loss, you would go to infinity, so your kernel will change. So that's one argument which, oh, okay, kernel maybe is important because when people train in practice, they actually do cross entropy. Now, here is a kind of counter to that, which I didn't have time to discuss, unfortunately. If you use square loss for classification, you actually get the same results in practice, often better for generalization. But for square law, this is a non-issue, at least for wide networks. So, so it's a subtle issue where actually your optimization happens. The claim is for square loss, if your network is wide enough, it will happen in this ball of radius. Hope that was not too confusing.
I see. No, thanks a lot.
Okay, it seems like maybe that's the end of the questions for now. So since this is Misha's last lecture, I just want to point out, I think this was a really excellent lecture series. Thank you very much, Misha. I think everybody basically agrees. So let's thank Misha again. As usual, these lectures will be posted on the YouTube channel, so you can view them as many times as you desire, although slightly less interactively. So our next lecture is in about 7 minutes. See you all hopefully then.
Thank you very much, Boris, and it was great to give this series of lectures. And yeah, thanks everyone for really good questions and excellent, just insightful questions and great discussion. I'll see everyone.
Okay, let's just give people another couple of seconds to come back. All right, so I suggest we slowly get started. So welcome everyone for the final lecture of all the lecture courses in this summer school. There's still the symposium afterwards. It's really exciting to have. I think Dan is going to give this last 5th lecture in the joint course with Show. So please take it away, Dan.
Thanks, Boris. And also, I want to say thanks, Boris. I think this was a really wonderful set of lectures and program, all of them and everything. And it was clearly a huge amount of work for you to organize this. So I want to thank the organizers, which is you. I guess since everyone's muted, I will just say thanks and do a brief applause. But thank you very much, and
thanks,
very much appreciated. Very happy to be here. So thanks for including us. So this is the last lecture, as Boris said, and as appropriate for the last lecture, we're going to be talking about the end of training and more. And given that in the first 2 lectures, I talked about the dynamics of particular networks, and then in the 3rd and 4th lecture, Show talked a lot about or discussed the initialization of models and the distribution that deep neural networks have. At this point, we're finally ready to put all the pieces together and understand what finite deep MLPs look like at the end of training. So here's an expression for the test prediction of a particular network at the end of training at finite width. And it's a very involved expression, but we've actually discussed most of what we need in order to understand this expression. And so let me take a few slides to go through piece by piece and explain what these terms are, although you're already familiar with a lot of them. And then we're going to spend a little bit more analyzing what this means and how to interpret it. So first, in this first line, we have a term that looks a lot like a kernel prediction, like kernel methods or kernel machine that has been discussed by Misha and also by me. However, compared to at least when I discussed it in the first case, we need to add one more piece, which is now we have neural indices on the NTK. Here again in our notation, H is the full stochastic NTK matrix, and it connects different neurons in addition to having indices for samples. The J, K indices are for neurons, the alpha indices are for training samples. And so for this expression, we need the complete inverse of the stochastic NTK. So which is defined by this expression here. So there's an inverse both on the neural indices and on the sample indices. And that would just come out of, so when I solved the linear dynamics, I was in a simplified setting of a kernel machine, and we didn't let the kernel have cross dependence between different output components. But in general, for a neural network, you do. So you get this slightly more general expression, but conceptually, it's the same as what I discussed in my previous lectures. So one way to just handle this is to define to decompose the NTK into a mean and a fluctuation piece, as I did here, and then expand this inverse. And again, also when we use these tilde indices, this is the inverse on the submatrix of the NTK on the training set only, and that's different than the inverse of the full NTK restricted to the training set. I discussed this before. I just want to make that clear. So expanding this inverse around the fluctuation, we get this expression. 2 comments. First of all, this is basically just expanding 1 over 1 plus something small, and taking the first 2 terms, it's the matrix version of that, nothing more, nothing less, or well, that's essentially what it is, I should say. And the reason we've truncated it after the first 2 terms at order cubic in this fluctuation is you can show that these higher order fluctuations are going to scale like 1 over n squared and can be neglected at the consistent order that we're working. And I won't show that on these slides, but it's actually not too hard to show. So that's the first piece that we'll need. So staring back at this expression here, we're going to need to expand it, plugging in that expansion. And so now we see, importantly, that we're going to have contributions from the instantiation to instantiation fluctuation of the NTK across different realizations of the parameters. So even though in the infinite width limit, the NTK is self-averages, it's constant, regardless of how you initialize the, on each draw of the parameters, you get the same NTK. At finite width, that's no longer the case. And these fluctuations actually do matter. They do figure into the final solution at the end of training. So we're going to need to take that into account in our solution, or we do take that into account in our solution, and we'll be able to discuss how this influences the predictions. The second thing to discuss, in some sense, the dominant part of the slide is the contribution from what Shou called the DD-NTKs. And that's these 4 terms here. And so while Shou mentioned obliquely that you do have these DD-NTKs and you need to take them into account, I don't think he went into detail about why there's 2 of them, and I'm not sure. I mean, we didn't, because some of the details are complicated, we didn't really focus on this. So I just want to explain briefly why at least there's so many terms. When you continue expanding out, say, when you expand the change in the network output to cubic order in the learning rate, and when you expand the NTK to quadratic order or the DNTK to linear order in the learning rate. So when you consider the expansions, that Taylor expansions, and look at the dynamics, when you go to study what we would call the cubic model in the language of my second lecture, there's essentially 2 different ways that you can construct a tensor that involves 6 derivatives. And so one involves the third derivative of the network output with these factors here, and the other involves 2 factors of the second derivative of the network output. And so both of these combinations show up in the dynamics. They show up in different ways in the different expressions. We don't have time to go into detail of how to solve the cubic model, but the conceptually, it's no different than the presentation that I gave in my second lecture. It's just a little bit more complicated. So if you just want the intuition for how nonlinear models works, the quadratic model is enough. If you care explicitly about how MLPs work, then you need to consider these additional terms and understand them completely. So having explained that, now let's just again go through all the terms. The first term is just the kernel prediction. So this is the infinite width network prediction, and it's a very small part of the slide compared to everything else, although it does make a importantly large contribution. So that's the first part. Then, as we discussed, the NTK fluctuates, and the fluctuations are also going to affect the test prediction. And so this is how they contribute. And note that the NTK, the kernel contribution, the linear contribution is linear in Y, the labels. And we see also that the fluctuation contributions are also linear in the labels. These 2 terms are the contribution from the cubic model. They're precisely what I discussed and showed in my second lecture, including these algorithm projectors ZA and ZB. Just here we're using, instead of calling this the meta kernel, we'll call it the DNTK, and there's additional neural index structure. But again, as I was saying, conceptually, it's the same as what I presented. There's just a little bit more details, and it's not too hard to work out given what I discussed last time. And these are the same tensors that I showed last time. I'll show them on the next slide, so you don't have to worry about remembering them. And importantly, this this term is quadratic in the residual or in the initial residual training error and quadratic in the labels. And then there's the two contributions from the DD-NTKs, the cubic model contributions. These are cubic in the residual training error, cubic in the labels. For each one, there's 2 different algorithm projectors. So we get 6 algorithm projectors in total. And there's corrections to this formula has some error. The error goes like 1 over n squared. And actually really, I'll say more on this later. But you know, from Misha's lectures, it's really L squared over n squared. So the error goes like the aspect ratio of the network, the depth to width ratio of the network squared. So if you had, say, a 10-layer network with 100 neurons in each of the hidden layers, then the infinite width solution would maybe give you an error of about 10%, whereas this solution would be an error of about 1%. And by error, I don't mean training accuracy. I mean, the question we're trying to answer here is, what does a real neural network do? And so these formulas are, you can either think about them as mathematical objects in their own right, or they're trying to model the actual neural network that you put on your computer. So if you were trying to use an infinite width network to model the actual neural network on your computer, then that would have some error. And the example that I gave, it would be about 10%, and using this formula would then reduce that error to about 1%. So depending on, this, depending on the test, that sort of error can be pretty significant. And so these corrections can be pretty important. So in addition to, that the solution takes the universal, or takes the form that I showed on the last slide, and there were 6 different tensors that we didn't define, or that need to be defined in terms of the quantities that we know and understand. We've called them algorithm projectors. And for gradient descent, I've listed them here. Unfortunately, it's a complicated expression, so you need to use various shorthands or to make it tractable. Again, shrink the font, fit on the slide, and then we've defined x2 and x3 as tensors that satisfy we've defined them implicitly as the tensors that satisfy this equation. And they're tensors that arise when you compute various generalizations of a geometric sum. So the point is, though, that well, first of all, so this is what comes out of the analysis of gradient descent. One of the points that I made in my second lecture was that at finite width, the details of the learning algorithm actually matter. You get different predictions on your training set depending on what learning algorithm you choose. And it's very simple to see that here. For instance, going from gradient descent to the ODE limit, studying gradient flow, involves setting eta to 0. So things simplify drastically. We only need 2 of the shorthands. We drop all the eta terms, and the inverting tensors simplify quite a bit. And I know that, in fact, there's been interest in understanding the difference in the literature between understanding the difference between gradient flow and gradient descent, and whether there's some sort of inductive bias of gradient descent that's positive for the solution that promotes better generalization. In principle, all of that is contained right here between the difference in these 2 tensors, in these 2 sets of different tensors. And furthermore, you can also solve this cubic model by a direct optimization. So you take the MSE loss, and then you just try to find inverting tensors and use perturbation theory, much like you would solve a standard linear regression problem. And you see things simplify even more to be quite drastically simple. So most of the algorithm tensors are 0, and you have, or algorithm projectors are 0, you have 2 non-zero contributions, and they're quite simple. And in fact, you can think of this as beginning to answer some of the missing pieces questions that Misha posed at the end of his last lecture, which was very, very nice for him to put up those questions, setting this up. We now have a means of at least addressing some of the differences between why does it matter if I do a direct optimization method versus if I train my network directly and optimize the parameters. We actually, at finite width, we get, first of all, at finite width, we see that we no longer have a linear model, and so there's additional contributions. in addition to the kernel contributions that we've evaluated. And furthermore, the way in which you optimize the learning algorithm itself does affect the solution. And so I just wanted to, even though the details of these tensors and the analysis of them is beyond the scope of the lecture, I think it's important to just point out how this dependence works. And the high level point though is that the form of the solution is the same. All the algorithm dependence is encoded in these tensors. You can think of the solution, you might call the solution or you might say that the solution takes a universal form, where as long as you change these tensors depending on the particular learning algorithm that you use. So to get a better handle on this solution, because it's quite involved, one of the things we should do perhaps is to consider the statistics of the ensemble. Note that we can think of this as telling us essentially how typical networks behave, or about a collection of fully trained networks. And in other words, we can think about training an ensemble and then computing their mean prediction, and that's what this expression gives. But also by looking at all of the statistics, we'll be able to figure out whether a typical network from the ensemble, so when you initialize a network and you train it, and you want to know how that network is going to behave, if members of the ensemble behave typically, then these formulas will be useful in explaining how they behave. And so that's for the next few slides, I'm gonna do that sort of analysis. So first, the first term is the kernel prediction coming from the neural tangent kernel. And now, since we're taking the mean, the dependence on the network at initialization, which has 0 mean, vanishes, and so we get this formula that's precisely the kernel machine that you get by direct optimization. So you have the labels and you apply the inverse of the kernel, and then you apply the test trained kernel, and you get this nice prediction. So everyone understands that quite well at this point. The 4 other kinds of terms give the 1/n corrections, give the leading 1/n corrections. And so there's four kinds of terms. They correspond to the different terms that I discussed in the stochastic solution before. So as I said, each network fits the training data with its own particular NTK. And so the resulting fully trained particular output will depend on which NTK you used actually to train your model, which NTK you got when you initialized your network. The difference between the mean NTK and the one you got is going to be expressed in the solution in this term, in these terms, this type of term. Then the other 3 kinds of terms encode the dependence of the NTK differentials. And as we discussed in previous lectures, these cause the NTK to evolve. And you can interpret that as giving you a data dependent kernel. So there's non-trivial representation learning that occurs at finite width, and it's encoded in these terms. And in general, it's really important to understand the trade-offs between these types of terms. They're very different, and in some sense you can think of one as being bad and one as being good. And in a bit we'll return to comments on this interplay a bit between these random fluctuations and directed representation learning in the finite width network. Before we do so, let's just look at these particular terms in a little more detail. So starting with the NTK fluctuation term, we take that expression, we compute the expectation, and if you look at that particular term, we can write it in the way that I've done at the top of the slide. These A and B tensors arise from decomposing the NTK variance like so, according to this expression here. I'm not sure, I don't remember if showed this exact equation, but I think he did at least discuss that there's a decomposition into certain tensors, and he at one point flashed the recursions for these A and Bs. So the point is, when you want to analyze the statistics of the distribution at initialization, one of the things you do is look at the variance of the NTK, and in doing so, we wrote down and flashed recursions for these tensors, and then also I don't think did it in his actual presentation, but told you that the solutions scale like L over N, or these guys scale like, or the appropriate, I should say, the appropriate normalized quantities scale like L over N. So the point I'm making here is just that these are now known quantities. We know the recursions that these describe, and we can solve them and understand them. So in principle, you can do that for your data set of interest and plug it in to this formula, and then you understand that exactly that contribution to the solution from without having to optimize your network. And as I said before, importantly, this is still linear in the labels. So this is still the this still can be interpreted as a kernel learning. It's just that the kernel has this fluctuation term that you have to take into account that modifies things. Okay. Now there's the three other kinds of terms coming from the NTK differentials. Here we're looking at the DNTK, pre-activation, cross-correlation. I think, I'm not sure if we emphasized this before, but the DNTK by itself has an expectation of 0. So the first non-trivial statistic is its correlation with the network output. So again, in doing the analysis, it's convenient to decompose it into different tensors. So we make this decomposition here, we find the recursions and solve the recursions. And if you look at the expression for the output and take the expectation, you get this formula here. The one thing to notice is that the fluctuation didn't depend on any algorithm projectors. So the fluctuation term doesn't care about the learning algorithm, whereas the contribution from this term does care about the learning algorithm. So in principle, you can tune it by changing your learning algorithm. And the second thing to notice here is that the contribution is linear in the labels. Now, even though this is a quadratic, even though this came from a quadratic model, because we took an expectation, because the DNTK needs to pair with a network output in order to have non-zero statistics, the surviving terms are still linear or only linear, for the mean at least, are linear in the labels. Even though for particular networks, it would be quadratic. And then finally, we have the contributions from the two DDNTK means. They have a non-zero mean on their own, and there's additional decompositions that you're motivated to make when you solve the recursions. And this expression looks a little more involved, but importantly, looking at the cubic contributions in the labels, we see that the jth component of the observed output influences the ith component of the mean prediction for I not equal to j. You can think of this as well. What this means is that if you have a component in your solution that normally for kernel methods, the one component of a label can only affect the mean prediction for that particular component. But in this case, for these neural networks and for finite width networks, I should say, that's no longer the case. The other component to the output of the true labels can affect can affect different components to the output. You can think of this as in the intermediate layers where something similar happens, as promoting representations that have correlated features. But in the output layer, this is important, for instance, for ensuring something like a distillation would work. So if you have soft labels, right? If you have a label, for instance, if you're trying to solve MNIST and you have different digits and you have a 2, there's important information encoded in a type of soft label where the 2 might be more 7-like, or it might be more 3-like. And in order for that information to be learned, you would need this sort of output component correlation to take place, and that only begins to happen in this finite width for finite width networks. Well, we're going to call this property a wiring property. The reasoning descends from at least in our analysis how we discussed Bayesian inference and Bayesian learning, and sort of descends from a notion of Hebbian wire together, fire together thing. I'm not going to go into the details of that, I'm sure, although some of you are familiar, but just as a shorthand, the correlation of these output components like this, we're going I might refer to as a wiring at some point, because what we're seeing in any of these layers is that the output features develop a correlate, or the representations begin to correlate with each other rather than being independent. And so you can think of them as sort of wiring together. But language aside, I think the concept hopefully is at least clear about what feature of the solution this is capturing and why it might be important. There's this very similar thing that happens for the second NTK mean. It involves the other algorithm projectors. So in principle, you could pick a learning algorithm that tune these guys differently. There's another tensor decomposition, another set of recursions you have to solve. It's kind of a slog, but if you care about the result, you have to do it. If you just care about it conceptually, then maybe you can just study a quadratic model rather than a cubic model. And there's a similar wiring like property that happens from the cubic contributions of the dependence on the output. Of course, so that's for the mean. Those are the different terms of the mean, and those are, you know, the details of sort of how they're contributing. We can also study other statistics of the fully trained distribution. For instance, we can study the 2-point function, or sorry, the covariance, which is standard formula here. We're not going to be able to print this quantity in full, unfortunately. The full expression doesn't really play nice with the constraints of any slides. But if you want, you can extract insights by considering specific contributions. So one of the things to point out is we can see the imprint of this output or wiring effect by looking at the following contribution to the covariance. So this comes from a cross correlation between a factor of the solution has, or sorry, let me go back, where we have to correlate two fully trained outputs. And so one piece comes from the initial output from the I2 component, and then the other piece comes from the I1 beta 1 component in the correlation. And I mean, it's just the expression that I wrote here. Taking the expectations, you get some factorization, and so you see there's two expectations to evaluate. Evaluating them, you get this expression here, and the point is that we see again that there's some non-trivial wiring when we have yi1 not equal to 0 and yi2 not equal to 0. The interpretation here is actually a little different than for the one in the mean. So I mean, so first of all, what this means is that this sort of correlation between components occurs differently for each network in the ensemble. In other words, the fluctuations from instantiation to instantiation of the parameters at initialization break the permutation symmetry among the output neurons. And so the fact that this sort of thing is exhibited in the solution suggests that the network is able to use these different fluctuations between output components to its advantage in order to correlate such components over the course of learning. And this sort of thing doesn't show up in the mean statistics because you have to preserve that permutation symmetry. But I guess the high level takeaway is that these initial fluctuations can be put to the advantage for building representations, and it does seem to happen in this piece involving the DNTK. And more broadly, unlike the kernel prediction at infinite width, at finite width, the fully trained distribution now has non-Gaussian statistics. The argument for this is kind of straightforward. The formula that I showed at the beginning of the talk expresses the output at the end of training in terms of all these quantities at initialization, the network output and the NTK and the various differentials. And from Show's lecture, we know that the statistics of all these guys is nearly Gaussian. It's not a Gaussian distribution, and we worked out in detail what the statistics are. And so putting that together, we would find non-Gaussian statistics for the fully trained distribution. Unfortunately, explicit expressions of higher point correlators are challenging to display in any media format, though all the information that you need to do so is fully contained in the solutions or the explicit expressions for both of these, for the initialization distribution and the particular output at the end of training. The information carried in these correlators probably contains useful information, and it would be interesting to evaluate them further. But although we haven't really done any analysis with that in particular. So yeah, maybe that's a good place to pause briefly for questions before moving on to discuss how generalization works for ed finite width, or before discussing generalization in this context. Let me see what time it is. Okay. Oh, I see. So Sadak, I think your hand was always up this whole time, so I'm not going to count that as a question. Let me go with James.
Hey, Dan. First of
Hey.
all, thanks for going through all of this. It's really interesting. My question kind of about the representation of all these formula. Have you thought about looking at like Penrose tensor diagrams or some sort of more graphical way of representing these equations so that like it's more intuitively visual what things are connected and what's going on instead of like this whole giant jumble of indices? Or do you think that wouldn't help?
I haven't thought about that. That could be an interesting thing to do. I like indices, so maybe that's my inductive bias, if you will, and your mileage with that may vary. I think for me, what was helpful was studying some of the simpler models without. I mean, that the MLP phenomenology is kind of gross, but you have to deal with it if you care about MLPs. But if you want to understand conceptually what's going on, for instance, about representation learning, then studying the simpler models might be useful. And that's why I talked about the quadratic model originally. Let me take one more and then I'll move on and I'll come back to get it later. And Gadi is to the left of Varun. So sorry, Varun. Go ahead, Gadi.
Thanks. So like a very non-technical question regarding what you're saying about dependence on the algorithm. So yeah, I mean, there's like many algorithms. So how could you, are you like saying you can code any possible algorithm there? I mean,
I don't know what class. I don't know what class of algorithm. I gave three different. Well, I gave in some sense 3 algorithms, and one of them had a 1-parameter family of different algorithms. Right, the different learning rate is each one is a different algorithm, and you could imagine also changing the learning rate. So I think you could probably encode. My guess is that you can probably encode the sorts of algorithms that we use to optimize networks in addition to this direct optimization formula, but I haven't worked out the details yet.
Right, so okay, so you meant like one of those 3, but basically you're saying it could be extended to like other ones used in practice.
Yeah, let's call it a conjecture.
Okay, thanks.
I'm pretty happy though with gradient descent, gradient flow, and direct optimization. And I mean, it's simple. For instance, changing your learning rate, having a scheduler probably is simple. Like the form will be the same. The projectors might be pretty gross. And I think also SGD, it has to be the same. So
and Adam or something.
Yeah, I hopefully will never analyze Adam in my life. But yeah, the way in which I think for some of these algorithms, okay, so less snarky comment for some of these algorithms, right? You have to be careful about whether something really should be part of the algorithm or part of the definition of an object. So for instance, we defined the lambda tensor, which we incorporated in the definition of the NTK, but at infinite width, that does have an effect on things because it controls the kernel. Those are in some sense layer dependent learning rates, but I think it's because of this presentation here, it's much more natural to think about it as the definition of the kernel and not really part of the learning algorithm. But I can imagine someone arguing with me about that, and I don't want to argue about that. I think the technical details should be clear And when I say it, I'm referring it to the way that we define these things. So if atom involves effectively changing the definition of the kernel at various stages, you have to incorporate that, and that might make different changes. I think for SGD, I would guess also if you include momentum, and certainly for having a scheduler, the form that I gave is sufficient, and all the details will go into the projectors. Great. So generalization. So I'm not going to belabor this because there's been lots of lectures and people have been talking about generalization, and even Sho talked a bit about generalization. So, generalization error is how well you're doing. It's important. And for over-parameterized networks, we don't have test error. Sorry, we don't have training error. We fully learn the training examples. So really, this is just a question of what is the test error. So going forward, let's see how this works for the MSE of test loss averaged over an ensemble of fully trained networks. So we're going to take the statistics that we worked out in the first half of this lecture across all those slides, and then we're going to try to use that to evaluate the MSE, to evaluate the test loss in the ensemble. The idea, well, so first of all, this can be extended for other types of loss by doing a Taylor expansion. So for simplicity, I'm going to focus on MSE. No one seems to have a problem with that in the theory school, so I won't belabor that further. Second, the reason to average is to answer the question. So we have this ensemble of networks, meaning every time you load up your computer and you instantiate your network and you want to train it, you're sampling from this ensemble. And the question we want to answer is, how good is that ensemble? Is a typical network going to behave well, or is it going to depend on the random seed, on the luck of the draw? And not only that, so that's about fluctuations, how well is it going to, on average, across the whole ensemble, give me good predictions? And so those two aspects let us, thinking about those two aspects and doing a standard manipulation, we can rewrite this in a form where we have a bias contribution, which is this first term, and a variance contribution with this, which is the second term. And Sho gave the algebra for how to do this decomposition. I'm just reviewing this, and Sho also explained this. So this is in some sense a review, but this is a generalized bias and variance trade-off. In other words, different settings of the hyperparameters, which define our ensemble, which define our distribution at initialization, and therefore define the distribution of fully trained networks, will decrease, in general, would decrease one term, say the bias, at the cost of increasing the other, the variance, or vice versa. And the reason we call it generalized is that in the standard bias and variance trade-off, the expectation is over different realizations of the training set A. Well, sorry, there's no A on the slide, but the over different realizations of the training set, I might label it A at some point. The bias and variance trade-off here, though, is over different realizations of the model, of the initialized model parameters. And importantly, the point is that we're trying to pick between different ensembles. We're trying to ask the question, how do we pick our ensemble given everything else fixed, such that we get the best generalization performance, not how do we pick our parameters of our model in order to fit various different training sets the best. So it's slightly different than I think how this is normally treated, but this is the central question that we should be asking ourselves for this type of analysis. And last time, Sho zoomed way in order to discuss how the initialization hyperparameters, how choosing criticality is important for weighing this bias and variance trade-off and giving us a good ensemble that is going to not be too biased, make good predictions, and also not fluctuate too much from instantiation to instantiation. So now we're going to zoom out a little bit, and instead of considering one training input and one test input, we're going to zoom out so that our field of view has two training inputs and one test input. And the question that we want to ask is, how are our networks interpolating and extrapolating? The setup is that we're going to consider our two training inputs. We're going to label them plus and minus. So we can think of this as there's some midpoint x0, and then I'm going to add and subtract some small perturbation so that I separate the two training points. And we want to ask, what prediction is our network making when I consider a a linear combination, a weighted linear combination of these two inputs. And there's just a simple manipulation to rewrite this using this expression in terms of the perturbation. And I'm going to label this as 2s minus 1. And s is a parameter, so we get a 1 parameter family of test inputs that we can interrogate. And depending on, let me pause that thought for a second. So the test input sits on a line between x plus and x minus, and we're going to move where it sits on the line and ask what sort of predictions we're getting. When our parameter is inside the unit interval, this is a question about interpolation. When s is outside the unit interval, it's a question about extrapolation. If I should have made figures, but hopefully this is clear what this means. And then for general s, we're just going to call it starpolation, because in general, it doesn't really matter whether you're inside the interval or outside the interval. The analysis is the same, and sort of the goodness is mostly going to be about how close you are to these points, not whether it's strictly doing interpolation or extrapolation. So that's the setup, and we're going to start by studying at infinite width, where the majority of the feature of how the network behaving occurs, and we're also going to focus on smooth activations. In principle, I think you can do this for non-smooth activations like ReLU. You just the way the analysis would go is a little different. This is not a fundamental. I think this is not like before when Sho was explaining the way that ReLU can't be analyzed by the Taylor expansion of for the training. The training dynamics can't be analyzed by a Taylor expansion. This is different. It's just that you have to do a different analysis depending on what activations you consider. So we'll think about smooth activations like tang, or maybe a smooth activation like a GELU or swish for you should have in mind here. And so this is the NTK prediction. This is the kernel prediction, just the linear model prediction. And so to answer this question of starpolation, there's two things that we need to do. First, we need to invert the 2x2 submatrix of the NTK on the training set only. Remember, this means the inverse when the indices are raised like this. And second, we need to evaluate this object, which is the elements of the NTK between our test and training set. And in this case, the test is our point 2s minus 1, and the points in the training set are these plus and minus. So we need to evaluate this component of the NTK. The inverse of the submatrix we can get just by writing in the components and taking the inverse, and we'll use this expression soon. So that's straightforward. It's a little less straightforward to evaluate this test train NTK. So to do so, you have to use the fact that these two training points are close together. There's some nice change of basis that you have to do in this analysis. I don't have time to go into full detail, but it's conceptually simple. And so you can write down this component in terms of the NTK components of the plus and minus points of the test set, of the training set points with this parametric dependence on the parameter s, minus this new object, delta delta theta 0, where this difference is, let me explain it in a second. And then there's some error that goes like how the training points are separated. So we're zoomed in on two training points that are kind of nearby each other. And this is kind of okay, because all of the dependence, when these sorts of components end up decaying and becoming small, or the precise thing is that the influence of points that are far away end up becoming small. So it's very natural to consider points that are close together and a test point that's nearby. So anyway, there's some error that goes like this lowercase delta cubed. Anyway, so this term, now let me explain this term. This is the difference between two objects. This theta 0, 0 is, if I go back, so there's the midpoint between my two training set points. The midpoint is not in my training set, but it's a particular input that could exist. You could make it averaging your two test points and put it through your network. And if you did, this would be the NTK, the diagonal part of the NTK for that input. On the other hand, the quantity in the square brackets with this 1/4, so that's like the average of all the components in the 2x2 NTK matrix of the two training points. You can also think about it kind of as, so this was, we average the input points first, and then we put them through the network and look at their NTK. This is kind of like we take the 2 points, we put them through the network, and then we average their kernels. And there's a way in which you can write the NTK as a sum. The NTK is this product of these two derivatives. And so you could write it as the product of the average of the network output of these 2 points of the derivative of that. But the expression maybe is hard to, I mean, this is the precise expression for what it is. I'm just trying to give it an intuition. So there's sort of averaging before the network and averaging after the network. And there's a difference potentially, which scales like delta squared. That's why I label it with 2 deltas, and that shows up in this expression. And I apologize for not having time to do this analysis, but hopefully at least intuitively this type of thing makes sense. So as an illustration, we will consider 2 points with the same norm. So you can imagine we took our training set and we pre-processed it. So all the points, all the inputs have the same norm. This really doesn't matter. It's just to simplify the algebra for the purpose of this discussion and this slide. Some terms that aren't interesting go away. So the first thing that we note is that nonlinear networks can nonlinear star plate. So here in this first square brackets, this is at initialization. These are all at initialization. So this is the network output on our test point. This is the linear combination of our network output on our 2 training points. And so if the network is at initialization, computing a nonlinear function of its input, then this is going to be non-zero. So for DLN, this is precisely 0. For non-DLN, this is a nonlinear term. This is just the linear interpolation of the labels. And then here we see another nonlinear piece. It involves the product of S and 1 minus S. So it cares both about the product of both of the training points, and it involves this object here that I discussed in the last slide, divided by theta 0, 0, which is so it's normalized by the NTK of the midpoint input. So perhaps to get a little more, to understand this further, we can use this to understand for the setup, the prediction of how the prediction of ensemble has a bias in the sense of generalization error, the biased part of the generalization error. So to do this, we took an expectation of the object of the expression on the last slide, and then we subtracted the true label for our test input here, which gives the bias, and we get this expression here that has 2 terms. So it decomposes into a part measuring the nonlinearity of the labels. So the test input is taken to lie on a line connecting the 2 training inputs. And so if the labels of those inputs also lie on a line, then this is going to vanish. But if the data has nonlinearity, so for linear input to the network, inputting a line, if it curves it at all, then or if the true data curves it, then this is going to be non-zero. And that's compared with the network curvature around the midpoint of the 2 true labels. So this is kind of really cool, I think. What this is telling us is that so first of all, the curvature of the network encodes the inductive bias of the function that's computed by the network. So if we have 2 points and we put them in and we want to ask how is our network interpolating or extrapolating, then whether it's linear or not, or the way it's doing that is encoded by this term here, which is measuring the curvature of that prediction. So first, I should add for deep linear networks, this delta theta is 0. That's an easy computation to do. So that means that if your data has output, if your labels have nonlinearity, the deep linear network cannot capture that. So that's a horrible inductive bias if your data has that property. The deep linear networks are very rigid and fixed and have an inflexible bias. On the other hand, if you know something about your particular data set, then you might be able to design this part of the kernel, right? This is just a component of the NTK. which we can modify it by changing the activation, by changing some of the hyperparameters. And so if you know something about the way your function is curving, then you might be able to use this type of analysis in order to design a network that's tailored to a particular data set. And the point though is that the curvature in the labels, the network is trying to match the curvature of the two labels, and if it does, then the bias can be made to be smaller. And the harder it is for it to do that, the larger the bias is. And before moving on, let me comment that at finite width, so the computation would be quite involved. But one important point is that we would also have a different linear piece, but most importantly, we would have cubic starpolation. So there would be a piece that's cubic in the labels here, and so you know, right now, even though there's curvature in terms of how there's curvature of the function seen as a function of the input, but if we're just thinking about how is the function interpolating in the label space, it's just only able to do linear interpolations at infinite width, and at finite width, we're able to do more complicated cubic things, more like perhaps like a spline or something. So there's more flexibility here coming at finite width in order to more easily match to reduce the bias in the generalization error. And you can think about this. This is sort of a direct way of analyzing it, but you can think about this as perhaps incorporating these together as giving you sort of a data-dependent curvature that, depending on what the data tells you to do, the function is curving in different ways, and that's sort of the representation learning interpretation of what's going on. Finally, we can just consider generalization more generally, if you will, at finite width. So going through that big expression, plugging in, looking at the mean, plugging in for the different algorithm projectors, and considering all the different terms, all the terms end up being proportional to one of these 8-dimensionalist ratios. And in some sense, and these ratios in fact showed up when in Shou's discussion, when he was describing bidimensional analysis, that these are the right combinations of terms in order to consider to understand the depth dependence. Here we see that dimensional analysis just tells us that if we're going to add things together, they all have to have the same dimensions. And so for it's essentially the same reason, these quantities all show up together. And as Shou explained, all these quantities scale like L over N at leading order in finite width. So overall, we should find for the finite width corrections that they're going to scale like L over N. So the question of how is depth affecting what role is depth playing in neural networks? This is a very concrete answer to that, which is that where depth is causing these finite width effects to become more important. The scaling is L over N, and the particular details involves you solve these recursions, which is not too hard to do, and then that tells you precisely how at finite width the prediction is changing as depth is increasing. And so we get this putting everything together, we see how this works here. So given that depth seems to be important, and given that the finite width corrections, now that we've discussed some of the finite width corrections, I want to return to something that I said a bit earlier when discussing the different parts of the mean, about how, on the one hand, representation learning seems to be something positive. We can think about it as letting the kernel have a data dependence or develop a data dependence. We can also think about it maybe at a very low level in terms of the analysis of starpolation, where we're just allowing some more flexibility in our functions for how we can fit things, how we can fit and reduce the generalization error. On the other hand, the effect of fluctuations can be pretty negative. Shou talked about this a bit, but the basic idea is that as the fluctuations between different realizations of our parameters increase, it's going to be harder, even if you tune to criticality, to reduce the negative exponential behavior of the signal propagation in your network, so that signals going forward propagate well and that gradients propagate well. That's a statement about the mean of the ensemble, but the fluctuations tell you how any particular network you have is going to behave. And as the effect of fluctuations, as you increase the size of the fluctuations, that means that any network that you train is likely to be very different than the mean of the ensemble. So any particular network is not going to behave typically, or it's not going to typically behave like we expect from the analysis of the mean. And in general, that means that any particular network is not going to have a nice signal propagation. So it's going to get harder and harder to train networks as there's more and more fluctuations. So the first part says that depth is following the logic through. The first part says that depth is good. The second part says that depth is bad. And so that suggests that perhaps there's some optimal aspect ratio of the network that mediates between these types of good and bad effects. One way, perhaps the most direct way to analyze this is to, just doing a quick time check. So perhaps the most direct way to analyze this is by looking at the generalization error, but that would require studying L squared over N squared effects. The reason being that if you imagine plugging into our big formula, plugging it into the generalization error, and then trying to optimize for the aspect ratio, we only have a linear piece, and so we'll only be able to conclude, for instance, that turning on, that deforming away from the infinite width network is a positive thing to do. So instead, we can try and pick a simpler quantity, perhaps one that we defined at initialization, where we can try and compute higher order effects. And Boris, I think, so is it correct? I have 5 minutes left, is that right?
Yeah, definitely. I mean, you can take another couple of minutes if you need at the end.
Plus the Q&A. Yeah, I might go 10 or 15 minutes over if that's okay, or
yeah, I mean, look, that should be fine. We have the symposium after, but I put like half hour between, so it's all good.
Great. So I'm going to skip this part because it's just an aside about, or it's just I think probably everyone here is pretty familiar with the concepts of entropy and mutual information. If not, I'll post the slides after and you can look at them. But the tool that we're going to use to answer this question is borrowed from information theory. So entropy is an important measure of expected surprisal. And depending on whether the independent variables are independent or dependent, they have different properties. And if the variables are dependent, then the entropy of a joint distribution is subadditive compared to the entropy of the marginals. And that's important. What it means is that for physically, for dependent variables, observing y doesn't inform you as much as it would have if we didn't already know x. This motivates the introduction of a different quantity called the mutual information, which is this combination of entropies here. I assume this is all familiar to everybody. That's why I'm going quickly. And it's an average measure of how much information an observation about x conveys about an observation about y, and vice versa. If this reminds you of subadditivity, then also note that rearranging the subadditivity relationship tells you that mutual information is positive. And the point of this exercise that I rushed through is that this is telling us something about non-trivial non-Gaussian correlations, about the interactions and distribution. So it's a good diagnostic of statistical dependence. So returning to our question, we want to somehow capture this notion of wiring, or this notion of correlation between the pre-activations in the deep layers of or in the neurons of a deep layer of our network, which is a consequence of the positive consequence of the NTK differentials. And the mutual information perhaps is an accessible measure of this, of the potential for this sort of correlation and lets us evaluate this as part of the inductive bias of the prior distribution. And so let's see how this can be made to work. The particular thing that I care about is that I want to compute the mutual information for a single input between two sets of neurons, let's say in the final layer. So I have set curly M1 and curly M2, and lowercase m1 and lowercase m2 are the number of neurons in each set. This is just notation for computing that mutual information. And what we want to do is we can perhaps estimate this optimal aspect ratio by maximizing the mutual information over the different sets and also over the different aspect ratios. So as an aside, this is actually related to an unsupervised learning objective. That's where the idea to do this comes from. The InfoMax principle is an unsupervised learning objective that recommends maximizing the mutual information between an input and a representation. And a related notion then says we should maximize the mutual information between two different representations in order to, and both of these are about learning representations for data that's not labeled. So it's an unsupervised criterion. This latter notion here can be shown to lower bound this InfoMax objective, which is a very natural heuristic for what a representation should do. You have an input and you have a representation. You want observation one to convey observation information about the other. So this is from the literature. This is a standard unsupervised learning criterion, and this is basically what we're doing here. We have two different representations by the different neurons in the last layer, and for the same input X, and we want to maximize that. And importantly, here there's no learning, like our discussion of the generalization error. We're just using this unsupervised criterion to pick an ensemble that performs best according to this objective, with the idea that then these sorts of objectives lead to better training once you fine tune after doing the unsupervised learning. So to see how this works, to how to compute it, let's go to the next slide. Uh-oh, I hate it when that happens. Mostly that I run out of time and I don't have the ability to explain the details of the calculations. There's a procedure you can go through that's based on the variational principle. And doing so, you can compute the entropy at up to order 1 over n cubed. There's some interesting points here about using the principle of maximum entropy, about why there had to be a negative sign. Mostly that I guess people here are probably familiar that the Gaussian distribution maximizes the entropy of a set of random variables of fixed mean and covariance. So for a nearly Gaussian distribution with the same mean, which is 0, and the same covariance, this 2-point function, 2-point correlator G, we must have lower entropy. So there's a minus sign here. And then also the reason we get a second order result is that for distribution, a distribution that's nearly Gaussian could have either fat tails or thin tails, and the leading correction to the entropy must be proportional to minus the square of the 4-point connected correlator, which is this V, this vertex, in order to guarantee that the entropy decreases. And so for sort of cute reasons like this, we don't have to compute this answer up to this order is going to depend only on G, the 2-point correlator, and V, the connected 4-point correlator. So we get, in some sense, we're able to, if we work a little hard, we were able to get some higher order information for free. You can then define take this 4-point vertex ratio of the 4-point vertex and the which is essentially the kernel, and extract the aspect ratio. We know from Show's talk this goes like L over N, and here nu is an activation function dependent constant, and we get an expression for the mutual information that's valid up to order R to the third, R to the third, where R is the aspect ratio. So these signs are different. We see that as the mutual information, as we deform away from the infinite width limit, begins to increase, and then eventually it's going to turn over and begin to decrease. And there's some maximum here. And so you can just go through this maximization problem, and you get an expression that depends on the number of classes that you're trying to learn, and also depends on the number of components for your output, and also depends on the details of the activation function. So for say 10 output components, we find that tangent, hyperbolic tangent is 0.12 and ReLU is 0.016. They nearly differ in terms of where they want to be according to how deep a networks they want to have according to this criteria by nearly an order of magnitude. And so the one thing to advertise from our work is that you can also do this analysis for residual connections to try and understand in this sort of language how residual connections can help you train deeper networks. And actually you find that this effective scale at which networks are effectively deep, at which they behave well, that the depth at which they behave well can be pushed to arbitrary depths by adding residual connections and by doing a very similar kind of analysis. So that answers the question about aspect ratio that we've been alluding to the whole time. And let me see, so I'm 5 minutes over. Let me take 5 additional minutes just to make some points. I'm gonna skip through some of these slides that I'll post them online and you can read them after. The point is going to try to address from our perspective, what it is about how to think about over-parameterized models. And given the fact that according to the traditional notion of machine learning and classical statistics, that models with tons of parameters are supposed to overfit. And I know Misha talked about this a bit in his lecture. Here we just have we're able to, using our effective theory approach, we have a pretty nice way, I think, of thinking about this. So namely, the question really depends what you mean by model complexity. So there's 2 different perspectives that you can have. One is in terms of what I'll call the microscopic perspective, in terms of the weights and biases, the low-level components of the network. And in that case, and in the traditional case of statistical modeling, you want to identify the model complexity with the model parameters. But on the other hand, in these lectures, we integrated out the model parameters and developed a macroscopic, what I'll call macroscopic perspective, where our effective description of these networks has a notion of model complexity that's completely reversed. So let me show and say in detail what I mean. So for the Gaussian distribution at infinite width, here I've now written it where I've conditioned on the true labels on the kernel and on the NTK. And the reason for doing that is that the mean and the variance, we wrote the mean, I don't think we wrote the variance, but if you go through the analysis, the statistics of the Gaussian are defined completely in terms of these objects here, in terms of the labels and in terms of the 2 different types of kernels. And so this is a sparse description in that the numbers that you need to define the distribution depends on a few objects in a simple way. And we'll count that in 1 second. The point I just want to make is that at finite width, we then also have a nearly Gaussian description. We have a few more letters here in order to encode the finite width non-trivial correlation functions that you get at finite width. And this description is nearly sparse. It depends on a handful of tensors, 2 handfuls of tensors, I guess, depending on how big your hand's on. So you get a slightly more complicated description, but it's still tractable. And if you try to count up these components, this comes from the labels, this comes from one of the kernels, this comes from the kernel, let's say, this comes from the NTK. So you need, in terms of the data set, if ND is the size of the data set, you need ND squared numbers in order to define the Gaussian distribution. For the nearly Gaussian distribution, you would need ND to the 4th numbers. And if you were to continue to compute additional corrections for accuracy L to the K over N to the K, your effective description would need N to the 2K numbers in general. And this counting comes from the new data dependent correlation functions that you get by going to the next order. And in this way, this analysis would give you a sequence of effective theories with increasing accuracy at the cost of increasing complexity. And this is really going to be the main point. There's a duality here in which complexity in parameter space is traded into simplicity in sample space, and density in model parameters is exchanged for sparsity in the data dependent couplings, the numbers that you need to define the effective fully trained distribution. And in this over-parameterized regime, the point is that we should really identify what we mean by model complexity with these data dependent couplings rather than the model parameters. And so this is basically what I said at the beginning of in my first lecture, that there's different regimes where, depending on, there's the infinite width limit, there's the nearly Gaussian limit where networks are working well, and then there's more generic non-Gaussian descriptions. But for these very deep models where you require this many parameters, first of all, the effective theory or the macroscopic description would be cumbersome and not particularly useful. and we've given arguments for why we don't think networks in this regime would be trainable, and in practice that they're not. So that's the point. The epilogue. Sorry for rushing through that, and thank you for listening to Sho and I for showing me for 5 lectures. We really appreciate it.
Okay, so before we take more questions for Dan, let's just pause for a moment and thank both him and Sho. You know, I think all this stuff with the like cubic and quadratic models in which you can actually say something about feature learning is extremely interesting. I also find that it's like almost fantastical that you can write down in any closed form what a finite width network is actually going to compute after training. I mean, you know, Dan says it looks horrible, and it does in some sense of the word horrible. I mean, there's just lots of things, but like it fit onto one slide, more or less. That's like for me, that's very exciting.
You have to shrink the slide, but it does fit. You can maybe print it on a t-shirt if you want to.
Yeah, right. Exactly. So let me turn it over for some more questions if there are some, and otherwise I just remind you all that in about 20 minutes we have the symposium as well.
Paulo. Sorry, Varun, I knew you wanted to ask earlier, but Paulo is to the left on my screen, but I'll get to you.
Hey, thanks. Yeah, I really enjoyed this mutual information analysis to find the optimal ratio. I just wanted to ask, do you have some intuition why it's so different, this R star for, you know, depending on the nonlinear, on the nonlinear activation function?
Yeah, so I mean, it arises from the 4-point correlator, the connected 4-point correlator, which controls the fluctuations. And so, I mean, maybe that's like saying the same thing, that somehow ReLU nets fluctuate more. That just seems to be a fact. The numbers that you get out of it, the analysis falls into 2 different universality classes. I think Sho discussed what we call the scale invariant class versus the k star equals 0 class, which is basically smooth versus things that are ReLU like. And the way you do those analyses are well, for single input, they're similar. You just compute these integrals, and yeah, I mean, even though they're universality classes, the details of the activation function control that number sometimes. Well, for the smooth one, it doesn't. You always get this. You always get, for anything that's like tang, sine, and so forth, you get one number. But for the non-smooth ones, it does depend sort of on this A plus, A minus, like how you define the activation. And beyond that, that may have been just regurgitating what you already extracted, like for reasons why ReLU behaves like this. I don't know. And deep linear, I should say deep linear networks behave somewhere between tang and ReLU. So they don't fluctuate. They fluctuate more than tang, but they don't fluctuate as much as ReLU. But on the other hand, you know, that analysis is not enough. It tells you about the optimal aspect ratio to be trained, but deep linear networks still have a horrible inductive bias, according to the starpolation discussion that I had earlier. So I mean, I guess I'm making a separate point, which is that there's a lot of things that you have to take into account when you're thinking about these things. And I think I've given you all the intuition I have. Thanks for your question.
Yeah, that makes sense. Thanks.
All right, Varun. Sorry to make you wait.
No, you're fine. The first thing I wanted to ask, since you had like 2 terms for DDNTK1 and DDNTK2 in the big giant expression at the beginning, and you were saying that you're explaining that there's like wiring happening between like I think it was the labels, correct?
Yep.
Is there some type of qualitative difference between the DDNTK1 type of wiring versus the second one? Is there something like qualitatively different happening, or that you could glean off?
It probably would take too long to scroll back, but from what I recall, I think the form of those terms is the same. So like as if you allow me, for the cubic model, as meta kernels, right? They would be the same. The difference is in the algorithm projectors, at least the way we wrote the solution. And one of them arises. So if one of them arises, only one of them shows up if you look at the evolution of the network output, but both of them show up if you look at the evolution of the NTK or the DNTK. I don't yet have a sense for one is helpful or harmful in terms of things that you might care about for the network. Yeah. In principle, you can take what we did and start answering those questions, but we don't have a sense of that yet.
Gotcha.
So we always refer, mostly we've referred in our work, refer to them collectively, except for when we need to be precise about the recursions or the particular details.
Sure. Okay.
One of them doesn't show, so if you do direct optimization, in some sense, the NTK changes a lot less, and only one of the second one, I believe, doesn't show up at all. And that's why the solution was a lot simpler. So
okay.
Anyway.
Cool.
Yeah.
I had one more question about, so like so all of these lectures sort of seem to answer like a lot of questions that people have had for a long time. And it's like a cool theory. Is there any like questions that you like, maybe you sped during like the last like epilogue section, are there any questions that you still think are sort of like, oh, we need to like figure this out? Like what has been left like still unexplained in your view?
I mean, there's a lot of great questions, I think, that you can use this to begin to answer. In particular, I mean, so sort of the obvious one is this I think is a pretty nice story for deep MLPs. You might care about other architectures. The framework will let you analyze other architectures. I mean, in the same way that people define kernels for other architectures, you just have to go through the perturbative analysis. And I think there would be different intuition that you might learn from that sort of thing. There's also, you can use these techniques in conjunction with, so a lot of what this tells you about is how different observables, how different correlation functions that you can measure relate to different properties of your solution, right? We're able to connect a bunch of things directly to generalization error. So some of those things for deep MLPs are computable, but for other situations, maybe you don't know how to compute them, but you can always measure them. So I think a lot of what we can do with these tools is come up with practical ways of saying, well, maybe I don't know because someone didn't go through the full theoretical analysis of what the answer is, but instead I can measure a few simple quantities that we know are important because universally they get translated to the generalization error, and we understand how that works. Measure those things ahead of time and use that to fix some of the hyperparameters. I mean, I'm being kind of vague here, but I think there's approaches like that. And then I guess one other point to make is well, 2 points. One is there's a lot that we didn't talk about. Like I gave the results, but you might have lots more questions about feature learning, how feature learning works, what sort of features are learned, or if you just want to use a quadratic model, what sort of meta features or meta kernel should you pick, right? In principle, like this is Misha was describing how exuding how kernel machines are great, and they are, but maybe these nearly kernel methods are also like even better, in which case the choice of these particular objects outside of the neural network setting could be pretty interesting to sort of develop a theory and understand how that works. And then the last thing I'll say is that by design, everything we did is conditioned on the data, right? What we're doing is solving the same problem that a practitioner would do, but using theory. We're trying to ask, given a data set, what function is learned and what predictions are made on held out data. Now, I don't like making unrealistic assumptions. So I don't think, I mean, you could also pick a data distribution and then see what happens. And like that might be a useful exercise sometimes, but you could begin to ask more generally, for instance, how do the statistics of a data distribution? So rather than conditioning on the data set, write out the statistics, which are things maybe that you can measure ahead of time of your data and see how those are transformed by the network. And in some sense, that's encoded already in our recursions, but I think there's a lot that can be done about that, or even just more broadly understanding how to make things unconditional or learn more about data dependence, but hopefully doing so in a way that doesn't make unrealistic assumptions about the data. But I think all those, sorry for speaking so quickly, but I think there's a ton of things that are exciting to still answer about this. The idea we were hoping is that this is a framework in which we can begin to start answering all the really good questions that we have about why is deep learning so awesome, why, and how is it working, and also to really emphasize that it's not a black box. I think you can really for any question that you have for a system, when a system works, and and these scaling laws that people have talked about, like when there's very simple empirical results or simple empirical behavior, I think likely there's always a way of making a nice theoretical explanation of it. And so we shouldn't think about things as black boxes, and we should really study as realistic models as possible. And even as I was saying, like, I think this sort of framework can be pushed towards the really realistic state-of-the-art models that people care about, and kind of bridge better between theory and practice, both to improve practice and also understand how these exciting things work.
Gotcha. Thank you. This is a great lecture series. Yeah.
Awesome. Sadak, I think this is the last hand. Hi.
Yeah. So in your slide about starpolation, you had that there's a cubic term in terms of the labels. So there's cubic extrapolation or whatever, cubic starpolation. Is there any intuition why the cubic term specifically pops up, not the quadratic interaction between the labels?
Yeah, so I did talk about that actually. Sorry, I guess it was to whoever asked the question. I said I wasn't going to go back. It turns out it's fast to go back, and I am able to do that quickly. So sorry to who that was before. Yeah, the point is right here. So if you look at the quadratic terms from the quadratic terms from the DNTK, note that the mean of, or as I was explaining, the mean of the DNTK is 0. It only correlates with a network output. So you always need a combination of this guy and this guy in order to get a non-zero term. So then, say, taking that combination, we're only going to pick up a term that's linear in the labels. And so and you see that here when I was discussing the DNTK pre-activation cross correlation. So the mean quantity is not going to be quadratic, and there's a nice argument that you can make, because the mean has one output index I, then you need to construct something that has one output index I. And if you try to make something quadratic, there's no such tensor that you can construct. So the mean can't involve it. The covariance is going to involve things that are like quadratic, and I think I discussed that, but the mean can't. And so if here, when I was talking about the starpolation, I was talking about the generalization bias, for the whole ensemble. So we're comparing the mean against the true label, and since we're comparing the mean, there can't be anything that's quadratic. And so the first thing that shows up is cubic.
I see. Thanks.
Of course. Any other questions?
Okay, if there aren't any more questions, let's thank Dan and Sho again for a very interesting lecture series. So the symposium, which will be the last thing in the summer school, starts in about 7 minutes. So do stick around for that.
Thank you.
Great. We can see it. You want to try zooming forward one slide just to make sure it's working, Ethan?
Yeah, I'll try, and also unmuting. Can you hear me?
Yes.
Okay.
Well, maybe I just randomly said yes.
Does this work?
Yeah, that works. We can see it moving. That's great. Okay, cool. Thanks for logging on a couple minutes early just to make sure.
Yeah.
We've been mainly glitch free, but
No one's been stuck as a cat.
Yeah. Well, that's that's not a bug, that's a feature.
Yeah, I intended to attend like the whole school, and then anyways, and then meetings and everything came along.
And you learned that in theory, there's a difference between theory and practice, or or whatever.
But there are videos, right? So I can maintain at least the fantasy that I will.
There are in fact videos. That's true. They're even time-stamped. You know, just like the extent of my technical knowledge.
I don't know. This seems pretty well orchestrated, as far as I can tell.
Yeah, I mean, thanks. You say that, and then of course the Zoom meeting is going to close, and
yeah,
hopefully not. Hopefully not.
Is Princeton not back to in office?
It is actually, everything is basically back live. I'm just sitting at home because I haven't moved my computer to my office yet. In fact, I don't have any, like I don't have a desk in my office yet. It's not a normal desk. I don't have any boards in my office. About the only thing that my office has is like a floor. Otherwise, I'm not really sure I can call it an office. It also has my name on the door.
Nice.
Otherwise, it would be an office. Yeah. But, you know, assuming Delta variant doesn't become too horrible, everything's supposed to be live. They're even saying short-term visitors are allowed in the fall,
oh, cool.
You know, to give talks and this kind of thing.
Nice.
Yeah.
You're not requiring
what about Google? What's the status there?
So it has been optionally like come in, but then as Delta has been ramping up, like the restrictions when you come in have been more. So at first it was like masks optional if you're vaccinated, and then it was masks required no matter what if you're within 6 feet, and now it's just masks required all the time, but you're allowed back in. And they might, anyways, we'll see.
I see, but breathing is still allowed.
It's not encouraged, but you know,
right.
Breathing optional.
Yeah, I mean, I honestly find it's not that horrible to wear a mask. I don't find that it restricts me too much.
Some of us are wearing a mask all the time, so.
This is a technical summer school, Ethan. You know,
sorry.
Not an exercise in humanistic thinking.
The required return date was supposed to be September, but it's now been pushed back to October because of Delta.
Right. I mean, hopefully it doesn't happen this way, but supposedly there's going to be a peak relatively soon, and then they say it's going to fall off relatively quickly, you know, if it follows how other countries go.
Yeah.
So, I mean, hopefully the peak doesn't happen, but hopefully the fall off happens.
Isn't there some connections between the peak and the tails for distribution that you? I'm just kidding.
I mean, it depends on the dynamics generating the data.
Yeah, I think at this point it would be hard to imagine a fall off without there being a peak.
Well, I think that's fair, given that we're sort of currently in a peak, I guess. That's fair.
Morse theory, maybe, argument. That... Same joke as Dan.
That happens sometimes.
No, but it's non-generic. It's not Morse theoretic, I guess in a discrete set, everything is generic. Okay, let's just give people another 30 seconds to arrive. Okay, so welcome back everyone for our final of the 3 symposia. Our first speaker, it's really great pleasure to have him, is Ethan Dyer. So Ethan, just for a bit of context, got his PhD in physics from MIT in 2014. Then he was a postdoc at Stanford and at Johns Hopkins for a couple of years. And then I think it was in 2018 that he started at Google, where he's currently a staff research scientist, and he's also the co-founder and co-lead of a group called Blue Shift, which is a group of physicists that work on theoretical ML. Hopefully I didn't mischaracterize you too badly, Ethan. I've talked to Ethan quite a bit the last couple of years. It's always extremely interesting and insightful. So I think this talk will be no different. So if I didn't miss anything, you can go ahead, please, Ethan.
Great. Yeah, thanks for having me and for inviting me to speak. So I'm going to talk about some work that was work done with people pictured here. So Yasaman Bahiri, Jared Kaplan, Jae-Hoon Lee, and Utkarsh Sharma. And let me just say, I'm not, super Zoom capable. So if you have questions, I would love if you just interrupt me and ask rather than say asking them in the chat. I'll try to pay attention to stuff, but please just feel free to interrupt me at any moment and derail the conversation however you see fit. Great. So, right. So, over the past, I don't know, since 2012, machine learning models have been getting bigger and bigger with corresponding gains in performance. So here are some examples. On the left is a now quite out of date set of models showing performance versus scale on ImageNet, and on the right is performance for big text models. And today, the hope is to take a pretty narrow slice through the question of understanding how do big models work.
Sorry, Ethan, people don't see the slides for some reason. I see them, but I'm not sure what's, I think some people see them and some people don't.
Do I need to be pinned or?
No, okay. Everything seems to be okay now. It seems to be okay. Sorry, you can keep going.
Okay.
There must have been some strange Zoom glitch.
Okay. Right. So, and the performance gains I'll talk about throughout the talk. I'll mostly talk about loss or accuracy, but just for context, these gains play out through lots of real downstream tasks we care about beyond just loss and classification accuracy. So for instance, if we look at the scaling of performance of text models on many downstream text tasks like question answering or summarization, we see corresponding gains in performance over many orders of magnitude. And if we imagine these trends continue and we can, take these improvements which have, been present for 4 or 5 orders of magnitude, extrapolate them a few more orders of magnitude further, we can expect just by scale these models to have broadly superhuman capabilities. Great. So in addition to the performance benefits we see, there's also dramatic analytic simplicity that happens in these extreme limits, and that's been a major focus of some of the lessons that have happened in this school. So a central example of this is wide networks at fixed depth, which approach linear models in the infinite width limit and one can work out systematic expansions around this limit, which I think you just finished hearing about. Right. So there's this nice analytic simplicity. There's also additional evidence of simplicity coming from the empirical side, where we see long swaths of roughly power law improvement in performance. So here's an example, an older example from Hassness et al. Showing performance versus scale, dataset scale on ImageNet. And we see similar scaling in text models with both parameters and dataset size. But there's some tension between many of the theoretical generalization bounds that have appeared in the literature and the scaling behavior that we see empirically. So for example, here's a bound taken from Rahimi and Rek, Random Kitchen Sinks paper. And they were considering linear models, but similar bounds hold for wide networks, for instance. And these bounds often have some fixed scaling with D dataset size or P parameters, which is independent of the underlying data and takes integer, half integer exponents. And we can contrast this with what we see empirically, which is often data dependent, non-trivial exponents taking values between 0 and 1. So the goal of this talk is to make some sense of these different scaling behaviors by walking through 4 different scaling regimes. And in particular, I want to talk about under-parameterized model scaling with dataset size, under-parameterized model scaling with model size, over-parameterized model scaling with dataset size, and over-parameterized model scaling with model size. And we'll see that these 4 regimes exhibit 2 qualitatively different types of scaling behavior, which I'll refer to as variance and resolution limited scaling.
Is this
right.
asymptotic? Is this asymptotic in a? Is this asymptotic in a P and D or?
Yes.
Mm-hmm.
So and I'll hopefully that'll become crystal clear throughout the talk. So that these different regimes will be take everything large, but different different, P bigger than D, P less than D.
And the ratio always goes to 0 or infinity.
So I will typically take for the over-parameterized scaling with model size, I'll hold the data set size fixed and just think about model set size scaling. For the over-parameterized scaling with data set size, I'll take the model size bigger than anything else I'm thinking about and send that to infinity and then ask about the scaling with data set size. Does that make sense?
Yeah, makes sense. Thanks.
Okay, great. Right. So let's see. Just an outline of where we're going. So I'll walk through and try to give some intuition for sort of why one can maybe imagine these variance limited and resolution limited regimes happening in general, provide a geometric picture for the resolution limited regime, and an argument based on smoothness for the variance limited regime. And we'll see that indeed the scaling in these regimes is borne out empirically. And then I'll try to argue that, in fact, these are so general that you can actually realize them in a fully solvable linear model. And I'll explain how these scaling regimes show up in kernel methods. Great. So to begin, I want to talk about the variance limited regime. And so that's the scaling properties of under-parameterized models with data set size and over-parameterized models with model size. And this seems to be described by the existence of well-defined infinite data or model size limit, and scalings come from just corrections around this limit. So I think you heard just now from Sho and Dan how one can systematically work out expansions around the infinite width limit, with those expansions coming with fixed powers of the model size. And so this framework where we have some well-defined limit with controlled expansion around it, though not explicitly stated, is actually the framework that underlies most of the theoretical results we see in the literature. And so just to give this story in a little bit more detail, if we imagine we have a random variable A that concentrates around its mean A bar with variance and higher moments scaling like some small number epsilon, then if we imagine any sufficiently smooth function of A, which let's call it fancy F, then the mean of fancy F of A also concentrates around fancy F of A bar with leading corrections controlled by the variance of A. Sorry, there's a question in the chat. So the question is, how is model size defined? So this is a good question. The concrete examples I'll talk about in this talk are the width of a model at fixed depth, and in the linear model case, just the number of features. So this is nonlinear features with linear weights, and it's just the number of nonlinear features. In general, similar arguments can be worked out if there's a well-defined, like any kind of well-defined limit as you take the model size to infinity. So for instance, Boris, Sho, Dan, others have thought about combined infinite depth, infinite width limits. So what one could think about similar story there. But for this talk, I'll just mean taking the width large at fixed depth, or in the linear case, looking at the number of features. Great. So here the point is, if I have a sufficiently smooth function, a concentrating random variable, I can the function of that variable also concentrates. And one way that we can get such a concentrating random variable is if it's an average over many independent draws of an underlying variable. So for instance, it could be the average over a large training set or the average over a large number of weights. And again, just to be very concrete, we can think about this in overparameterized models, scaling with width. So as we take the model width to infinity at fixed depth, with certain caveats about optimization, etc., there's this nice result that finite depth wide networks approach linear models, and the leading order behavior at large width for their evolution is just given by linear model evolution, but one can systematically work out corrections to that evolution, and those corrections are controlled by an expansion in 1 over width. So here is a plot. In blue is a width 128 network, 2-layer network, just measuring its empirical evolution and subtracting off the linear evolution. So the black solid line would be what you'd get for a linear model, and this dashed line is what you get with including the 1 over width correction to the evolution. And if we push this through to the loss, we can just expand the loss, and we get that the loss approaches what the loss would be for a linear model plus corrections which scale like 1 over width. And so again, here's just some empirical evidence for this. So this is CNNs trained on CFAR, looked at as a function of training time. The leftmost plot is accuracy, the rightmost plot is loss. And we see that the infinite width model can be better or worse depending on the time that we stop training than these finite width models shown in the different colors. But if you look at the scaling with width, in both cases, whether better or worse, it approaches its infinite width limit with a scaling which looks like 1 over n. And one can construct a similar argument for the scaling with respect to data set size. So one way to think about this is if I think about the training loss as a function of some network parameters for a particular draw of my training data set. If I think about this as a random variable over different draws of my training data set of size D, then this variable concentrates around its mean with variance, which scales like 1 over d. And so if the optimization procedure is sufficiently smooth, then my network output also concentrates around the infinite training set size mean with corrections that scale as 1 over d, and similarly for the loss.
Can I ask you a quick question, Ethan?
Yeah.
Actually, on the previous slide, right before this one.
Yeah.
So I understand, of course, what you mean about just doing this Taylor expansion. But at least a priori, it seems like, when you train the model parameters, those parameters also depend on like various things like the data set size or whatever. So you would have to potentially like re-expand them as well. And they might, and there can be more and more of them, but I mean, empirically it seems to work out, but I'm just wondering if like there's other things you would imagine expanding.
Yeah, let me just make sure. Are you asking specifically in this over-parameterized case? Is that, or are you asking in the data set size scaling case?
So I'm really asking about both. But
yeah, so I mean, let me just walk through the logic in let's start with the model set size case. So here, it's non-trivial, but like you can work out this expansion explicitly for F, for the network output. You could in principle work it out for the weights if you want, but in this case, it's easier to work it out for the network output itself. And you see that it has this 1 over n expansion.
Right. Sorry, I just mean like, you're writing this pretty generically, like for a neural network in some regime, we can kind of check it.
Yeah. So with the model size statement, the statement is like, if I know the variance of say the network output, then I know the then I know how the mean of the loss scales. And whether or not I know the mean, that statement about the network is a non-trivial statement, and for instance, we've understood it recently for large width networks, but in general, depending on how you take, say, depth and width large or architecture in a way that violates this, we don't know it in general. The data set size is actually much more general. So there, indeed, you can push this through, you can start with the gradient, you can push it through to the weights. So you can, for when you're in this under parameterized limit, getting this 1 over d scaling for the data set size, you can make much more general arguments for when that's true. And I'm happy to walk through that afterwards if you'd like.
Yeah. No, so I think I agree with you. That's the kind of thing I was asking about. So I understand. Here, I just missed that somehow. You have to know the variance. I agree.
Yeah.
And if you know something like that, you can at least try to write this down.
Yeah.
Thank you.
Great. And so here's some empirical evidence for this. So we see in these regimes this. So here I'm plotting scaling as a function, so that the different colors are different underlying data sets, and we see relatively little dependence on the scaling exponent on the data set, and exponents that look close to this variance limited type exponent that we expect. Great. Okay, so now we can move on to this other regime and try to give some intuition for what's going on with these resolution limited exponents. And so so here we'll talk about over parameterized model scaling with data set size and under parameterized model scaling with model size. Okay, so how can we understand scaling in this regime? Well, I'm going to give a simple geometric picture, which, if true, allows us to derive this scaling behavior. I'm not going to prove that this picture is the picture that describes neural networks. I think it's plausible, but that's not the point here. The point is, like, given this geometric structure, we can see where a scaling law like this might come from. To begin with, let's start with over-parameterized model scaling with data set size. And let's imagine that our data is drawn from some smooth d-dimensional manifold, and that the target function we're trying to learn, I'll call it fancy F again, is some smooth function on that manifold. So in the picture sketched here, these blue points represent the training data, and the maroon dot represents a test point. And let's imagine that what our network does is to learn to interpolate all of the blue training data, but then on the test point that it hasn't seen, it just takes the value of the nearest test point. Sorry, of the nearest training point, x close. So here, little f is the output of our function, and on a new test point, it just takes the value of the closest training point. And if one wants, so one can generalize this by, say, some simple interpolation from that closest training point, but let's just say it's just literally equal for simplicity of this argument. So if that's the structure, then we can ask, well, what is the loss at this test point? And we can just expand around this closest training point. And in particular, we get that the loss, if we take the average of this over test points, the loss is just determined by the nearest neighbor distance, the scaling between the test point and its closest training point. And so if we're imagining drawing points at random on a d-dimensional manifold, the loss, we can just expect that it scales like the distance to nearest neighbors. And on a d-dimensional manifold, if I take capital D points, the distance decreases as I take more and more points, but with an exponent which is given like cursive dimensionality. So I get something which looks like capital D to the -2 over the dimension of the little d of the manifold that the data is drawn from. And so I get this nearest neighbor scaling distance, which in particular depends on my data set through the manifold dimension and can take non-trivial values depending on the dimension of that data manifold. Great. And so we can run a similar story in the underparameterized picture. Now imagining taking the training set size to infinity and asking about the scaling of loss with respect to number of parameters in my model. And so rather than data being drawn from a smooth d-dimensional manifold that just makes up this manifold, and more parameters are just performing a finer grained approximation to my underlying smooth manifold. And so, for instance, if the network is learning a piecewise linear approximation, which you might imagine for ReLU networks or something like that, we get a picture which looks like this. But quite generally, for mesh approximations to smooth manifolds, we get something which scales like the number of regions, which is set by the number of parameters here, to again a cursive dimensionality style scaling. Okay, and so right, so putting that.
Can I ask you a,
yeah.
Can I ask you a quick question? So in that last case, I guess the dimension of the data manifold would be defined by like the P of X type distribution, but does the details of the network affect in the overparameterized case? Maybe it doesn't based on your explicit argument, but I might think like, you know, the relevant manifold depends on like the task that you're doing or like the model you're using or things like that.
Yeah, so
or like what you mean by D, I guess.
Totally. Yeah. So I think short answer is we don't have at the moment a perfect picture of what we mean by D. So empirically, it seems like once one gets to a saturating model size, like you can do experiments like, does it depend on width? Does it depend on depth? The answer seems to be it does at smaller values of these. Once either of them gets big enough, then there's some sort of saturating manifold dimension that you find, but that's just an empirical observation. Don't have a great understanding. You can also do experiments like, does the target structure of the targets matter? So I'll show some slides maybe at the end if there's time. Like if you take CFAR 100 and you keep the data the same, but change the classes, so it's doing a different problem. So like 100-way classification, 50-way, 2-way, turns out it doesn't seem to change the dimension of the manifold at all. So somehow it seems like even in the classification setting, it's learning something like P of X, like the dimension of the underlying data, although that's like there's no derivation there. It's just like some empirical evidence.
When you changed the classes, did you, I mean, this might be too much in the weeds, but did you like did you change the task?
What'd you say?
Yeah, you changed the task in a significant what like as opposed to just like, is it a dog or like did the my question maybe is not important. I was going to ask like about subset, like, is it all the even digits or not, or versus did you change like the thing that you're looking for, like in a fundamental way?
Yeah, so in those experiments that I'm describing, it's like you go from all of the 100 CFAR classes to something like artificial versus natural. So it's still like they're semantically meaningful super classes of the original label.
Okay, thanks. Sorry.
Yeah, no, that's good. Right. So okay. So the picture I'm painting is these four regimes, and just to maybe cast this in a way that perhaps is more familiar, just to make contact with double descent curves that you may have seen. If we think about like where do these regimes sit in this double descent picture, the resolution limited scaling is kind of, if you imagine sending the double descent peak out to infinity, it's the scaling as you descend your first descent. And if we ask about these variance limited scalings, these are the descents past the peak on your second descent as you approach the infinite size floor. And just to emphasize another point, if what we're trying to do is make the best models we can for a given compute budget, we typically want to live in this resolution limited, not variance limited regime. And that's just because there we're increasing the quantity which is actually bottlenecking performance. So for instance, if I have an over-parameterized model, maybe I can eke out a little bit of gains by making it even bigger, but it's actually my data set size which is bottlenecking me in that case. So if I'm free to increase either one, I get more performance bang for my compute dollar by increasing my data set size. And similarly, if I have an under-parameterized model, I get more benefit from scaling up the model than I do from increasing the data set size. Great. So, okay. So now I'd like to describe how, right, so I gave some sort of empirical evidence and some particular pictures where one can, that relied on assumptions where one can derive this kind of behavior. But one can also see the same scaling regimes very sharply in a simple teacher-student linear model. So to be concrete, let's consider teacher-student setup where I have some target capital F built out of some features capital F sub m, and a student with features little f mu, which are just a subset of the teacher features. And if we consider training this model with mean squared error loss, there's just this is a convex problem. There's a global optimum. And if we do this, say on average over Gaussian teacher weights, we get a loss which looks like the following. So the loss is just a function of K, the kernel, which is here, the fancy K is just the average on different data points over the teacher features, and the different decorations on top represent whether this kernel is evaluated on the training set or the test set. So the K with no bars is evaluated on the test set, and K with a bar has 2 indices on the training set, and K with an arrow has 1 index on the training set. And so if the decorated K was the same as the K on the full distribution, this loss LD would just vanish. But the reason why we get some non-trivial loss here is because for finite D, the K evaluated on the training data set is different than K evaluated on the whole distribution. Okay, and so what we'd like to do to solve this kernel model is just understand the scaling of this loss LD with respect to data set size. And to proceed further, we're going to actually need to come up with some ansatz for what this kernel looks like. And so how might we do this? Well, we can gain some intuition by looking at various examples empirically for what random feature kernels look like. And so here I'm contrasting 2 different types of kernels both of these are built out of the same types of features, random features built from few layer ReLU networks. But the one on the left is evaluated on uniform data on the sphere, while the one on the right is evaluated on MNIST. And so here are the different colors. We took MNIST and we pooled it at different scales. So you start with normal 28 by 28 MNIST. You can pool it by averaging, neighboring pixels, et cetera. So here there's different pool sizes to just artificially generate different data sets. But what we see is that the example on the left, the uniform data on the sphere, so this has a lot of symmetry. It turns out that the kernel itself is also rotation invariant, and so you get a spectrum which is highly degenerate, with degeneracy increasing as you go up in eigenvalue index. So just to be clear, what I'm plotting here is eigenvalue versus index of the eigenvalue. Whereas if you look at something like MNIST or other sort of standard data sets, you see something which looks qualitatively much more like a long power law scaling region for the eigenvalues with respect to the index. And so, to make progress, what we'll do is we'll build in a minimal model of realistic data. And so we'll take as our starting point an ansatz for our kernel, which looks like a power law. So we'll parameterize the kernel eigenvalues as the eigenvalue at index I goes like 1 over I to the alpha k plus 1.
Sorry, can I ask you one more, hopefully not annoying question? Is
Yeah,
there a
sure.
simple thing that you mean by integrable on the previous slide? I mean, by analogy, it looks great, and I think I know what you're talking about, but I'm wondering if there's like a thing that you want to say.
Yeah, so I mean, here there's like there is a large symmetry group in rotations, and also one can like solve analytically for the spectrum in this case. So I don't I don't know if there's like an infinite set of conserved quantities that like is the standard picture for integrable systems, but it is solvable, and it does have huge symmetry group.
Thanks.
So right, okay, so with this assumption for the spectrum, it turns out that we can actually solve this model, and one can do this using replica theory to solve it exactly. If one wants sort of simple intuition for understanding the behavior, one can think about large alpha k, in which case the top eigenvectors of the empirical kernel and the true kernel align. And so we just get this difference between k and this k vector, k bar inverse k vector, just projects out the first d eigen components, and you get the sum up from d plus 1 up to infinity. And so this gives you a scaling of data set size controlled by the 1 minus the exponent that you saw in the kernel. And so just summarizing this story in a diagram, we get some, if we assume a power law scaling for the spectrum of our kernel, we get a power law spectrum for the scaling of the loss with respect to data set size. And a similar computation goes through for the scaling of the model with parameters. So yeah, so far I've just I've motivated empirically, but we haven't really given so much intuition for why you might expect a power law spectrum for the kernel, and it certainly hasn't connected with the geometric picture I mentioned before. But there's actually some nice work going back to Weil about properties of smooth kernels on d-dimensional manifolds. And so if I have a kernel in CT on a d-dimensional smooth manifold, then there's bounds on the kernel spectrum. So for instance, one can rephrase this if you don't like CT in terms of Lifshitz conditions, but here you get a bound that the eigenvalues have to increase no faster than 1 over I to the 1 plus T over D. And so the point is, this is phrased as a bound, and the idea is that generic data, non-integrable data, saturates this bound. And so that's the picture here for where these power laws are coming from, and if they have geometric origin. Right. So adding a node to this diagram, if we imagine smooth generic kernels on d-dimensional manifolds, that gives rise to this power law for the spectrum, which in turn gives rise to power laws with respect to data set size and model size. And indeed, if you go and measure this on random ReLU features on pooled MNIST, we see all these 4 regions where the variance limited scaling is independent of the pooling, and the exponent in the resolution limited case is dependent on the pooling size. Right, and so yeah, so just to summarize, we see these 4 scaling regions quite generally, and the resolution limited region in particular has interesting non-trivial exponents and is relevant if we're trying to understand how to spend compute most efficiently to improve performance. And linear teacher-student models, kernel models, realize a solvable version of this as long as one puts in some kind of minimal model, at least, of what generic data looks like. And so, yeah, so some things that I'm thinking about exploring as a result of this are questions like, can we understand not just how performance scales with data set and model size, but with, are people still there? Sorry, it's frozen for me.
Yeah, I mean, I can still hear you. I think everyone can.
Cool, great. Yeah, so can we understand power laws for compute scaling as well? Like Dan asked, like, what is the data manifold? What role do targets play? And then there's another sort of class of question, which is, okay, fine. You've shown me some plots of things improving with scale, but how does fill in the blank ML problem I really care about improve with scaling? So for instance, like, how does catastrophic forgetting improve? How does performance on subgroup or class imbalance improve? In some cases, we may find that actually this problem that we thought was a deep, important problem in ML is actually only such a problem at small scales, and maybe just scaling up is enough to solve it. And so here's a plug for an effort to crowdsource benchmarks for big text models to try to understand what sorts of problems are solved by scale alone and what sorts of problems need other non-trivial ideas. And happy to go into any of these if people have questions, but I think I'll, for now, just say thank you and yeah, ask if anyone has any questions.
Great. Let's briefly thank Ethan. That was a very interesting talk. As you know, I like this line of work quite a bit. And we definitely have a bunch of time for questions. So I encourage you all to ask away.
I'll ask a question if no one else is, or it looks like someone else is asking.
I think those might be just claps, Dan. I think you're safe.
Oh, unless you want to answer the claps, then yeah. My question, the thing you said about top eigenvalue, this is probably a stupid question that I should just think about, but so is the top one the one that's going to correspond to a single input, or the more complicated part of the spectrum?
Sorry, your question is,
there was a part, and I missed the details, so it's maybe remedial, but there was you assumed something about the spectrum, and then you had some argument, and that gave you the whole scaling, right?
Like this, like, how did I get this part here?
Well, so you said something top eigenvalue. I guess the question is, like, there's a unless I'm confused, but like if you have the kernel, let's take the NTK, there's some recursion, right? So you can imagine solving it, say for a single input or for many inputs, then you have to deal with there's the diagonal part, right? Which is one of the eigen.
Sure.
I guess basically I'm asking, is the diagonal part, I would guess by symmetry that should be like at the end of one end of the spectrum, but that's the wrong end for the thing you want. So you want the other end.
No, I think so. So if I think about the, yeah, so maybe I'll try to make the statement clear, and then I'll talk, like, I'll make a general statement, and then I'll make a, like, properties of NTK type kernels statement. So the general statement is if I have, let's say I have some kernel which is defined over like a full data manifold or full distribution, and then I have just a sampled version of that. Like how do the two spectra relate? Like how do the eigenvalues and eigenvectors relate? And my statement is if I have a hierarchy in the spectrum, then the way they relate is that the top eigenvalues are close and the top eigenvectors are close. And this fact I think is people sort of use it all the time in the following setup, which is if I think about PCA, right? Like I think that my principal components are representative of the principal components in the underlying data. And so that's an example where I think like typically I have some data which is just sampled, but I think that the important directions that I get from diagonalizing the empirical covariance there match some important directions in the underlying data distribution. So that's just so here all I'm saying is just that if I think about the spectrum of K bar, that it matches a spectrum of K in this top part of the spectrum. So that's the first point. And the second point is like, okay, so what does the top part of the spectrum look like for NTK? And I think you 100% can have like the case that the like the all ones vector, which I guess is the is the like largest eigenvector. I think you can dial the relative importance of these two.
I see.
You go from the chaotic to ordered regime at a nit. Yeah. So does that answer your question?
Yeah, I think the intuition of like the symmetry of that, I assume that would be the top or something like that. But I think you're saying it's not. That's not necessarily the case. But it's right. It's the right part of the spectrum, but it's not necessarily the top one. And okay, I think I understand. Thanks.
Yeah. No. Thanks for that question. And you know, maybe advertise that like if you look at say compute scaling in GPT style models and linear models, that this again seems qualitatively like quite similar. So I do think like one take home message is that like there's this quite generic behavior, but I do think these models are like great testing grounds for understanding it.
Other questions for Ethan? Yeah, maybe let me just say, I think this potential direction of including the computation time, and doing all that together obviously seems practically very relevant, but also like understudied. I know very little theoretical work, which like it really includes the compute budget.
Yeah.
Maybe it includes in some implicit way, but like not as a kind of star player.
Right.
So.
And in some ways, I feel like the field, myself included, like has often had blinders on. Like we think about sitting at the optimum of a convex problem. If I'm a practitioner, I don't think about double descent at all, because like why would I ever wait? Like I'm just spending more compute to do worse if I'm at the peak of the double descent curve. But
so I just realized I was muted. Indeed, all I said was indeed. Okay, well, thanks again, Ethan. I think that was a very interesting talk. Appreciate it. I think Guy is already on, and I think that when you're ready, you can share your screen, Guy.
Thanks, everyone.
That sounds good.
Okay, excellent. We can see the slides move, and we can see, I don't think we can see you. Maybe that's on purpose.
You cannot see me because, can you hear me?
Yeah, we can hear you.
Huh. For some reason, it doesn't let me share the camera. Let me leave and rejoin to fix this. Sorry
Sure.
about that.
Okay, let me make you co-host, Guy. Sec. Okay, now we can see you. This is great. We can even see a nice blackboard behind you. Even better.
Share the tab. Mhm. Mhm.
Oh.
Dealing with some permission issues on
Yeah,
the
sure.
work laptop. All right, now it says, I think you might need to make me co-host again.
Okay.
I can share.
Okay, try now.
And
Okay, success. Great. Okay, so it's a pleasure to have Guy Gur-Ari give the second talk of our symposium, the anti-penultimate talk, if you would like. So Guy also got his PhD in physics, just like Ethan in 2014, but from the Weizmann Institute, I believe. He's in a postdoc at Stanford and at DIS, also in physics. And afterwards, he was also one of the founders of Blueshift. And so he's been a research scientist at Google for the last several years, part of the same group as Ethan. You know, I've also spoken to Guy over the last couple of years. It's always, again, been super useful. So, you know, I'm excited to hear about the kind of continuation of the sparsity work, which you told me about at some point. So that this is going to be great. Please.
awesome. Thanks a lot, Boris. Thanks for the opportunity to speak here. Thanks for the introduction. Today I'd like to tell you about a paper I wrote with Anna Galyubeva and Benem Neishabur, where the goal is to try to understand why is it that wider networks perform better. That's a very vague question, so let me explain what that means. We have a lot of empirical evidence that as we increase the width, the performance of networks tends to get better, especially on vision tasks. I think this plot from 2017 is one of the earliest systematic investigations of this, where Neishabur and company showed that you can increase the width, performance will keep getting better. Here, number of hidden units just means the width. And it will keep getting better even when the network becomes over-parameterized. You can keep pushing the width higher, the training error goes to 0, but the performance keeps improving. And since then, we've seen this effect again and again on many architectures and many data sets. And the sort of high-level question is kind of, why does this happen? And more concretely, can we attribute this simply to the fact that when we increase the width, we have more network parameters? So we're just increasing the capacity and then gradient descent makes good use of that. Or are there reasons why specifically increasing the width rather than increasing the number of parameters in some other way gives us better performance? That's kind of the question we'd like to tackle. And to do that, we are going to try to decouple the effect of width as much as we can from other hyperparameters that we control. So we're going to try to control other hyperparameters as much as we can and increase the width. So the most salient hyperparameters here include the total number of parameters. We would definitely like to control that because that is the most direct proxy that we have to the capacity of the network. So we're going to try to increase the width while keeping the total number of parameters fixed. We would also like to control other hyperparameters that we know are important for performance. So that includes depth, because we know the depth of the network can have significant effect on the performance, and any other hyperparameter that we can think of. And as you'll see, we can't completely do this because there's no way to keep everything fixed, including number of parameters, and increase the width. So we'll have to make a best effort at approaching this sort of ideal decoupling. And what we will find is that, at least with one way of doing this that we found kind of natural, we will actually see that width by itself can improve the performance of the network. So increasing the width improves the performance of the network, even though we're not introducing any new parameters. So this plot is gonna show that, but we'll get to that. And before we go into what we did, I want to mention that there are definitely previous works that have looked at the effect that width has on performance. In particular, in the scaling laws paper from Kaplan and company from OpenAI, they did this nice experiment where they changed the aspect ratio of the network. So aspect ratio here means take the ratio of the width, that's the model, over the depth, that's n layer. Do that while keeping the number of parameters fixed, just like we'd like to do. And they found that there is indeed some effect on performance. So it looks like there is some trade-off between width and depth in their experiment. However, in our case, we would like to stick, when we make these changes, we would like to stick, excuse me, as close as possible to the original architecture. If we can, we would like to not change depth and not change other things which we know have a strong effect on performance. And so the criteria we set here are, yes, we're going to fix the number of parameters. We're going to try to make the modification as we're changing the width as simple as possible. And we'd like to make it be a minimal change to the architecture. This part is definitely subjective. We try to find things which we feel are the most minimal changes to the architecture, but it is a subjective question whether you would call this minimal or not. So let me just say what we tried, and then I hope you'll see how this fits in within our criteria. So how do we increase the width while keeping number of parameters fixed? We tried 3 different methods. The first method is to introduce a linear bottleneck. So here the blue part is a weight matrix of a layer, and the red line is a nonlinearity. So with this first method, we are introducing an extra linear layer in the middle. So we're basically, you can think of it as factoring the weight matrix into 2 weight matrices, but not introducing any linearity, any nonlinearity in the middle. And this allows us to increase the width of the original layer while decreasing the width of the bottleneck, so introducing a bottleneck. And so because we have this new parameter to play with, this allows us to keep the total number of parameters fixed. We are introducing a new layer here, but we're still not introducing a new nonlinearity. And so in that sense, even by doing this, we're not actually changing the capacity of the model, although we are affecting the training dynamics of the model, because as we know, even if we introduce linear layers in a network, gradient descent can behave differently. So that's the first method. The second method is to consider a nonlinear bottleneck. So here we look at a pair of layers. We're not introducing any new layers. We're increasing the width of the first one and decreasing the width of the adjacent layer, introducing a new nonlinear bottleneck. And so here, this is perhaps a more minimal change to the network. It has the downside that we're not strictly increasing the width, we're also decreasing it elsewhere. And so it's not clear that this is exactly capturing what we want, but that's another thing we can do. And the last method, which is the one we'll focus on for most of this talk, is to introduce a static sparsity pattern. So here we're going to increase the width of some layers, and we're going to take the weight matrix of these layers, which is now enlarged, and we're going to set some of those weights to 0. We're going to choose randomly which weights to set to 0 at initialization, and we're going to keep those weights at 0 throughout training. And the number that we set to 0 is going to be such that the total number of tunable parameters is fixed as we do this. And so first, let's talk about what happens when we do the two bottleneck methods, what the results are, and then we'll turn to the sparsity method, and that's going to be the bulk of the talk. Okay, so here's what happens when we consider introducing these bottlenecks. So in each one of these plots, we train ResNet 18 on a particular data set, CFAR10 or CFAR100. And each curve here, each color, corresponds to a series of models, which all have the same number of parameters. The leftmost model is an ordinary ResNet with some width. And then as we go right along the x-axis, we make it wider, and we keep the number of parameters fixed, either with the linear bottleneck method or the nonlinear bottleneck method. And what we can see is that we don't see a bump in performance using any of these methods. It seems that either with the nonlinear bottleneck or with a linear bottleneck, it only gets worse as we increase the width. And so we can say, by this measure, width is not helping at all. In fact, with a linear bottleneck, if you look at the dashed lines are the performance of the original network. And you can see that even just by introducing this extra linear layer, even before we do any widening, we're already hurting performance. And it sort of, at least in some cases, never recovers. I'm just talking about the fact that the solid line here, which are the bottleneck networks, the performance is worse than the baseline original network, which is the dashed line.
Yeah, it doesn't necessarily seem to be true for that dark blue line. Do you just view that as like close enough to being true, sort of?
Yeah, this is that's true. This is like what is it? Probably 0.5% maybe here, which I would consider that could kind of be a fluctuation. It's just a tiny.
Fair enough.
Yeah. Yes. The other thing also, maybe from kind of a scientific perspective, we are trying to stay, one of the criteria is to actually try and stay as close as possible to the original architecture. So the fact that we need to make this change, we're making this change, which, it doesn't change the capacity of the network, but after training, we see that it actually does have a significant effect on performance if we just compare the leftmost dots with the baselines, right? So it looks like we did do something more than we kind of intended. This was not such a minimal change because we can see a few % drop in performance just by introducing this linear layer. Okay, so this is not terribly exciting, and so we'll move on to the next method, which is to introduce static sparsity. So again, what I mean by this is we like to keep things as simple as possible. And again, there are many works introducing sparsity into neural networks. Most of these works have to do with how can we set some parameters to 0 to maybe save space while not deteriorating network performance. And typically the way to do this is to first train the network and then use the information after training to prune some of the weights. The most common way to do this is to train and then take the some % of smallest weights that we got after training and set those to 0. And very often you can do this in a way that doesn't actually hurt performance. And so you get a smaller model that is useful, maybe if you want to fit it on your phone or something, but you didn't hurt performance. Here, we're trying to really isolate the effect of width. And so we want to do everything before training. We want to just look at a different kind of architecture with larger width. And so we're doing something much simpler, which is at initialization, we're going to initialize the weights. We're going to also select at random some of these weights to set to 0. And then we're going to change the width, keep the number of parameters fixed that way, and see how it affects performance. This is kind of if you keep the width fixed, this is a silly thing to do because, of course, if you remove some of the weights at initialization, you're going to get worse performance, but it is helpful for our goal of trying to understand what width does. So having said that, we still need to choose across layers how many weights to set to 0 in each layer, right? This is still a choice that needs to be made. So we know we want to choose things randomly, but we still need to choose how to distribute these zeros across layers. And to do that, we ran some simple experiments. So here is a small, fully connected ReLU network with just one hidden layer. We train it on MNIST, and we scan over 2 parameters. So each square here is the result of one experiment of one network. These networks all have the same number of parameters. We change the width, and we we can sparsify the first or the second weight matrix in this network, right? It has one hidden layer, so 2 weight matrices, and we scan over the connectivity. Connectivity here is 1 minus the sparsity. So the connectivity of the whole network, and we also scan over, keep the connectivity of the whole thing fixed, but just change the connectivity of the last layer. I choose keep the connectivity of the whole thing fixed, but take more or fewer weights away from the last layer. So connectivity 1 means connectivity of the whole network 1 means that it's all completely dense. And again, connectivity of last layer 1 means that the last layer weights are all there, no zeros. And so what we find here is that, so we see 2 things. One is if we go from the top right point, which is just the ordinary dense network, and we start decreasing the connectivity of the whole network while increasing the width, we see that this helps performance. And actually, this seems to be the best thing to do to get better performance. However, we see that if we reduce the connectivity of the last layer, this typically hurts performance. And this is telling us that, yeah, sparsity helps, increasing the width while introducing sparsity can help, but we shouldn't do that in the last layer. We should do it in the first layer. And the intuition for this is pretty simple. So this is MNIST, and so the first, so the input is like 784, and the output has size 10. And that means the weight matrix in the first layer is much bigger than the weight matrix in the second layer. And so it kind of makes sense that we'd like to take away a larger proportion of weights from the larger weight matrix, because if we start taking it away from the smaller matrix, the second layer matrix, we quickly kind of probably hurt connectivity, and we quickly make it difficult for the network to optimize. So it's kind of intuitive that we want to take more weights away from the bigger weight matrices. And this is kind of what this experiment is telling us. And so this is what we did. This is how we organized the sparsity algorithm. We we organize all the layers by size. We start taking away weights from the biggest layers, and once the number of weights in those layers matches up with other layers, we start taking away weights from all those layers combined, and so on. So we only take away at each step of like sparsifying, we only take away the weights from the biggest layers. And that indeed led to the most interesting effects from the different methods that we tried.
Can I ask a quick question, Guy? So when you do this sparsification, you're not balancing anything. Like some neurons could have like, a lot of weights removed, and some could have slightly fewer weights. It's not like you're, making sure that every neuron has the same number of its weights going into it, let's say removed or whatever.
That's right. For each weight, for a given weight matrix, once we decided how many weights to take away, we're just randomly choosing those within the matrix. Yeah.
Okay, thanks.
Okay, and this is what we find. So these are experiments. I'll explain again what the plots mean, but these are similar plots to the ones we've seen before, just with this other method of increasing the width. So again, each plot here corresponds to training resonant 18 on one of these data sets. The leftmost points correspond to dense networks with a certain number of parameters. So these are number of parameters. And then as we go to the right on each one of these curves, we're increasing the width, sparsifying such that total number of parameters stays fixed, and measuring the performance. And what we see typically is that we get a performance boost, and you can see it's in some cases it's a non-trivial performance boost of several percent in accuracy up to some point. And then as we keep increasing the width, the performance deteriorates. So in some sense, we're increasing the width, but we're in some sense sparsifying too much, and then we get worse performance. This effect is more pronounced on the smaller network. So if we start with a network that has fewer parameters, we see a larger bump in performance. If we start with a network that has lots of parameters, we still see an increase in performance, but it's smaller. The bump is smaller relatively. But we see this effect across different data sets. So I hope the effect is clear here. The effect is we're widening. All these networks along the curve have the same number of parameters, and yet we get a bump in, we get better performance by doing this. So
one more question.
Yeah. Mm-hmm.
One more question about this guy. It seems like a lot of the peaks, like if you look at that middle plot, correspond to like a similar widening factor, although the models are rather different. You know, like, is that something you see kind of consistently, or is it just like it's something where there's not much spread in this experiment?
So I would say that, yeah, the optimum we've seen is more or less around the sort of 10-fold widening factor, typically. I mean, I can't say that they all lined up like perfectly, but around 10-fold seemed to be the number where we got the best performance. Yeah. Okay.
That seems non-trivial. Like I wouldn't have necessarily guessed that's the same for different architectures on the same problem.
Yeah, so I should say we haven't tried. I mean, I can say that this seems kind of true for fully connected and for ConvNets or ResNets. Maybe, you know, if we go elsewhere, like the transformers and so on, I think the picture is different. But at least for this set of architectures, it seems consistent.
I see. But you're kind of saying you maybe could predict this by like training a small model or something, you know, and then you could predict how to scale a larger model, you know, if you wanted to fix the sparsity or something like that.
Yes, that I think is true, and that is like what these experiments are actually showing, because this is consistent across model scales. Yeah.
Okay. Yeah. Thanks.
May I also ask a question?
Please.
To me, it seems like if I compare the linear bottleneck case versus this case where you have a random sparsity pattern, what seems to happen underlying as a side effect of these two experiments that you're doing is that the rank of the weight matrices is changing quite differently. So in the linear bottleneck case, the rank is decreasing, whereas in this random sparsity case, the rank will not really decrease or would be about the same because you're just randomly removing. And of course, model complexity depends on number of parameters, but it also depends on, I think, maybe in more structured ways. So do you also think maybe the rank of the weight matrices could be at play?
Yes, I agree with that. Like, I don't know how to make that formal, but I agree that like the problem with the bottlenecks is that is the fact that the bottleneck makes the rank smaller. It might be here that this is it might be here that the rank is helping. I can say that in practice, like another way I think maybe to say this is we're keeping the number of parameters fixed, but we're not keeping the compute fixed, right? The compute is increasing when we're doing this because we have more neurons. And so that's not exactly the rank, but that's kind of another thing that we're changing here. But I mean, that intuition makes sense. And maybe there's even yeah, I'm trying to think if there's like an experiment to probe that. Nothing comes to mind immediately, but the intuition does make sense to me.
Okay, thanks.
Thanks. Other questions? Okay, cool. Here's another experiment and also an ablation experiment that we did with ImageNet. So on ImageNet, same architecture, looking at ImageNet, we're seeing the same effect. So if we look, so here the x-axis again is again the width. In the bottom line, we have the sparse models, which all have the same number of parameters. And we see again the same effect. We start with a baseline model at 68% accuracy, and we increase the width, keep the number of parameters fixed, and we find that the performance increases. So here we can even increase the performance by like 2.5% on ImageNet, which is non-trivial. We also compare that against what we get if we just increase the width and make the model dense. So like as we would normally increase the width, that's the top row. And we see that actually for a while, the performance of the sparse models tracks that of the dense models, even slightly outperforming the dense models in a bit, although this might be a fluctuation, maybe 0.5% might be a fluctuation, but it at least tracks the improvement that we get from width up to some point. Beyond some point, again, the sparse performance starts deteriorating and the dense performance keeps improving like we would expect. And so we want to say that based on this comparison, at least initially as we're increasing the width, most of the performance improvement from increasing the width can be attributed to the width itself, so to speak, and not the increase in number of parameters of the model. And here's another plot that shows this. So we just discussed what this looks like on ImageNet. Here we're basically plotting the same kind of data. We're trying to see what is the what part of the improvement in performance can be attributed to width versus the rest, which we attribute to maybe number of parameters. And those are the black line, the black dots here. And so we see this is not only happening for ImageNet, on other data sets as well. We see that at least initially, most of the improvement in performance, so above 50% of the improvement in performance, can be attributed to the width and not the number of parameters. So again, these are all plots that we get by comparing the performance from increasing width with a dense network versus increasing it with a sparse network. Okay, so it seems there is a real effect here. Here's another experiment that we tried. This goes a bit to your question, Boris, of what happens if we what would happen if we tried to sparsify in a not a completely random way. So here we try. So I explained what it looks like on fully connected networks. With ConvNets, the weight matrix is actually a rank 4 tensor, right? Because we have the X and Y directions, and then we have channels in, channels out. And we can ask, well, what happens if we sparsify non-uniformly across these different axes? For example, the hypothesis that we had was that maybe keeping the kernels either completely dense or completely zero, maybe that's better than sparsifying things uniformly, where we get kernels which have some zeros in them, where like many kernels will have some zeros in them. So that means choosing to sparsify just along the channel axes and not along the XY directions, if that makes sense. But bottom line is we found that actually doesn't help at all. It actually hurts. The best thing we found is just to take this whole weight tensor as a whole and just randomly sparsifying it, disregarding the fact that we have an E-axis structure. So that was the conclusion from this experiment.
That's very interesting. So how small is the smallest connectivity? Like 0.01?
In this experiment, yeah, something like that, maybe 0.01, 0.02, yeah.
Okay, thanks.
Yeah. Okay, so that's the empirical part of the talk. And in the time I have left, I want to suggest kind of a first step toward a theoretical understanding of this effect. And it's going to be based on kernel methods, because that's kind of the best handle we have at the moment for addressing these questions. You'll see there's still going to be a pretty big gap between like running experiments on ResNet and what we're going to do theoretically, but we'll see that there seems to be some nice agreement, at least with the simple experiments. So we're going to sort of scale things down to a much simpler model that we can get a handle on. We're going to look at a fully connected network with one hidden layer and ReLU activations. So you have the input X, first layer weights U, and then second layer weights V, and a ReLU activation in the middle. And we're going to initialize the network using this distribution over the parameters theta. So theta here is collectively U and V, with some probability P we're going to initialize the weight as a Gaussian, and with probability 1 minus p, we're going to set it to 0. So this is a direct delta function. And that's going to be our initialization scheme. And then as we train the network, all those weights that happen to be 0, they're going to stay 0 during training. This is not captured by this distribution, but that's what we do when we train the network. And we're going to look at the Gaussian process kernel of this network with the sparse pattern. So this is the Gaussian process kernel, which I believe people are familiar with, and I'm sure you discussed also extensively in the classes. And the hypothesis is as follows. We're going to make a few kind of leaps of faith here. So we know that as we increase the width, performance gets better. We also know that as we increase the width, if we scale everything correctly, then the network can be characterized to a better and better approximation by the infinite width GP kernel. And so what we can do is we can measure the distance between the finite width GP kernel and the infinite width one, right? This is a measure of how close are we to the infinite width limit. And we're going to guess that this distance to the infinite width kernel is correlated or anti-correlated with the performance of the network. That is, the closer we are to the infinite width limit in this measure, in the measure of distance in kernel space, the better the performance should be. And now for a given number of parameters, we can compare the distance of a dense narrow network to the infinite width one, compare that against the distance of a wide sparse network. And if we find that the wide sparse network is closer to the infinite width one, then maybe we'll say we predict that the performance will be better. I'll explain this all again. I know this was kind of fast probably, but roughly we're trying to, or at a high level, we're trying to measure distances in kernel space and say that that kind of maybe correlates with the performance of the network. Now, technically, the reason we need to have some kind of handle on these calculations to say anything about this. And the handle we have is the Cho and Sol kernel. So if we write down the GP kernel for this network, and then we take the expectation value at initialization, we end up with an integral that looks like this. This is just writing out what the kernel is, having an integral. Oh, sorry, I forgot the Gaussian measure here, but there needs to be a Gaussian measure here over the U weights. And then these are just like the activations of the hidden layer of the network. H is the step function that comes from ReLU, and the point is not the detailed structure of here is not important. The point is just that we know how to calculate such integrals. That's really the point. We can do these integrals analytically, and that's going to be helpful in the calculation. We can do similar things with the NTK, but it's just easier to work with the GP kernel, and we still get interesting results. So this is so repeating what I said before. This is the object that we would like to compute. We would like to take the GP kernel of some finite width network with sparsity, and we'd like to compute the average distance, the mean distance from that to the infinite width kernel. Okay, so that's the thing we would like to calculate, and then we would like to do an experiment and compare that against the performance of the network. Also related to your question, Boris, if we can calculate this thing, then we can find this, so we can fix the number of parameters, and we can find the sparsity at which this distance is minimized, and that will give us a prediction of maybe where the best performance can be expected. And then we can compare that against these other empirical results that we have.
But it seems like you can calculate this expectation explicitly in this model. Is that too ambitious?
No, that's what we'll do. Maybe not to your standards, but to my standards, yes.
Okay, no, but at least I get the answer. Like the integrals are tractable. It's just some things are zero sometimes, independent of some other things.
Yes, that's right. That's right. Mm-hmm. That's right.
Cool.
And so this is kind of where I'm. You know, my background is in physics. I can't prove all these things, but some things are simple enough that I can write them down formally. And so once you crank these expressions, you can get a somewhat opaque expression for this average distance between kernels as a function of width and sparsity. So there's some width here, which is n, the number of neurons, and sparsity is controlled by that probability p of having a non-zero weight. And so we get some expression in terms of k, which are the Cho and Sol kernels, these integrals, and also what we call k tilde, which are just these sort of weighted averages of the kernels k, weighted simply by which weights happen to be zero and which weights did not happen to be zero. So we sum over all those, or we take a sort of expectation value over all the different sparsity patterns that we can get. We get this ugly, big ugly expression that we can write down explicitly. And then the question is, what do we do with it? And the answer is that with some hand waving, we can take these sparse kernels that control the answer of the kernel distance, and we actually can simplify them quite a bit. The basic insight here is that if you take your input dimension to be very large and you don't take your sparsity to be too small, then most of the terms that actually contribute to the sum in practice will have a certain amount of non-zero weights in them. So most of the sparsity, so there will be a typical sparsity pattern in the sense that there will be a typical number of non-zero weights, and we're just going to focus on them because those are like the dominant contributions to the sum. This is kind of a typical argument when you deal with these things, and I'm sure this can be, I think this can be made formal, but here we just took this as an assumption. Another assumption that we make are that the input vectors to the network behave as random vectors, and that helps us calculate what happens when we take a vector dot products of them. We assume that they behave as random vectors. This assumption actually in vision is an extremely good assumption. If you take two images from a typical natural vision data set and you look at their dot product, and you do this across the whole data set, they seem surprisingly close to random vectors in terms of what their dot product looks like. And so this is actually a great assumption in practice. Okay, so once you take these assumptions, that helps us simplify these opaque expressions a lot, and we end up with this this expression for the distance between the kernels. This is an approximation, but we have the input dimension here. We have the sparsity p, we have the width n, and so we have a prediction for the distance between the kernels. And if we choose to take this seriously, we can, for a given number of parameters, we can actually calculate the sparsity at which the distance becomes minimized. And so we get this very simple expression for that. And then we can go and compare this with an experiment. So we take the same network, fully connected network with one hidden layer. We calculate this distance, let's call it d. This is the average distance between kernels as a function of the width. That's like the solid line here. And we can compare that against the test error of all these networks. And we can see that actually we need to normalize the whole scale. So there's one normalization parameter that's happening here to match the test error against the kernel distance. Once we do that, we find that it tracks really well up to a certain width where it breaks down. This is a width where our assumption that the sparsity is not too low breaks down. We assume that input dimension times sparsity is much bigger than 1. If we increase the width enough, sparsity is going to be small enough that that assumption breaks down, and then that whole approximation we had to do with the sum breaks down. And so that's where we get like this deviation, but the approximation is good enough that it actually predicts where the best performance is going to be. So yeah, so at least in this simple setting, it seems that the theory surprisingly is actually correlated with experiment. And I say surprisingly because the calculation we did was just a calculation at initialization. There's nothing here about gradient descent. This is just taking the GP kernel at initialization and calculating some distances. That's why we got away with just looking at the sparse initialization scheme. We didn't have to say anything about tracking the weights and making sure that they're 0 in the theoretical calculation. But still, somehow this captures what's going on with the test error after some training.
Maybe another question, Guy.
Yep.
So is it true that if, you know, your P is like much bigger than D, like log D over D or something like that, or I forget what the numbers are, but you're in the regime where you're not too sparse, that you can also sort of make the NTK analysis go through, in the sense that you just plug through the usual calculations and the NTK is close to its initialized value and the mean is going to be well conditioned. And in the sense that I'm just wondering if in this regime where you see it, you're already kind of implicitly in the NTK regime. You know, at least if the width is kind of big enough to start.
Yes. So I think these are like two questions. So I think the NTK calculation will go through. I think that's true. The question of whether in this experiment we're in the NTK regime, I think the answer is no. I don't think this width is big enough to be in the NTK regime. You probably need like at least 1,000. 1,000, 2,000, that's kind of where you start seeing the NTK regime behavior. Yeah. So this
even
is
on MNIST.
Yeah, I think even on MNIST, yeah.
I just have no idea.
Yeah, I think that's right. I think 1,000 is kind of where you start seeing that. And but that's also a good point. That's another reason this is surprising. I would say that this is not really a large width regime, and we're like the large width assumptions are really heavily baked into this.
Right. Okay. Thanks.
Yeah, and to show that this is not just it does not seem to just be a fluke. There was another paper that came out around the same time from a group at Apple called Collegial Ensembles. And what they did was they took a somewhat more practical approach to this, because the way we're doing sparsity, it's not very practical. The hardware we have to work with doesn't actually let us reap the benefits of these 0 weights. We effectively still need to calculate all the matrix vector products just like before. There's zeros in there, but like the zeros are still counted like in the calculation. So we didn't actually gain any compute benefit from doing this sort of sparsity. They kind of took a more practical approach and they used the structure. I mean, I can recast what they did as a structured sparsity experiment, where the weight matrices, you can think of them as having some kind of block structure. There are like 0 blocks and non-zero blocks, and that helps when you try to implement things efficiently. But they also did a theoretical analysis also based on kernels, so pretty similar. And they also found surprisingly good agreement on CFAR 100. So here, objective here is like their kernel distance calculation. They did something slightly different, but it's close enough that I think it kind of captures the same effect. There is the theoretical line, and then there's the performance of their networks. Please disregard the right plot here is some other experiment that they did. The relevant one is like the left experiment, and n is the width. And you can see that yeah, it also tracks the kernel distance calculation surprisingly well. So I think there is some interesting effect here, which again, the results are, they seem to work well, and I don't really understand why. And I talked to them about it, and they don't really understand why this agreement is that good either. And so I think this is kind of an interesting effect. Okay, so let me summarize quickly. Our goal was to isolate the effect of width on network performance. The empirical effect we found is that as we increase the width, we sparsify the network. And these wide sparse networks tend to outperform narrow dense networks. The effect is bigger the smaller the original network is, and we proposed a kernel-based explanation for why this might be the case. Thanks a lot.
Great, super interesting, Guy. Thank you. I think we have time for 1 or 2 quick questions while Suriya gets set up.
Yeah, I have a quick question, actually, if that's all right.
Sure.
So I'm a I'm a little suspicious of the argument you gave about, well, you didn't give the full algorithm that you used, but about how the output weights in the 2-layer network are smaller. So the effect of sparsity. I think even if you had a deep network with hidden layers that are all the same size, so most of the layers are the same size, I think sparsifying the deeper layers is going to be far more problematic. And it's hard for me to, at least in my mind, disentangle that effect. If you just think about how the NTK features, say the derivative of the network output with respect to the parameter, right? That's like the NTK features. They're going to involve a chain of weights from the last layer to the weight that you're considering. So if you sparsify in the later layers, you're killing a ton of features compared to the earlier ones. And so I would expect the performance to care a lot about the number of features. And so unless you hit that exact, I mean, you're using a ResNet 18, so it might be hard to figure out what this correspondence is, but the point is you're using a deep network. And I feel like I would expect that it's very sensitive to exactly how you change the sparsification as you go deeper.
So yeah, I can't say I really understand this. I don't think I have a good answer. I think the best answer I can give you is we kind of noticed this when we started with deep convnets and we just tried sparsifying uniformly, and that didn't work well at all. And we kind of, through experiments, isolated the problem to the last layer. And I didn't show all that. I just showed the simpler experiment. So I kind of empirically believe what I believe what I said because we did some other experiments that support this. But I see your point. I think maybe this goes back to the question about rank. Maybe the fact that we're increasing the width, but by sparsifying, we're not really lowering the rank of the matrices in the deeper layers. Maybe that's the thing that's keeping the performance from deteriorating. But I don't think I really have a good answer, except that that's kind of what we saw empirically. Does that make sense?
Yeah, I just think, I guess just in trying to interpret what's better, it's hard for me to, I mean, as you said, the last layer is very important because every single feature goes through the last layer. So if you sparsify in the last layer, you're killing a ton of features. But the point is, I would expect the particular details of the result in terms of what's optimal or not to care a lot about sort of the algorithm that you use or the ratio of sparsities at the different depths. But
I see. I think maybe you're saying maybe you're saying it's maybe even better to introduce like layer dependence in the sparsification and to sparsify the deeper layers less, and maybe that will help performance more.
I would have thought that the actual standard of comparison in terms of keeping the effective linear model number of linear model features fixed would require some sort of layer dependent sparsification scheme. But yeah, thanks.
Thanks.
Okay, so let me just suggest we take the rest of the questions offline just so we can more or less stay on time. So thanks again very much, Guy, for the very interesting talk. Sorry, I saw you had a question, Paulo, but maybe you can message Guy. I'm sure he'll be happy. Well, I assume he'll be happy to take the question. I can't be sure. So I think you should be able to share your screen, Suriya. Well, we see that you have started sharing your screen, but turns out that's different than you're sharing your screen. You're muted, Suriya.
So, sorry, was it not sharing my PowerPoint?
Okay, now it is. Now it's working.
Oh, was it sharing some other?
No, it just wasn't sharing anything.
Okay.
At least it wasn't for me. Maybe it was for others. No, yeah, it was just sharing a second ago.
I just made it full screen and then it stopped sharing.
Ah.
Okay, so let's try this. Can you see the full screen share mode or no?
I mean, we only see the non-full screen at the moment, or more precisely, like, we see the slides on the left that you could scroll through.
Okay. So that's what I was trying to do, but now?
Oh yeah, that's great.
The full screen mode?
Yeah.
So I
Yeah.
didn't drag first time.
Okay, excellent. I hope we're off to the races. Okay, so it's a pleasure for the third speaker in our symposium to have Suriya Gunasekar. So Suriya got her PhD in ECE from UT Austin in 2016. You should correct me if I get something wrong. I got this off your website. She was then a postdoc, I think technically a visiting assistant professor, or maybe a research assistant professor at TTIC in Chicago until 2019. And then since then, she's been a senior research scientist or senior researcher maybe at Microsoft Research. So it's, a really great pleasure to have her here, and we're looking forward to your talk.
Okay. So after 2 years in Zoom, and still don't know how to see everyone. So please feel free to stop me if you have a question. Please shout out, because I'm not able to put it in a configuration where I can see the entire gallery. Okay. So good afternoon, everyone. Thank you for inviting me to speak, and thank you all for also attending, and thanks to the organizers for organizing the summer school trip. So today I want to tell you about a broad overview of how to look at function space view of minimizing norm in overparameterized models in general, and specifically I'll give some specific results in the case of multi-channel linear convolution networks. But the first part of the talk, I'll try to pose it more in a broader context. And this work is, the most of the results I'll be presenting was driven by Meena Jagdishan, who's a postdoc was a grad student at UC Berkeley, but she's probably smart enough to be a postdoc already. And my colleague, Ilya Rajesh. Okay, so just to get the notations in the same page, so today we'll be talking about learning prediction functions where you have input X and labels Y, and the goal is to learn a prediction function which maps input to some representation of the labels. And we'll be looking at the candidate functions which are parameterized by tunable parameters will denote as W. So unless specified otherwise, W will probably denote the set of parameters like weights of the network which you're allowed to tune. And a standard method to do loss minimization is to learn such a prediction function would be to do some kind of empirical risk minimization over the loss over some observed data set of input label pairs. But today we'll be looking at primarily overparameterized regime, where the number of functional definition I'll be using is that the models are the candidate model class is large enough such that this loss function here has multiple minimizers. So there are many parameters, and as a consequence, there are many functions which perfectly fit the observed data, but most of it will perform poorly on unobserved data. So this characterization of overparameterized models is not something very new. In fact, for much of machine learning, we have been looking at other forms of regularization rather than just number of parameters as a metric for reducing the complexity. So you can think of the complexity of a class of functions as in terms of number of parameters or number of distinct functions you can realize with a network or with a function class. Or you can also think of the capacity in terms, you can also control the capacity by some other explicit forms of regularization, which is pretty popular in machine learning. And in particular, in deep learning in particular, weight norm based regularization is pretty ubiquitous, both in the form of explicit regularization, where L2 norm is pretty popular, and also in the form of implicit regularization, which is more of a prominent phenomenon in modern deep learning, wherein we don't explicitly constrain the models, but like the specific algorithms like gradient descent and stochastic gradient descent implicitly explore only a small subspace of the model class, and as a consequence lead to some form of implicit regularization. And a few of the earlier work kind of showed a connection between implicit regularization and minimizing L2 norm of parameters in some asymptotic settings. Although these works work in like some asymptotic setting, and there are other work which show that the implicit regularization is not always tied to minimizing L2 norm of the parameters. It is still a prominent form of implicit regularization to have an effect where you're minimizing L2 norm of the parameters. So it is kind of clear that L2 norm of minimizing L2 norm of parameters is a prominent form of like inductive bias used in modern learning. And even though it may not be the only one which is important, but it is still one of the prominent forms which is used in learning. And today we'll ask the question of what is the function space view of minimizing L2 norm of parameters. So a cartoon picture to keep in mind is as here. So script W is say, let's say the space of parameters, so the set of allowed parameters. And let's say if we put a simple constraint in the space of W, either implicitly or explicitly, saying that the L2 norm of the parameters cannot be larger than some value, then what does this constraint look like in the function space? So capital F maps every parameter to a function over inputs. And we want to understand what is minimizing L2 norm of weights is in the function space for different networks of interest. And you can clearly see that even if the function space is the same, if I have different parameterizations mapping from input to mapping from parameters to the function, we get like different constraint set in the function space. So specifically this question, the answer to this question will crucially depend upon the parameterization or architecture we use. And one way to capture this dependence is through the by looking at what is called the induced regularizer, which is essentially the representation cost of realizing a function in terms of L2 norm of weights. So R is a function, R is the regularizer defined over functions. And the way I define it is like of all the ways I can realize F using a network. Let's say we're thinking about neural networks, but it's in general, it applies to any parametric function class. Of all the ways you can realize F using a network, we pick what is the minimum L2 norm cost required among all such networks. And the reason this is used, like, so this is nothing but essentially a representation cost which is measured in terms of L2 norm of weights as opposed to number of parameters. And it's easy to see that, like, if we indeed have a minimum L2 norm solution, like if we look at the optimization problem of minimizing some loss with L2 norm regularization, L2 norm of weights regularization, this is equivalent to finding a function which minimizes the loss and with this induced regularizer. So at least in terms of global minimizers, these two are equivalent. Just a caveat that it is often impossible to solve this global minimizer of the L2 regularized problem. So this connection is subject to some caveats that if you just get to a stationary point of minimizing L2 norm or even a local minima, it is not clear that those are meaningful, that effect is meaningfully captured by R of F. But to begin with, like at least the global minimizers are captured by this induced regularizer. And subject to that caveat, this R of F plays an important role in understanding what is the nature of inductive bias when we constrain L2 norm of weights, either implicitly or explicitly. Okay, so this will be the broad question of interest, and as you can see, for different architectures or different parameterizations, we can now decouple the optimization problem. So assume that, like, subject to the caveats, if we play a little bit loosely in terms of what the optimization is doing, if we can separate the effects of explicit and implicit regularization from what is the function space inductive bias. So here it's saying that, like, let's say, for now, like, I'm willing to believe that in this architecture, gradient descent leads to minimizing L2 norm of parameters. Then what is the function space effect of minimizing the L2 norm of parameters? And often, even if this is not a strong theoretical connection between what gradient descent does to the function space view, looking into these questions can give us insights which can in turn be tested on tested experimentally on practical neural networks. Okay. So I'll give you some examples where such a this question has been looked at either directly or indirectly as a part of implicit regularization work. One interesting work we will build on later in today's talk is the connection between like looking at the induced regularizer in linear networks. So linear networks are essentially preserve the architectures of standard networks used in practice, but without the non-linearities. So in some sense, it's just a complicated way of writing a linear function. And here you can think of like two architectures of interest. One is fully connected network, where each of the layers are fully connected. There are L layers, and all of the intermediate connections are fully connected. And the second is a full convolutional network, wherein like each of the intermediate layer except the last layer is a convolution. There's a single channel convolution with where the kernel size is equal to input dimension size. It is not the standard practice to use full width convolutions, but this makes the analysis quite a bit simpler to consider full width convolutions. And even though these both networks represent the same function space, the function space, set of all functions realized by these networks is just all linear functions. And you can equivalently write it in terms of over a d-dimensional input, the all linear functions are denoted as beta and RD. So now for different parameterizations, we can ask what is this induced regularizer? And this induced regularizer turns out to be like very different depending upon the architecture, somewhat unsurprisingly at this point. So for fully connected networks, for example, we get like a minimum L2 norm. The induced regularizer is also minimizing L2 norm of the end-to-end linear function. Whereas for full width convolutional networks, you get a sparsity inducing penalty in the Fourier space. So the effective regularizer is you take the Fourier transform of the linear function, end-to-end linear function, and take a 2 by L norm. And 2 by L is here the depth. So for example, if for a 2-layer network, you get an L1 norm of Fourier transforms. And for L larger than 2, you get a non-convex regularizer, which is an LP norm for P less than 1. And as you can clearly see, these are very qualitatively very different types of inductive biases, and clearly the convolutional architecture captures something which is of interest for image type of signals or more natural signals, where we look for information in the frequency domain. Okay. So today's talk will build on like the convolutional part a bit more in detail and look at like different kernel sizes and channels. But just for completeness, a few other places where we have understood what this induced regularizer looks like is matrix factorization and infinite width 2-layer networks. For matrix factorization, this is essentially a formulation where the end-to-end function is essentially a matrix. And instead of writing the matrix as direct parameterization, you use a factorized parameterization. And in this case, if you don't have a bottleneck layer, it can be shown that the induced regularizer is a nuclear norm of the end-to-end matrix. And finally, for 2-layer infinite width networks, so these 2-layer infinite width networks can approximate any continuous function. And in this case, for in this case, for one-dimensional signals, so if d equal to 1 for scalar functions, the induced regularizer looks like an integral of a total variation distance of the second derivative. So in some sense, a smoothness kind of a penalty. And there has also been characterization of this for like larger, higher dimensional inputs in terms of Radon transforms. So these are some style of results we'll be looking at. But today's talk will focus on what does this induced regularizer look like for 2-layer convolutional network. But we'll look at the influence of number of channels and kernel size. We'll focus on the influence on number of channels and kernel size. So just to go a bit more detail about what the 2-layer networks are. So before I move on, there was just a broad overview of the kind of problem I was going for. If there are any questions, I can take it now, or I can just move on.
I mean, I just had a kind of very high level question, Suriya. You know, I understand the setup of the problem.
Mm-hmm.
Is there a way to at least heuristically guess what these implicit regularizers are in some case. Like, for example, if your L2 norm is like, has a very small regularization strength, and so to first order, to second order in that strength, like for example, for the infinite width ReLU networks, I've never read the proof of that theorem, but like I couldn't have necessarily guessed that it's exactly that norm, that gives you whatever the cubic splines are or whatever they're called.
Right.
But maybe in retrospect, there's a kind of simple, intuitive way to do these things. Like I'm trying to get the answer to your question, but I don't know how.
So I don't have an intuitive way. Like most of the time, I just like try to run some experiments, can give a bit of an idea. Like try to think of what I mean. For example, for convolutions, it would be interesting to run like some experiment in different wavelet or Fourier basis, and that kind of sometimes gives a bit of an idea, but I don't have a theoretically intuitive way to guess it. If that, unfortunately, I don't have a, so it's usually like, I mean, one way is you can try to write the KKT conditions of this problem itself, and that can sometimes give some structure, but most of the intuitions I get from like running some simple toy experiments early on. If that makes sense.
Yeah, fair enough. Thanks.
Okay. Okay. So the other point I wanted to make here is like, there's also like one high level point that even though we think of L2 norm regularization as a very vanilla regularization, we see that like these lead to very, very interesting, very special types of regularizers depending upon the architecture. So in some sense, the architecture or specific parameterizations can crucially influence what type of functions you are learning. And in particular, we can get some very non-RKHS behavior even with linear models. So even with linear models, we can get like a non-RKHS norm minimization purely by doing different parameterizations. Like all of, except for the L2 norm, of course, like both sparsity in the Fourier domain, nuclear norm cannot be realized by an RKHS no. And same thing with like the infinite width ReLU network, where this is like a total variation norm. I mean, it actually leads to, if you are thinking of interpolation while minimizing R of S, it leads to linear interpolation kind of a thing. And it's usually not easy to get, it's usually not possible to get linear interpolation with standard RKHS spaces. So yeah, that was a high level overview of it. And then now we'll look at something specific in terms of number of channels and kernel sizes. Although it posed this problem, like even understanding these for simple models is sometimes challenging, and usually like much of the understanding comes from a combination of theory and experiments. And we'll see some aspects of this even in today's talk. Okay, so we'll look at what a simple linear convolutional network looks like. So you have your input, which is denoted as X, and then you have a filter, like this is just a two-layer network. So you have a convolution filters. I'm going to denote the first layer convolution filter as U. So you convolve it with U. For simplicity, I'm going to use like, circular convolution. But I think experimentally, like there are some edge effects for zero padding as opposed to circular padding, but qualitative statements still hold. Okay. And the second layer is just a simple linear layer. So your end-to-end network proceeds as you convolve with U and then take an inner product with V. And this entire thing, since there is no nonlinearity, can be represented as the entire end-to-end function can be represented as a linear model, which is denoted as beta UV. Right. So in the end-to-end function, you can realize any linear model in RE, and the beta UV can, I mean, with a little bit of algebra, can be shown to be just U convolved with V with a reversing of order. So the down arrow essentially means that you just reverse permute the coordinates to be in the reverse order. For the purpose of this, I mean, this is more important to be rigorous quantitatively. For the purpose of this talk, you can just ignore the down arrows. I mean, they need to be taken care of, but they're not pretty painful. Okay, so then the question of what the induced regularizer is simply info over all the ways I can generate beta as a convolution of U and V. Among all the ways, I picked the one with like minimum L2 norm and of U and V, and the minimum L2 and norm of U and V is my induced regularizer. And like I said before, you can, even for k equal to 1, which is like the smallest k you can get, you can realize all linear functions, because for k equal to 1, it's just a one scalar quantity, it's a one scalar convolution, and you just, if, for example, if you take u to be 1, then like v can take care of all linear functions. So it's clear that every linear function can be represented by this network, even for k, smallest value of k. Right? And so to understand the answers better, like we'll look at the Fourier space, in which the network becomes much simpler. So, and if you look at the same network in the discrete Fourier domain, so for each of these quantities, we take a Fourier transform where for any variable z, a z hat would essentially represent a d-dimensional Fourier transform with respect to d. So if you're not familiar with Fourier transforms, think of it as an invertible univariate matrix, which is essentially change of basis. So FD is essentially a unitary matrix in complex space. So z hat is essentially just a change of basis of z. And the property of convolution which comes to aid is that a convolution can be written as an element-wise product in the Fourier space with some conjugation. Again, like you can, for the first approximation of this talk, you can ignore the conjugation. They need to be taken care of to be precise, but it doesn't create any complication. So the star represents here the conjugation for complex numbers. Okay, so in the Fourier domain, like now beta hat becomes a very simple function of just like element-wise product of u hat and v hat. And now we can think of what Rk of beta is. So if u is unconstrained, if u could be any value in Rd, then u hat is in some sense unconstrained because F is just an invertible matrix. And now you can think of what Rd of beta is very easily, because you're essentially, you have to write beta hat as a multiplication of u hat and v hat. And you can get L1 norm simply by setting u hat and v hat to be square root of beta hat while capturing the signs in one of the two vectors. And it is easy to see from this and a little bit of algebra that you can, when u is completely unconstrained, you will get like L1 norm of beta hat as like the induced regularizer. And again, this essentially forms by, you can get an upper bound in terms of L1 norm by using AMGM inequality. And you can match that upper bound, sorry, you can get a lower bound and you can match the lower bound by setting u hat and v hat to be square root of beta hat. Right? But this argument breaks when k is not equal to d, when like the u cannot be any full dimensional matrix, but u is restricted to be in some k dimensional space. So if you take a u which has only k coordinates and take a d-dimensional Fourier transform, it's a vector in d dimension, but it has only k independent parameters. So in some sense, u has a restriction. And in particular, the extreme case when k equal to 1, u hat has to be like, you cannot set u hat to be beta hat, because u hat will also always be of the form some scalar multiplied by all ones vector. And here you can clearly see that you cannot get minimum L1 norm. In fact, like because u hat is all ones vector, in order to satisfy the constraint, we need v hat to be exactly equal to beta hat. And the only thing we can change is like the norms of u hat and v hat. And if you actually like compute what the answer comes out to be is like if you have k equal to 1, you go back to getting L2 norm of beta hat as your induced bias, as opposed to L1 of Fourier transform of beta, which is kind of surprising because both cases it's a convolutional network, but simply by changing the kernel sizes, you go between something which is simply an L2 norm, which is basis independent. It doesn't care about Fourier basis or like wavelet, any other basis, to something very specific to a special kind of basis, which is the Fourier domain in the case of k equal to d. And here is an illustration in an MNIST example. So like I said in the beginning, this way of separating the representation cost from gradient descent kind of it is subject to some caveats, but we can experimentally see that like if we take a simple MNIST data experiment, and then we run like essentially a gradient descent over a separable data set, linearly separable data set, subset of MNIST. In fact, most of MNIST can be linearly separable pretty easily. But if we do it on a subset of MNIST, when k equal to 1, you get, the pictures here on the left are like the signal space view, and k equal to 1 is in the top and k equal to d is in the bottom. And the right are Fourier space views. So if you, for k equal to 1, you can see that it kind of, and this is a binary classification problem of classifying 0 versus 1. For k equal to 1, it's kind of finding a minimum L2 norm solution. So it's setting most of the outside pictures, most of the corners to be 0, whereas there is no structure in the Fourier space. On the other hand, for k equal to d, you get like this kind of a repeated patterns of 1s, and you get very good sparsity in the Fourier space. And when I first looked at these things, it looked like the first one is in fact more interpretable. But if you think about the problem domain, like you want some sort of like translation invariance. So having a sparsity in the Fourier domain is somewhat related to translation invariance. It's not exactly, because it only captures like translation after some periodic translations, but in this at least has a little bit more scope of being translation invariant than the first one. And so these are the two extremes for k equal to 1 and 2, and then one can hope that like for different k's, you can also get closed form solution which kind of interpolate between the two cases. And unfortunately, to get it is we found that it is kind of intractable to get any form of analytical solution, because even for k equals to 2, like the final solution looks like some form of weighted averaging of the Fourier space. So weighted averaging of Fourier space coordinates. So it's like, so you beta hat j is like the jth coordinate in the Fourier space, and you have a weighted averaging of them. But the weights themselves are much more complicated to compute in a closed form way. On the other hand, like it also shows that the weighted averaging shows that you kind of have some kind of a grouping in the Fourier space, wherein we can show that the nearby weights are much closer to each other than, for nearby frequencies, the weights are much closer to each other than the faraway frequencies. So although we were not able to get a closed form solution for general k, like at a later point, I'll explain a general theorem which shows that for any k, this Rk of beta is indeed a norm, and it is in some form an interpolation between L2 and L1 norm in the Fourier space. And here is also a more empirical demonstration of the same phenomenon, where it's a similar picture to as previous, but from going from left to down, top left, top down, sorry, bottom left, top right, and bottom right, it's increasing k from 1 to 5 to 16 to 28. And even for small case, this is even for small case, you get like quite a bit of sparsity in the frequency domain. You don't have to go all the way to 28. For small case, you again get quite a bit of sparsity, and as we expected, we also get some kind of a grouping in the frequency domain. So when things are not sparse, they are kind of grouped together in locations. And so empirically, we do see that the group sparsity effect, which we show theoretically, which we kind of argue theoretically also holds. Okay, so now we wanted to see if we can say something more quantitative about like when do we get like so even if we cannot get closed form solutions, can we get can I tell you when you are closer to minimizing L2 norm versus minimizing L1 norm, and is there really an interpolation and so on. And for this, we looked at one of the tools we use is looking at the SDP relaxation. So this tool we thought is of independent interest. That's why I would also like to spend a few minutes on this. Okay. Okay. So if you look at the both, if we take two-layer networks, especially two-layer convolution networks, this can also be generalized to other two-layer networks, and look at what the objective and constraints are. They both can be written as, at least for linear models, can be written as some linear functions of this lifted matrix W, which is written as U, V, and U transpose, V transpose. If you take U and V and then construct this matrix W, both the objective and the constraints can be written as linear functions of this W matrix. And as a consequence, you can write Rk of beta as essentially something which looks like an SDP. So SDP is a mid-definite program where both So both the objective and the constraints are linear functions of some matrix, positive semi-definite matrix W. It looks nearly like an SDP, but we also have a constraint that W has to be written as U times like a product of rank 1 matrices. So it's an SDP with a rank constraint. This naturally leads to an SDP relaxation as an approximation, where you can upper bound this by just dropping the rank constraint. And once we drop the rank constraint, you get this nice SDP, which is a convex program, and we can compute it at least and visualize it and so on, right? And another advantage of this SDP formulation, so it is an upper bound which can lead us to quantitatively like reason about the problem a bit more. On the other hand, it was also an easy generalization to multi-channel problems. So I won't go into too much detail, but a multi-channel version of convolution is like as depicted in the picture on the right. So you do the same convolution, but like repeat it multiple times. On the first layer, you repeat multiple times. Your input is still one channel, but the output is multiple channels. And then the final layer takes a linear combination of all the output channels. And in this case, your beta hat is still remains a linear function because there is no non-linearity. It can be written as diagonal values of U hat, V hat transpose. So now you have a matrix for each output channel. You have a k-dimensional kernel. So your parameter space for first layer is a matrix, and same thing with the second layer. And you can write beta hat in terms of like the Fourier transform of these matrices, where the Fourier transform of a matrix is taken per column. Okay, and if we look at a similar SDP formulation for general number of output channels, it again looks like a Fourier transform, but with a different rank constraint. So you can show that the rank constraint is exactly equivalent to Cout. So if you look at, take a multi-channel output, look at the representation cost that can be represented by a similar trick as for one channel, you can write it as a SDP with a rank constraint. And again, like if you drop the rank constraint, we get an SDP relaxation, which is always an upper bound. Now, already we see that, like even just from this one slide, we see that once Cout becomes larger than the size of W. So W is a matrix in D plus K dimensions. Once Cout becomes larger than D plus K, there is no dependence of the, like increasing Cout beyond that doesn't give us any advantage in terms of representation cost. So let's say we are looking at 3-dimensional kernel in like 32 by 32 dimensional space. So once Cout becomes larger than some value, like the width becomes larger than some large enough value, there is no dependence of the representation cost on the Cout. In some sense, like the inductive bias doesn't depend upon how much more Cout you add. So this is for large enough Cout, and actually with a little bit more trick, you can actually show that once Cout even becomes larger than the kernel size, it doesn't matter with some simple tricks. But the key proof in our paper, we also show that for 2-layer networks, even having Cout greater than 1 is enough. So as long as, whatever be the number of output channels, the induced regularizer is completely independent of output channels. So this is not for some large enough Cout, but for any Cout. And as a consequence, we can say that like for any number of output channels, we can see what is the end cases. And for any number of output channels, it's also the induced regularizer is also a norm because it can always be represented by an SDP, which is a convex program. And it's a norm which interpolates between the two extreme cases of L2 norm of beta and L1 norm of beta hat. And with this SDP relaxation, we can now also like give quantitative bounds like the style I asked about, like when is it closer to L2 norm? So we say that when K is like, what is an approximation to L2 norm? We can get an approximation to L2 norm in terms of K. And similarly, we can also get an approximation to L1 norm. So when K is like very close to D, it doesn't have to be exactly D, you get within a factor of D by K times the L1 norm, whereas when it's very close to 1, it's much more closer to the L2 norm, and we can exactly quantify these bounds. And a brief comment on the proof is, like I said, it's just looking at the KKT conditions, it shows that it's easy to show that all the solutions of the SDP will be of rank K. So once C out is greater than K, C out is the number of output channels and K is the kernel size. Once C out is greater than K, you're not gaining any more in the representation cost. But showing that once C out is greater than 1, it's completely independent of C out is much more trickier. And the way we show it is by showing that for given any SDP solution, which is always a lower bound, we can construct a rank 1 version which has the same objective and satisfies the constraint. And that essentially is like the key technical content of the proof. Okay, so this gives us a kind of a testable hypothesis we are saying that for any kernel size, if I had only 2 layers and my input channel doesn't have multiple layers, it doesn't make sense to have more number of output channels. And this is in some sense counterintuitive to what we actually see in practice, because increasing the width even in convolutional networks usually helps with generalization. But so in some sense, this result is telling us that if we don't, but sorry. I was also going to say that the increasing the width also increases the generalization, usually for convolution networks when we have strides and pooling. And so in some sense, this result is pointing out the shortcoming that if you want to explain the benefit of width in convolutions, we might have to look at the strides in more detail as opposed to like just general convolutions. Or it's also possible that this is a phenomenon which is observed only in linear networks, but not in nonlinear networks. On the other hand, we can also test this whether this phenomenon translates to nonlinear network. So we can form a testable hypothesis whether for 2-layer networks, if I add nonlinearity, does the representation cost increase? First, without nonlinearity, we do see this empirically too. When without nonlinearity, we can, for different values of K, we can look at K and C. C is the number of output channels again. For different values of K and C, we can look at what is the learned predictor by gradient descent. This is again an MNIST 01 classification problem. And we see that the output doesn't change with, like, visually doesn't change with number of output channels. So the learned function doesn't change with the number of output channels. So these set of features are for K equals C equals 1 output channel. This is for 2 output channels. These are for 4 output channels, and so on. And you can also quantify it where we compute what the L2 norm of all the weights are. So even if for C equal to 1 versus 8, we have added 7 extra channels, but we see that after training, the L2 norm of the learned predictors, L2 norm of the weights of the learned network is kind of invariant to the number of channels. And so these are for like linear networks, but surprisingly, we also observe, so this is for linear networks. Surprisingly, we also observe the similar phenomenon for nonlinear networks where we add really nonlinearity between the first layer and the second layer. So this in some sense says that it's not, the shortcoming is not from looking at linear models, but it is potentially from like not looking at max pooling or strides, which are used commonly in convolution. The other aspect of our proof, which I didn't touch upon, is like what happens for multi-channel if the input itself has multiple channels. Because it is also, if you think of most architectures in neural networks, like the number of output channels is typically matches the input channels after the first layer, unless you have some kind of downstride. Usually you downsample and then increase the width. Every time you downsample is when you increase the width. This is partially done to maintain the number of parameters, but our theory can also kind of shed a light in it, in the sense that we show for we extend the analysis also for multi-input channel networks. And here is the answers are a little bit different, but in the interest of time, I'll just briefly say that in terms of multi-channel networks, we show that a similar phenomenon where the number of output channels stops mattering once it's larger than the input channel size. So this kind of is partly explaining why we normally, when we are maintaining the size of, when we're not downsampling, we kind of maintain the size of output channel to match the input channel size. and this is some theoretical justification in a much simpler linear model, but it seems to align with practice too. And to summarize, like we studied a broader problem of interest in a very special case of two-layer linear networks. And even though two-layer linear convolutions are like very limiting in terms of theory, we find that like the insights from the theory can actually be tested for nonlinear networks in practice. And they point out like some interesting phenomenon in terms of how number of channels influence the learn predictors, and where what are the shortcomings in understanding the benefit of width comes from. And in this case, it's pointing to the fact that we are not doing any downsampling, and probably increasing the width helps usually when we also downsample or do a dilated convolution, etc. So thank you for your attention, and sorry, I might have gone over a bit of time. Sorry.
No, you're exactly on time, in fact.
Okay, but I didn't leave any time for questions. Sorry about that.
Yeah, that's true. I mean, maybe what I can suggest is that David can share his screen, but if people have questions, maybe you don't mind if they just reach out to you directly, either by email or something. Right. I think this whole line of work about implicit regularization and what's going on when you switch to a function space instead of parameter space is like actually quite interesting, but still somehow like surprisingly difficult to say something very general about. We can take these models and sometimes write down these specific answers, which are always kind of interesting, but then it's like for the next model, oh my god.
Right.
So,
but the good thing is, I think this is probably one way to bring in data into consideration, because now the architecture and the data will be related. Usually with most of the theory of deep learning, we say something general and we never consider the structure in the data. And usually like a specific architecture works for a specific type of data. And this is potentially one venue to look deeply into one type of architectures and understand how the data brings into point of view. And
yeah, I think that's a good point.
I think it may not be a bad thing if it's not like applicable to all networks, but if we can say all transformers or all convolutions, that would already make a pretty good headway.
Yeah, for sure. Thanks again, Suriya.
Thank you.
Tell me if this works.
Yep, we can
Are you
see it.
You're saying on the screen?
Yep.
Cool.
Amazing. It works beautifully, it seems. Okay, so we are very happy to have David Schwab here for the last lecture of the last symposium of the summer school. So just for some background, David got his PhD in physics from UCLA in 2009. You should correct me if I got this wrong. I think I got all this right.
Yeah, you got it.
He was then a postdoc at Princeton in physics. And then was an assistant professor at Northwestern, also in physics. And now is an assistant professor, maybe associate professor, now associate, I see that on your slide, very good, at the Graduate Center at CUNY. And so David is someone that, again, I've talked to over the last couple of years, and he comes from a kind of, biophysics background, information theory background, and like, always a new perspective. So I think we're about to learn something we haven't really heard almost anything about in the summer school at all. So that's exciting.
Awesome. Yeah, thank you, Boris, for the invitation and the kind introduction, and you all for sticking around till the end. I sort of took the charge to mean a bit more leaning towards the tutorial end than like a research seminar, assuming that you all didn't have like that much background in information bottleneck and information theory. So keep that in mind. Nonetheless, I've certainly erred on the side of including my own work much more than other people's, than if I were doing truly an overview of this field. So here's a brief outline of what I'll be telling you. First of all, what is the information bottleneck? It's something that you might have heard a bit about here and there. It has sort of a niche representation at conferences like NeurIPS. but I'll assume that you know something of some basics about information theory, but not about the information bottleneck. Then I'll talk about how it could potentially be applied to machine learning problems, which are in some sense somewhat different from the original problems for which it was formulated. And then I'll end with sort of asking whether the information bottleneck is the right objective function for machine learning, or maybe there are other objective functions that better capture what we'd like to do. Let me also emphasize, I super encourage questions throughout. Interrupt me. Don't wait till the end if something's confusing. Let me know. Okay, so what is the information bottleneck? At a very high level, the idea is you have some joint distribution of input data and targets, and your goal is to find a compression of the input data in such a way that you retain predictive power with that compressed representation to predict the targets of interest. So the objective function that was initially written down by Tali Tishby and collaborators 20 years ago said, what you should do is you should minimize the mutual information that your representation has about the input data. But you should also maximize the information that you have about the targets, and nobody can tell you how much you should care about minimizing the input information versus maximizing the output. So put in a trade-off parameter, beta, and then in principle you can solve this objective function for some encoding distribution. And if you do that for different values of beta, in this information plane, which is the information about the input versus information about the target, you trace out some curve parameterized by beta, and reasonable people could disagree about where you should sit on this curve, but certainly, although you could live anywhere in this bulk for different encoders, there's no good reason to be in the bulk. You should be somewhere on this boundary, and anything up here is disallowed. So that's the goal, is to find this sort of like optimal encoding of your data. A little bit more detail on, like, in principle how you do that. So you need to be given a joint distribution. So let me emphasize that. You're in at least in the sort of vanilla version, you're not given samples. You're given a joint distribution of on X and Y, and you want to optimize this objective function subject to a sort of Markov constraint where your encoding only talks to Y through X. And you can solve this, at least formally, with variational calculus, and you end up with a solution that looks something like this, where you have your encoder written in terms of a marginal on the latence, or on the encoding, and on the conditional of the targets given the encoding. But both of those distributions depend on the encoder itself. So you need to solve these equations sort of self-consistently. So you iterate them until convergence. And this is called Blahu-Gur-Ari-Modo, and you can show that this will eventually converge to something, but you're not guaranteed that it'll be a global minimum of the objective. It may be local. And actually, one thing I wanted to mention here, just go back to this picture. In the information theory world, the encoding variable is usually written as T. In machine learning, it's Z. And I'm going to go back and forth between the two to train you up to not get confused, not because I'm lazy, I roll. Moreover, the objective function in machine learning is often written as the minus of this and a maximization, which shouldn't confuse you, except that the beta is on the other term, so beta becomes 1 over beta often. And again, I will train you up to not get confused. Okay, so you may have heard about the information bottleneck because a couple of years ago, Tali Tishby, one of the inventors of the information bottleneck, had suggested that neural networks trained via SGD naturally solve an information bottleneck objective. So if you think about some particular layer in your neural network and call that your encoding layer, then he suggested that that SGD finds you a representation that minimizes the information about the inputs while maximizing the information about the targets. And the two claims, or two of the claims that he made, were that this sort of reveals two phases of learning, a sort of memorization and a forgetting phase, where if you plot the learning dynamics in this information plane, you see that there's a first phase where the information about the input is going up and the information about the targets are going up. And then there's a second phase where the information about the inputs starts decreasing, but nonetheless, the information about the targets continues to increase. By the way, can you see my cursor? I think the answer is yes, but just to make sure.
Yes.
Cool. So that was one of the claims. Another one is that if you look at different layers in the neural network and you plot where at the end of training where they land, they sort of sit on the sort of optimal boundary at different locations corresponding to particular values of the trade-off parameter beta. Let me emphasize that everything I've put on this slide has a question mark after it. This was very controversial, and you can find lots of interesting discussions on the open review of this paper and blog posts and all sorts of things. So I'm going to leave this here. My interest in this talk is more about how can we use the information bottleneck as an objective for training machine learning models, as opposed to whether neural networks trained via SGD naturally solve the information bottleneck problem. So I'd like to move towards how can we use the information bottleneck in practice, and this is a problem because solving it is hard in general. I mentioned that even if you did have the full joint distribution of data, the iterative solution doesn't necessarily converge to the global optimum. It's very expensive, and so people have developed or people have solved special cases like a case where X and Y are jointly Gaussian that have been quite useful. You can solve analytically, but even then, like, the solution is more complicated than you might think. So the first question is, can we make progress on the general information bottleneck problem without making certain assumptions on the data, like it being Gaussian? And the answer is yes. At least you could say something perturbatively near the onset of learning. So near this part of the curve where you have very little information retained and very little predictive information, but you sort of have the maximum like bang for your buck. And so this is a paper that my postdoc Wave wrote, you can find in the archive. It's also under review at NeurIPS, where he developed a perturbative solution for the information bottleneck objective, where you can exactly construct the critical beta at which learning starts to take off. Is for beta too small, you won't get you'll get a trivial solution of mapping to zero, but at some critical beta you'll start to get something, and the slope of this curve is 1/beta, so you can sort of compute the slope of this curve at the onset of learning exactly, and moreover, you can compute how these informations as a function of beta rise linearly from zero. So this is nice for getting a lot of information about what's going on near the onset of learning, but it's sort of limited to that regime. So
can I ask a question?
Yeah.
So it might be hopelessly mathematical as a question, but is it true that for every beta, a minimizer exists?
So
like of course an approximate minimizer will exist, but like, is it clear that like in principle there's something you can write down?
So if beta in this case, if beta is too small, then you will have a minimizer, but it'll be trivial that you just map everything to one point. So there is a sort of phase
right,
where,
but like for arbitrary beta, do we know? Is there like at least fixed point?
I just lost the sound. I'm not sure if
Sorry,
other people did as well.
Can you hear me?
Yeah, I can hear you now.
Oh, it might have been my fault. I was just wondering for general beta. Like I understand what you're saying, that maybe in this perturbative regime you can just write it down. At least like for beta small, it's trivial, and maybe for beta slightly bigger, you can still track it somehow.
So you're asking, is there a global optimum always?
Yeah.
For any value of beta? I guess I haven't thought about that question. Is there a reason that you're worried about this?
Well, I mean, like lots of spaces that you're optimizing over, like the space of probability measures is like not compact. So it could be that like you have a sequence of things that goes off to infinity that does better and better, but there's just nothing that actually is minimum, like minimizing cross entropy loss or something.
Right. Yeah, I don't know the answer.
Yeah, fair enough.
Sure. Okay, so this only gives you information sort of near the onset of learning. A paper that has been incredibly influential from some number of years ago, from Alex Alemi and collaborators at Google, said, trying to solve these iterative equations is difficult for a number of reasons. One reason that they're difficult is this marginal here, for example, requires a sum or integral of your data, as does this one here, and that's just going to be intractable for large data sets. So what we can do instead is, once again, replace the that marginal and the decoder of y given z with some variational approximation, and then you'll get an objective function that looks something like this. That you can also, first of all, you can estimate from samples. So you can just put in your joint distribution of x and y as your samples from the data, and moreover, this L is a lower bound to the objective function that you're trying to maximize. So here now, because it's machine learning, we switch to maximization and Z's. And so it makes sense to maximize this objective function with respect to both the encoder as well as the variational approximations to the decoder and perhaps the marginal as well, if you want. And so you might recognize this objective as being sort of like pretty similar to like a variational autoencoder, except that when you map your input data to your latents, and then you map your latents to targets, you're not mapping back to your input space, you're mapping to the targets. And second of all, there's a beta here, so there, people do study beta VAEs, but in that case, the beta that you put in is a little bit sort of ad hoc, where you had this elbow and you threw a beta in, whereas here it sort of naturally emerges from the IB objective. This turns out to be quite useful as a regularizer when training models, and especially for adversarial robustness. So I would say this is probably the approach that has been most fruitful for trying to use information bottleneck as an objective function for training neural networks. So now I want to turn a bit to rethinking the IB objective and asking, like, is that sort of obviously the right objective, or are there other kinds of things that we might want to study instead? And the first is an old paper that DJ Strauss, who's now at Google DeepMind, wrote, and the idea here was to say the original IB objective penalizes your representation and encourages compression via minimizing this mutual information between the inputs and the targets, or sorry, the inputs and the representation. And that kind of makes sense if you were doing something like channel coding, where you imagine that there was a channel between your inputs and your compression, and you wanted to minimize the size of that channel. However, if what you really care about is compression, then and you don't really care about a channel, then instead of charging you for how many bits of information you send, maybe you should just be charged for how big your representation is, and you might want to measure that via the entropy. And if you look at the difference between these two objectives, the difference is minus the noise entropy of the compression given the inputs. And what that means essentially is that, at least relative to this objective, the original IB objective is really encouraging the encoding to be stochastic. It's really asking you to add noise, which, if compression is what you want, it's not obvious that you want to add noise. So we thought we would study this problem instead. It turns out that in practice, what you do is you keep the noise entropy term in with a coefficient in front. You solve it for the general coefficient, then you send that coefficient to 0 to get your solution. But essentially, you can solve this problem. And when you do that, indeed, you find that the solution, in the information bottleneck case, gives you this stochastic encoder. But when you solve this other objective function, you end up with a deterministic function where your encoding is just a function of the inputs. And so the D for this DIV stands for deterministic. And I want to emphasize here that, like, other work had tried to take the information bottleneck and sort of force it to be deterministic. Whereas here we wrote down an objective function where the deterministic encoding sort of naturally emerges instead of us forcing it in some sense.
Sorry,
yeah,
David, I don't think I've been trained up enough. So in this one, you're trying to minimize LDIB?
Yeah, here we're trying to minimize LDIB instead of this L here. Right,
I see. So minimizing H of T is like making it deterministic.
So it's more that, yeah, in some sense, because
like if I only look at that, I mean.
Yeah, if you had noise in your encoding, that would just be adding entropy in some sense to your
exactly.
and not benefiting you in any way. So you shouldn't have it.
Okay, I see.
Yeah.
So but what's the use of such a deterministic encoding? The point is that somehow, like, this is the best deterministic encoding. Like, you didn't want it to be a priori deterministic, but it just turns out that in this sense, the best one is deterministic. Maybe you can even calculate it sometimes or something like that.
Right. Yeah, and in the case of at least in principle here, now you're searching over the space of functions and the space instead of the space of conditional distributions, so it's a little bit smaller of a space perhaps. So you might be able to, this might converge faster. And just in general, if it makes sense to you that what you want is to minimize the entropy of your representation, then this is what you get.
So then is it true that, like, if I had some candidate T, I could like always do better by replacing it by its like expectation given X or something like that? Like, is that how I should think about it?
You had some candidate like encoding that was stochastic?
Yeah, like I'm trying to understand why this thing would be exactly minimized on a deterministic one. Like, I understand if I didn't have the second term, but of course the second term is there.
Right. Well, I guess so adding noise, starting deterministic and then adding noise is just going to potentially increase your entropy, but it's not going to increase your information, right? If anything, it's just going to decrease it. that make sense?
Yeah, actually, it does make sense. Thanks.
Maybe the sort of toy experiment on the next slide will also help. So here's a toy problem just to illustrate the differences between these two. And on the left, we plotted the IB in blue and the DIB in green solutions in the information bottleneck plane, where the x-axis is information, and on the right it's the same solutions, but now in the DIB plane, where the x-axis is entropy. And in this case, what you find is that they both perform basically the same in terms of IB's objective, but in the DIB plane they're very different. And you know, where DIB sort of like tunes how much entropy it uses, IB is just like using the most entropy it can possibly use always, because it's not penalized for it. And you know, one explanation for why it's finding these solutions instead of these is that, you know, if you want to have, for example, no input information, you could either do that by having you know, the marginal and the conditional entropies be zero, or you could just have them be equal and non-zero. And it's just so much easier to find a solution like this. There's just so many more solutions like this. So you know, it's just much more likely to find that one. So IB is sort of being very, very sloppy and using all of its capacity all the time, and just changing the degree of noise to dial up and down the information.
So can you get some of these like actual original IB solutions by like adding a constraint, like doing it perturbatively in the entropy of T? Like you say, I also want H of T to be epsilon at most. And then maybe you could do it by perturbing your DIB solution or something, you know, because you said it for other beta, for general beta, it's like hard to solve directly. So maybe you could like start to get some feeling for it this way.
Perhaps. So that's I mentioned when you solve this, you know, analytically in quotes, you know, you add a parameter here and then send that to 0. But if you keep it non-zero, then it's kind of like mixing these two objective functions, and you're saying you might want to study the solution like perturbatively as a function of that parameter instead of sending it just to 0. So
oh yeah, I didn't understand, but yeah, like, you know, somehow around the thing you know how to calculate, like, you know, maybe that gives you a little bit more information.
Right. Yeah, you can do that. Another thing you can do is if you initialize the model differently, then IB will find different solutions. It's you know, it's finding different local minima all the time, and depending on how you initialize it, it will have a different character. So if you initialize them with very low entropy solutions, then you can actually even with just IB, you can make it look a little bit more like DIB.
I see.
The other thing I wanted to mention, just as an aside, is that you can use this DIB to do clustering, where the deterministic function is now a cluster assignment, and the target information is preserving information about the position of the points. And when you do this, what you find is that the curve that you get has these kinks in it, and the kinks sort of correspond to regions of beta where the solution doesn't change. So in some sense, like the sharper the kink, the more like robust that is. So you can sort of use that as a model selection signature to say like, oh, like I really think that, you know, that there's this many clusters or something like that. But this is just an aside if you're interested. Here's a paper. The main thing I wanted to talk about with regards to changing the objective function, and the thing I'm most excited about is another paper that I wrote called DIB, but D now stands for decodable instead of deterministic. And the idea here is if we think about training a neural network, and we treat the you know, encoding or compressed representation as, you know, think like the penultimate layer in your network. The information bottleneck objective, again, says that you should maximize the mutual information that you have about the targets while minimizing the mutual information that this penultimate layer has about the inputs. And if we think about this target information for a minute, another way to write that target information is as related to a minimization over all possible decoders from that representation, making target predictions and looking at that cross entropy. So you get to choose all possible decoders to really characterize that mutual information. But if I tell you, or if you know that your model has a linear layer and that's it, you might be you might be overestimating your ability to really understand these targets, because your linear layer might not do a very good job. So what you should instead do is restrict this minimization to be over the function family that you know is coming. And then if you do that, you get something that is called V information. And I should have a reference here to a paper by Stefan Ramon from last year or so that introduced this. I should also have a reference to our paper. It was spotlighted in the RIPS last year. So it sort of makes sense if you want to do something like have an information bottleneck objective for training a neural network, that you should instead use this V information in place of mutual information up here. So that seems like a good idea. For this sufficiency information, let's replace it with this V information. For this minimality, let's replace it with this V information. The only problem is here I've only talked about making predictions from the representational space to the target space using the function family that you know is coming. But how do you make sense of the input information or the minimality information when this function family doesn't make predictions in that same space, right? It's making predictions in 10 classes if it's CFAR10, and these are images. So what do you do? And what we came up with, which we call V minimality, is a little bit easier to explain with the picture here on the right. So the objective function that we have is a sort of multi-headed objective where you have your encoder that takes you into some layer, and from there you have a bunch of heads that come off, and one is like the main head, and that gets like the real labels, and it's trying to predict cat, dog, and so on. And then you have a bunch of negative heads, and what those get instead is, say, the first one gets all of the dog samples, but it gets random labelings, and it tries to do its darndest to predict those dog labelings, those random labelings on all those dog images. Maybe the second negative head gets all the cats, and with a random labeling here, and it tries to memorize those random labels there. And the objective function tries to find a representation such that the main head succeeds and the other heads fail. And in practice, you can do that by reversing gradients, and it's a sort of minimax objective. It's involved to get this to work in practice, but I hope the idea kind of makes sense. And what that's trying to do, schematically, if you imagine the Z space to be the plane, and you imagine the function family that you're using to predict to be vertical lines for your decision boundary, then being sort of V sufficient means that your cats and your dogs are separated horizontally, so a vertical line can separate those classes. And being V minimal means that your dogs are all stacked vertically on top of each other, so the dog with the glasses isn't laterally separated from the one with the bow tie, so you can't separate them. In contrast, if you ask to be truly minimal by minimizing the mutual information, then you would need all of the dogs to collapse to a point, as opposed to sort of just being stacked vertically. And so this objective allows for a lot of extra slack that mutual information doesn't allow for, that perhaps makes it easier to optimize. And you certainly pay no cost in having this vertical spread, because your decoder can't distinguish it anyway. So that's the idea for training with this DIB objective. So how does it perform? First of all, if you use it as a regularizer, where you basically have a model like this, and you have some beta that is a hyperparameter that tells you how much you care about making these heads unhappy, you find that it performs pretty well, on a par with other regularizers. I wouldn't say that it really excels, and I wouldn't say everyone should run out and start using this, but it works pretty well. Another way to test this is actually, there are two experiments that are done here. So first, we were interested in whether this allows for sort of robust representation learning, such that you do a stage of training with this DIB objective, and then you freeze the encoding, and then you give that to someone else, and then they learn a model via just ERM from that representation, and you would like them to be sort of guaranteed to generalize well. So what we did is that first stage of representation learning with the DIB objective, and then looked for like the worst performing ERM that you could get from that representation. And we did this by adding to the training set test examples, but with randomized labels. This is like a trick that comes from Tom Goldstein, I think. And what you find is in these dashed lines, that as you increase during the representation learning phase, as you increase the degree of V minimality that you enforce, you go from having models you go from having representations from which you may generalize terribly to representations that even in the worst case, you can't generalize badly. So you can sort of like enforce good generalization downstream. Secondly, here we superimposed on the CIFAR-10 images MNIST digits, and we ignored them during the representation learning phase. The DIB objective with these heads was all with respect to CIFAR-10 labels, but then from that frozen representation, we asked, if I train a decoder from that representation, can I read out MNIST digits? And what you find is that as the representation learning has a stronger degree of V minimality enforced, it gets increasingly difficult to read out those MNIST digits. So it's sort of removing irrelevant information. We didn't ask specifically for MNIST to be removed. We just asked for anything that wasn't useful for predicting the CIFAR classes to be removed. And that indeed made it more difficult to read out the MNIST digits. Finally, what we decided to check is whether this V minimality, which is sort of how well can these negative heads succeed at memorizing random labels from a representation. We want to see whether that degree of V minimality was useful as a probe for predicting generalization of models trained via just standard SGD, or someone hands you a model. And for that, we compared to the results from the Fantastic Generalization Measures paper, if you know it, and found that our V minimality probe worked as well or better than the best performing predictors from that paper. So this is encouraging that in addition to being used as an objective to train with, it could be useful for understanding when models will generalize and when they won't. So I'm now at the end. So just to summarize, I introduced to you the information bottleneck as a way of formalizing compression with relevance. I mentioned that it's hard to solve in general, but there are various approximations, variational and perturbative, that can make it tractable. And then I talked about variants of the objective that, at least from my perspective, are more appropriate for machine learning tasks than the original IB objective. So I think we have a few minutes for discussion and questions.
Right. Okay. So before that, let's just thank David again. I think that's quite cool. I don't know much about the information bottleneck, but I now know more. Although I still don't know if there's always a minimizer. But okay, maybe that's for later. Oh, I see Dan has a question. Let's turn it over.
Hi. I have a question for you.
Sure.
So this IB thing, I'm confused about one aspect of it, which is there's this InfoMax objective, which says that you should maximize the mutual information between a representation and the input, and it's like an unsupervised learning thing. And so that's one thing, and that seems to be a positive thing that you want to increase. But I think it's the same quantity that appears in the information bottleneck. So is there a sense in which both can be good because there's the difference for the IB, or is it because we're doing different tasks, or is there some way of understanding the relationship of these things? I don't have intuition about IB, but I just realized that I'm confused about this. Oh no, the signs are correct here. I guess I looked at it. No, that's minimizing. So the signs are not correct.
Yeah, your question makes sense. So
thanks.
I've wondered about this too. I don't have a great answer, but my current thinking is that so here you're trying to minimize the information that you have here, but maximizing the information you have here, right? And you only can hear from Y through X. So in some sense, like that sort of difference is what information bottleneck is leveraging. And so obviously, like if you sent beta to 0, right? Like if you just minimize that information, there's just nothing to do, right? And maximizing it instead, can make sense in as much as X and Y are strongly correlated, right? So like you're the idea of minimizing here is only useful when you already are asking to maximize Y.
That makes sense. So I mean, they're different channels. So I guess it really is a supervised versus unsupervised question in that sense.
Yeah, I think so. Like this is really a supervised kind of objective.
And then the Tishby thing was which goes up first, or which thing are you doing first? I mean, maybe it doesn't matter because it's fake, but or I don't know. I'm not sure what we're supposed to believe at this point. But
what is he claiming? Like in this?
Yeah, which thing is supposed to happen first?
So memorizing happens first, where like you go to the right in the early epochs, where you're sort of increasing the input information you have, and then you go to the left where you decrease it.
Oh, I see.
Supposedly,
okay, so
all the time.
If you do that first before even any learning starts, then that's sort of on the same page, if you believe him. Like unsupervised, so you don't even learn any. Like the first thing you want to do is increase that. It sounds like you're saying.
Right. Yeah. If you just sort of started up here, by having information about the inputs, you'll sort of, tagging along. Hopefully, will be some information about the targets, right? And then you can sort of start pruning away and sparsifying out your information to just keep the stuff that you want.
Okay, cool. Thanks.
Sure. Yeah.
Hey, so maybe you mentioned this, but I was wondering how, in this case, the wire are labels, yes, but in the case, if like this framework has been studied or is like, what kind of things we can glean when y and x are like you instead of having like, oh, you're going to be trying to do this this representation learning type thing, get the best representation for this task. It's actually just like an autoencoder. Like, is there anything that you've like, if the y's are actually like the things themselves, would you be, you know, what do you sort of get from this framework, I guess?
So if the y's are essentially x.
Yeah.
Yeah.
So, yeah, it seems like you would just be.
So from the original objective, yeah, you can't say much, right? You just end up with you know, depending on whether beta is bigger or smaller than 1, you end up minimizing or maximizing that information. That said, with the variational IB, then, you know, after you do the variational approximations, you're doing different variational approximations on the two informations. So then you can put x. You can replace y with x here, and then you'll get a variational autoencoder back.
Gotcha. Okay.
So I think that's the most that I can say about it.
No, yeah.
Any more questions for David? Okay, so maybe not. So thanks again, David, for the instructive talk. I think it was really good to have a tutorial towards the end. That way we could follow. It's been a long summer school. Thank you all for attending. Hope you enjoyed it as much as I did, at least as much as I did, only lower bound. Yeah, enjoy the rest of your summer.